All right, welcome back. In this video, I just want to do a quick walkthrough of the curriculum, talk about what to expect. This course is a little different than others, including my other courses, in that it's not exactly linear. You don't have to go through every section in order. At the beginning of every single section, there is a text lecture, an article called Prerequisites, and that explains, at a minimum, the sections you need to have finished before you start the new section. And so let's just begin. The very first section, or technically the second one, but the first technical section is called Big O notation. Really important stuff. We come back to it in every single section from basically there until the end of the course. It's a way of describing or talking about the performance, the efficiency of code. So we use that all the time. So definitely don't skip that. Then we move on to a really quick section called Analyzing Performance of Arrays and Objects. Nice and short. We take what we just learned about Big O notation and apply it to some built-in data structures we work with all the time. So that's really quick. Next, we shift over to talking about interviews, algorithms, challenges. Basically, what do you do when you're confronted with a tough problem and you don't know how to solve it? Whether that's in an interview and you're at a whiteboard and you're panicking, or it's at home, you're working on a side project, or at work, how do you approach a difficult problem? And then the second sort of, what goes in tandem with that, these are two sections, problem-solving approach, problem-solving patterns. When we talk about patterns, we actually get into specific sort of archetypes for your code. They have different names, things like divide and conquer, sliding window, frequency counter patterns. These are all different patterns we describe. There's a lot of challenges. This first section that comes before is more about sort of setting up a framework for you to think and approach a problem. This is about concrete patterns. Then we move on to recursion. So recursion, a really important topic. Definitely don't skip this if you're not familiar with recursion. It comes up later on in many of our algorithms. There's also two challenge sections, sort of intermediate recursion problems and then tougher recursion problems that follow this section. Then we move on to searching algorithms, fun one. We talk about things like binary search here, if you've heard about that. Then we move to sorting algorithms. So I think we have 6 sorting algorithms at least, and these are kind of fun. If you've never worked with sorting algorithms, you've never heard about them, they have some odd names. We start with bubble sort, which is often considered the easiest or one of the easiest. We move to selection sort and then insertion sort. And those 3 form a little group, sort of the intermediate or elementary sorting algorithms. Then we move on to everyone's favorite merge sort. I like merge sort. A lot of people don't. Then we get to quick sort. So these all involve recursion. They involve Big O notation. So it's very important that you pay attention to the prerequisite little text lectures at the beginning of every section to explain what you need. And then we finish up with radix sort, a pretty rare sort. Very fast in a special situation, and not very often taught. Not in my experience. I've never really seen it taught. It's a fun one, though. I actually really liked it. So from there, we get to sort of the second section of the course. Up until this point, it's been about sort of stepping stones, recursion, Big O notation, problem-solving approaches, lots of algorithms, searching, sorting algorithms. Then we transition to data structures. So from this slide until the end of the course, there's a ton of different data structures we talk about. And this intro section compares them all. It tries to answer the question, what's the best data structure? And the answer is that there isn't one, but we talk about where they excel or certain structures excel. We also talk about ES 2015 class syntax. If you're not familiar with how you can approximate an object-oriented class using JavaScript, we talk about that in this section. Then I'm just going to run through these quickly. Singly linked lists, then we cover doubly linked lists. So if you've never heard of these data structures, very understandable, but we spend a lot of time talking about them. Then we move on to 2 more, stacks and queues, very commonly used structures. Then we go to binary search trees. Really, it's trees in general, and then we specifically hone in on binary search trees. Then we have a section devoted to tree traversal. So if you've ever heard the term breadth first search, depth first search, post order, pre-order, in order, depth first traversal, that's the kind of stuff we cover here. Important, somewhat intimidating, and again, it calls on things like Big O notation and recursion. It builds on linked lists. So a lot of this is interconnected, but you could also jump here and just look at the prerequisites and figure out what you need to learn. So then we go to binary heaps, which is it's very related to trees, but a very special case. We talk about building something called a priority queue. This is a fun section, in my opinion. Then we go to hash tables. I also like this section. Hash tables, we talk about a very particular data structure that what we're doing here is sort of understanding how JavaScript objects work, how they're implemented behind the scenes. How would you implement a key value pair data structure? And we talk about hashing algorithms. I think it's a fun one. Then we go to graphs, something that a lot of people are intimidated by. We talk about how you would model GPS, global positioning. Oh God, my cat. Hey, you can't interrupt me like that. What is it? GPS mapping, figure out how to find, basically how would you represent a map and traffic data and all these different variables so that you could create a GPS application or something like that. We also talk about storing social network data and one-way relationships, two-way relationships. We explore a lot of stuff around graphs, networks, routing. We talk about graph traversal, which, well, I won't get into too much. Same thing, breadth first, depth first, if you've heard of that. And then one of my favorite parts of the course, and one of the more complicated things we talk about, is called Dijkstra's algorithm. And this has to do with finding the shortest path between two nodes on a graph, two vertices. If that means nothing to you, well, this course is still definitely for you. You're not expected to understand what that is. But if we go back to the idea of GPS, say you want to get from point A to point B, from New York to Los Angeles. What's the fastest way to do that on the roads? If we have a complete map of all the roads, and let's ignore traffic data, just distances, what's the best way to calculate that? I mean, there's so many possibilities. So we learn an algorithm to do that, and we do basically an approximation of the same thing. It's this very famous mathematician and computer scientist, Dijkstra, came up with it, and that's what we talk about here. And this is sort of a pinnacle of the course, because we talk, it relies on big O notation, recursion, it relies on heaps, binary heaps, priority queues, stacks. A lot of things that we talked about earlier in the course come back in this last section. Oh, graphs, I forgot to mention graphs. So that's where we finish up. Really just to revisit this, there's a division right here, Intro to Data Structures, where everything else is focused on individual data structures from there on out. And before that, there's some really important stuff, sorting algorithms, searching algorithms. But no matter what, I recommend you start with big O notation, don't skip the recursion sections, and then from there, totally up to you. Just pay attention to the prerequisite lectures. You absolutely can go in order. I mean, it's designed in an order. It's not just arbitrary. But if you don't want to, sit through all of doubly linked lists, you could skip it as long as you did singly linked lists. Anyway, I'll see you in the course. Goodbye. I don't know how to end this. Bye. Welcome back. In this video, I want to address my developer environment. I'm keeping things really, really simple for this course. I'm not downloading any software. I'm doing everything in the browser. That doesn't mean that you need to do that. At this point, the only requirement for the course is that you know the basic syntax of JavaScript, that you're comfortable writing JS code. So however you do that up until now, I would just do that, continue on. But I wanted to show you what I'm going to do if you do want to follow along. So I'm using Chrome as my browser. I always do in all my courses. And Chrome comes with a little developer tool called snippets, JavaScript snippets. So here's Chrome. And I just open up the console. I usually use a shortcut on a Mac. It's Command Option J. But you can also go to Inspect, and then that takes you to the elements, and you can go over to the Sources tab. And then in the Sources tab, there's a Snippets sub-tab, I guess you would call it. There's a couple of them, but I have snippets as the only thing that shows. And you can see I have a bunch of named snippets. I'm recording this after I've finished writing and recording the rest of the course. So you can see, for example, here's one of our snippets. So I'm just doing everything in the browser here rather than using the terminal and running code with Node.js. You absolutely could do that. You could write your code in Sublime Text. You could use, I think there's equivalents to snippets in other browsers. You could use JSBin, CodePen. There's many options out there. Just run JavaScript. But to show you how this works, let's say I'm just going to make a new empty snippet. You'll see me do this a couple times in the course. I'll just call this demo snippet. And then in here, close that. I'll make it a little larger, and then just do some really simple thing like console.log hello from the snippet. Oh my gosh, cannot spell here. Okay, so let's leave it at that. And all I have to do to execute this code is either go down here and click play, but also it shows me the shortcut command return on a Mac, and on a PC it will tell you whatever the respective equivalent is. So when I hit that, I'm going to do it right now. If I scroll up, I should see, there we go, hello from the snippet. So you'll see me do this throughout the course. For example, I might run this snippet here, and it doesn't matter what it does. It's a binary search tree, breadth first search. If I hit command enter, it just ran, and you can see this was the output. This is what was returned. And that's pretty much all I have to say about Chrome snippets. So you'll see me work with them frequently. I have a bunch of them over here. I usually make a new one for each thing. So here's a doubly linked list. We add a set method, and then I'll make a new one when we add a remove method, for example. But that's all I'll say for now. It's a very easy way for me to run code in the browser that everyone can do. You don't have to download anything. It's not Mac or PC specific. But also, if you know how to write JavaScript, which I hope you do, to take this course, you should know the basics. You might just want to continue on with whatever you're most comfortable with. This is not a requirement for the course. We're writing basic JavaScript. Run it however you prefer. Okay. Hey, welcome back. So this is the first real section of the course, and we're kicking it off with something really important, something big. It's called Big O notation. And when I say big, I don't mean that it's long or difficult even. It's big in significance. It's something that I had no choice but to start the course off with this topic because, at least if I wanted to make it a good course, because it's going to come up in, I won't say every single video, but maybe 70% of the videos in the rest of the course. Don't hold me to that, but a lot of videos, a significant number. We're going to refer back to what we talk about in this section. So before I even explain what it is, I have a quick warning. There's a bit of math in this section. And I'm warning you not to scare you away, but actually to encourage you to push through it if you do struggle with math, or if you're someone who hasn't heard the word logarithm ever or in 10 or 20 years. That's going to come up in this section at the end, but don't panic, because what we're going to do here in this section is establish a framework for talking about code in the rest of the course. And that does involve some math up front, but it means that the rest of the course isn't going to be, some of it will be mathy, definitely, but this is not indicative of what the rest of the course will look like. So just push through it. If you like math, great. If you have some problems with this section, just remember that the entire course isn't like this. And we're just getting it out of the way because, like I said, it has to come first. I don't really have a choice. Okay, sorry if I scared anybody there. Let's talk about the objectives for this section. So in this video, we're going to start by just talking about the need for something like Big O notation. I haven't even mentioned what it is, so we're going to get to that. Then we're going to describe what it is, so why we care about it, what it is. We're going to learn to simplify Big O expressions. We'll define time complexity and space complexity. We'll evaluate time complexity and space complexity of different algorithms using Big O notation. And then we'll describe what a logarithm is, a bit of math at the end there. So I know it's a lot, but we're going to start with this first bullet point. Motivate the need for something like Big O notation. So what is the idea here? Well, this course is about algorithms, it's about solving challenges, it's about computer science and data structures, but for every topic in this course, there's 10, 20 different implementations or solutions that could work, probably way more. How do we know what's best? So let's scale it down a bit just to a single problem. Let's say that there are two valid solutions to a problem. They both work and they're different, not just in names or variable names or something, but totally different in approaches. One uses a loop, the other uses, a list or a string or something to accomplish the same task. How do we know which one is best? That's really what Big O is about. It's a system, it's a way of generalizing code and talking about it and comparing code and its performance to other pieces of code. Okay, so here's a more concrete example. Write a function that accepts a string input and returns a reversed copy. If I asked you to do this, which maybe some enterprising students will do this and come up with some creative solutions, off the top of my head, I can come up with 3-ish solutions, different approaches, and I'm sure there are way more out there. I actually found this post on Stack Overflow that has 10 different implementations in JavaScript, and they're all different. Like I said, it's not just a different variable name. It's not just switching a for loop for a while loop. There are different approaches. How do we know if all of these work? Here's one using a for loop. and an array. Here's one that uses no loops and it's no arrays. It's all, actually, I guess there is an array in there at one point, but it's all built-in methods. How do we know which one's best? Well, we'll get there. But wouldn't it be nice if there was sort of a system for classifying code or for comparing it, which I've already spoiled it and said that's what big O sort of is. Think of it sort of like if we're talking about earthquakes. If this was a seismology 101 class, very early on, I would start off by talking about the Richter scale, because then that allows us to talk about earthquakes and compare them to one another, so that instead of just saying, oh, there's a big earthquake and then a bigger one over there, we can say there was a 7.5 and then a 9.2 over there. And that puts things into context. It's kind of not a great analogy, but the idea is that we can assign labels, generalized labels to our code. So instead of saying something like great or or awful for our code, we can have a numeric representation of the performance of code. So that's what big O is going to give us. Rather than colors and text like great, it's going to look a little bit different. It might look a little mathy, but it's actually pretty straightforward once you get past the first hurdle of it looking very foreign and weird. So one last point I want to make. Some of you might be wondering, if I asked you to write a function that reverses a string and you get it to work, doesn't it only matter that you get it to work? Like, why does it matter what's best? The solution you come up with is the best. And in some ways, I think that depending on your project and the context, that's true. The best solution is the one that you can get to work. But when we're talking about things like interviewing, technical interview, code challenges, or you're working at a large company where you're working with a huge data set, let's say hundreds of millions of pieces of data, where one algorithm implementation could save an hour every time it runs compared to another implementation. Performance matters at that point, and there is an actual best algorithm or best solution. So it's important to have a precise vocabulary to talk about how our code performs. So even if you're content with your solution to something, it's helpful to be able to understand how it compares, how it performs compared to others. It's also good for discussing trade-offs between different approaches, because often it's not as cut and dry as I made it seem. It's not that one solution is always great and the other one is always terrible. Sometimes one solution might be great at handling really large data sets, pieces of data. Another one might always be very consistent in the time that it takes, but it might take more time up front. There's trade-offs, so it's not always just this is the best. Also, if you're trying to debug your code, it helps to understand things that are slowing it down. Not just looking for errors, but let's say that your code is working, but for some reason it's taking a lot longer than you expect, or your computer is lagging and freaking out in the browser when you execute some function. It helps if you understand some of the things we're going to talk about in this section in big O notation. You can actually pinpoint where some problems might arise. So it helps us identify inefficient points. And then finally, you should care, because it comes up in interviews a lot. A lot of times an interviewer will say something like, tell me the big O of this algorithm or of this function that you've written, or here's 3 functions, what's the big O? That will make sense in a bit, but it's important just to know for interviews. I said it's less important because hopefully you're learning it to actually understand things and to help you understand your code better and talk about your code better, rather than just directly trying to master it for an interview. But interviews are important, so no judgment there either. So I'm going to leave this video off here. I'm trying to keep things more compact. Don't want any rambling videos. In the next video, we're going to pick up with a real example, some code, and start to analyze how efficient it is. All right, so let's take a look at a more concrete example. Let's compare 2 solutions to the same problem. All right, so here's our problem. Suppose we want to write a function that calculates the sum of all numbers from 1 up to and including some number n. So if we plug 3 in, we should get 1 plus 2 plus 3, which is 6. The most common, or the easiest to come up with solution, this is the one that comes to my mind first, is to basically create a total variable, a accumulator, and loop through all those numbers and add them in one at a time, starting at 1 all the way up until n. So that's what I've done here. We have a for loop, total variable starts at 0, and at the end we return total. We start the loop at 1, we go up until n, each time through, total plus equals I. Okay? And I actually have, there we go, I have it open as a snippet here. If you're not familiar with snippets, Basically, it's a way for me to just, rather than copy and paste code into the console and have to deal with losing it and rerunning it and that pain, in Chrome, you can go to the Sources tab, and then there's a Snippets tab you can click on, and it allows you to create new snippets. I have a couple of them here, and I'm going to use them in this course quite frequently as an easy way to save code and execute it. And just to show you how it works, here's the same add up to function, and I'm printing it out at the bottom, the result of adding up to 6. So that should be 6 plus 5 plus 4 plus 3 plus 2 plus 1. To execute it, I can either click over here, or you can see the shortcut it suggests to me on a Mac is Command Enter. It will say the correct shortcut on a PC. I think it's Control Enter. So if I do that now, I get 21. If I did it with 3, there we go, I get 6. If I did it with 100, I get 50/50. Okay, so that's just to demonstrate that that works. Next, there's a second solution. There's more than these two, but these are two that I'm going to use because they illustrate my point. This one is definitely less intuitive. As you can see, it's a lot shorter. It's a single line, which doesn't necessarily make it better, but it's very different. There's no loop involved. What we're doing is, it's more of a mathematical formula. We take n and we multiply it by n plus 1 divided by 2. And where this is derived from, I'm not going to go into. I do have slides on it, or a slide that talks about how we arrive with this formula. If you want to check it out, you can, but it's not the focus of this video. So I don't want to distract from the actual focus, which is evaluating and comparing these pieces of code, not actually diving into how we write them. So just to show you this one, it does work. I have another snippet over here. I can run the same thing. Let's do it with 6 again. And I'll do Command Enter to execute, and I get 21. And just to walk through what happens there, it's the equivalent of taking 6 plus 1 first, which is going to give us 7. And then we multiply that by 6, which gives us 42. And then we divide by 2, which gives us 21. So it does work. It gives us the same answer in the end. Again, how it works, we'll leave that be. All right, so we established there are two working solutions. Which one is better? And of course, the first thing that we could ask is, what does better actually mean? Does it mean the faster code in seconds or milliseconds? Does it mean the code that's fastest when we're adding a small number versus a large number? Let's say we want to benchmark it at when we add up all the numbers between 0 and 1 billion. Is that a good test? Or is it about how much memory is used? Is it, the number of variables that are created, the data that is stored each time that function is called? Or what about something like readability, legibility? How important is that? Is that better? Or brevity, that's not on here, but a lot of people care about that. They like to minimize the length, the number of characters used in their programming. Not my style personally, but definitely valid. All of these are valid concerns, and it really comes down to the situation. But I think most people would agree that the first two, especially for now, we're going to focus on speed. We'll come back to memory usage in a bit, but these two often can be more important than something like readability. And unfortunately, they often come at the expense of readability, and that's sort of the balancing act of writing good code, is writing efficient code that doesn't use up a ton of memory, but also is still readable and doesn't look like complete gibberish. So we're going to talk about basically how all of these play together throughout the entire course. It will be a recurring theme, but we're going to focus on evaluating speed, how long code takes to execute. That's where we're going to start. So how do we do that? Well, the simplest way would be to use something like built-in timing functions, something like this, where we have our first add up to, and then I use a function or a method called performance.now, which in the browser is just going to tell me the number of milliseconds since the document was created, basically since I opened the window. And then so I'm going to save that to a variable before I call add up to. Then I'm going to call add up to with, what did I do? Is this a billion? I think it's a billion. So I'm going to call it with a large number. And then after that finishes, I'm going to check performance.now again, which should have incremented a bunch of milliseconds, most likely. So I have two numbers. Then I just subtract them, the second time minus the first time. And I divide it by 1,000 because it's in milliseconds and I want to work in seconds. We don't have to do that last part. And I print it out. So this should work. And I actually have a snippet right here. Same thing. So add up to our same one from before. And we're calling it with 1 billion. and we're going to print out how long elapsed. Let me clear my console first, and I'm going to execute it. There we go. 1.2575 so on seconds. Let me do it one more time. And what you'll actually see, I don't think I executed it, there we go, is that it varies. So it changes. Even on my own computer, nothing really has changed. Right? I haven't added code, I haven't changed the numbers here. It's the exact same code, but we're getting a different output. Before I forget, let's go over to this second solution. So the exact same number, let me just make sure I didn't leave off or add a 0. Yes, they are the same. And I'm doing the same thing, taking performance.now at the beginning and performance.now at the end. I guess I should show what that looks like. You can see that it's kind of a large number at this point because I've had this open for a number of minutes. If I refresh the page though, which I just did, now it's at 2000 milliseconds, which is 2 seconds. And now if I did it again, we're at 6.6 seconds. And if we subtract the 2, it's 4 seconds roughly in between. Anyway, we're doing the same thing here. Okay, so now if I run this, you can see we get a way smaller number. But it's still, actually, I guess it doesn't look like it's changing here, is it? The measurements, the differences are too small, not really to capture. But my point is that this is significantly shorter in duration with the same data as this one. Here we go, 1.24 seconds compared to basically 0 seconds. So that seems like a good sign for this solution. It seems like it's much more efficient, and that's great. But this process, it's not the most reliable of manually timing things like this before and after and comparing it to the other function. And it's not that easy for us to talk about. How would I actually write down, how would I give it a label of how efficient this one is compared to this one? Is it based off of the percentage of speed? Is it do I subtract the number of seconds or milliseconds? It gets a little blurry. This brings us to the problem with time, which I'm reserving for my end-of-life memoir title, The Problem with Time. It's just a nice little, sounds very deep. So the first is that different machines will record different times, so it's not reliable. Depending on the specifications of a machine and what's currently happening on that machine, what code is running, the results you can get will be different. That doesn't really mean that we'll get the opposite results where the first solution is suddenly faster than the second one, but it means that the margins could change. The actual measurements could be different and are almost guaranteed to be different times. And as we saw, the same machine will record different times. So in my browser, I just did the exact same code, that first example, and it differed each time by a little bit, which isn't really a problem, but it still shows that it's not precise and that we can't rely on that. And second of all, or third of all, I guess, is that for fast algorithms, things that are happening on a really, really fast scale, speed measurements might not be precise enough. We have 2 or 3 or 4 algorithms and they're all super fast and they're doing something very quickly. There still is one that is going to be fastest or most efficient. But if our timing functions can't figure it out because they're, the smallest interval of time that can be measured isn't good enough, then it doesn't really help us. So how do we walk through our code and actually talk in general terms about which code is better without having to go and time it? So I want to be clear, I'm not saying that timing your code is a bad idea. I do it all the time. What I'm more saying is that it would be cool if there was another way that didn't involve having to set up a new file and actually go through the process of timing our code. What if our code takes, an hour, something massive, and I'm comparing it to another version that takes 4 hours? I don't want to have to run a test to figure out which one is faster. We want to be able to assign a value to, in general terms, talk about how code compares to other code without having to go through all of this. And that's where big O notation comes in. And that's coming up next. Cliffhanger, sorry. Okay, well, we talked about the problems with using time as our way of comparing code. So if we're not using time, what should we do? Well, it's a very similar thing. Rather than counting the exact seconds that it takes for code to run, which can change so much, what we can do instead is count the number of simple operations that a computer has to perform, because that remains constant no matter what computer we're on. So if we just simplified it like crazy and said that, this one algorithm has 5 operations to run and the other one has 7, it doesn't matter what the specifications of my computer are, or the mood that my laptop's in that day, the time we get might be different, but the times will always be determined by the number of operations. So we can use that rather than the exact times. We can just focus on the number of simple operations the computer has to perform. So what I mean by simple operations, if we take a look at this example, the shorter one-line version that was faster. We've got a multiplication happening. We have, after that, an addition. So that's another operation. And then we have a division. Things like the number 1 or 2 aren't operations. The computer doesn't really need to do much there, at least compared to multiplication, addition, and division. Those are operations. So there are 3 operations, and it doesn't really matter what n is. If n is 2, or if n is a billion, there's only 3 calculations that are happening. So 3 simple operations regardless of the size of n, whether it's small or massive. If we compare that to our other solution, the first one, this one has a few more operations. So let's start here. We see a plus sign, which we saw in the last video, and we counted that as 1 operation. But there's a difference here because this is in a loop. So if n is 5, we're adding 5 things. So that's 5 operations. If n is 20, there's 20 pluses. If it's a billion, there's a billion pluses. So it's not just 1 operation anymore. It's n operations. N additions. And actually, it's more than that because the equal sign is it's an assignment. Now, I hope you definitely shouldn't get too bogged down in the details of counting every minute operation because, as you'll see in a moment, all that matters is the general terms of things, a very, very fuzzy overview. So this distinction doesn't really matter. But to be clear, yes, this is another operation, and it happens as n grows. There's more assignments that happen. So quickly running through these, we've also got this here. So plus plus is shorthand for I plus equals 1. So there's a plus in there and there's an equals. So 2 simple operations. However, they happen 1 time each per n. That's not a good way of saying that. They happen more as n grows. So if n is 10, we've got 10 additions and 10 assignments. If n is a billion, we've got a billion. So they scale with n. Then up here, we've got 1 assignment. So this only happens once, because it's not a loop. It happens 1 time at the beginning. And then we also have this here. This is a single assignment. I equals 1. That happens once as well at the beginning of the loop. We start with I equals 1. And then we've also got comparisons here. I less than or equal to n. And that is n comparisons again. If we're dealing with 20, this loop runs 20 times. We compare I to n 20 times. So yeah, counting these operations can be tricky. Overall, how many would we say there are? If the previous one, there was 3 operations, what do we say about this one? I mean, it's not a static number. It's not a constant number like 3. So how do we generalize it? There's a lot of ways of counting it and of arriving at an answer, but it could be as high as 5n plus 2, right? 1, 2, 3, 4, 5 plus 2. So if n is 10, we've got 50 operations plus 2 that are outside the loop, so that means 52. That's one way of doing it, but what I want to say is that it doesn't really matter, because regardless of the exact number, whether it's 5n plus 2 or 2n or 3n or even 50n, it doesn't matter, because what we care about is a general trend. And this is what we're going to see a lot with big O. We're focused on the big picture. So in this case, as n grows, the number of operations grow roughly in proportion with n. Okay, so this will be a really quick video, but I want to show something I'm kind of proud of. This is a little widget that I've made that helps us understand or plot the time that functions take to execute and get a general graph, a chart that shows us a trend. So there's only 7 of them in here, and we're going to focus on the first 2. Add up to first. I had to give them unique names before they were both called add up to, but add up to first uses the loop. Add up to second uses that little shortcut. Let me see if is that big enough to see. And so we select one of them. Then I can specify a value for n and hit plot and then change n. And what I'll do is increase n, and we'll see some sort of chart that shows what happens as n grows larger. And this is basically just done with a timer in the background. So I click plot, starts a timer, it does the operation, stops a timer, and then plots it. And then we do it again, and it connects the dots and builds a little graph. So what I want to show you is that if we take this first one, add up to second, which was the one that was faster, we already know it's faster. But what we talked about in the last video is that there are 3 operations, 3 things that take time. Let's think about it that way. This other one, there's a lot of things that take time. But this, there's 3, and there's always 3 things that take time, no matter what n is, if it's 10 or a billion. So I'm going to plug in a number for n, like 100, and I'm going to hit plot. And it's going to time it. So what it's plotting for us here is not the number of operations, because that's always 3. It's plotting the time. Okay, so we only have 1 value, so it doesn't really mean much. Let's add in 1,000. There we go. Let's add in 10,000. Okay. So it does seem like this is an extreme slope all of a sudden, but just hang in there because we pop back up. And if we look at the difference here, it's a matter of, what are we talking about? Is these, I can't remember if these are nanoseconds, what that little symbol means. It's a very small fraction of a second. So it looks like this chart is all over the place, and it is on such a small scale. But what I want to show you is that we don't really care about that. We care about a general trend. And when we switch over to add up to first, I'm going to do the same thing, but I'm going to start again with 100. So we're going to add up the first 100. And remember that in this case, unlike add up to second, where it was a constant number of operations, and add up to first, the number of operations depends on n because of this loop. So if we start with 100, okay, you can already see that it's definitely slower. Let's go to 1,000. All right, definitely looks slower again. 10,000. Keep going here. Keep adding in. I'm going to keep going so that we can get a generalized trend. Okay, and that last one took a little bit, and the next one will take a couple seconds, so I'm not going to do it. But what we can see here is that there's a pretty good line that's pretty easy to follow. And as n grows larger, which is down here, the time grows in proportion, which we kind of discussed in the last video, although we were talking about the number of operations. But this is actually time being printed here. And you can see that it follows what we were talking about. It's not perfect, but overall, it's pretty close. And same thing down here, where we said that for add up to second, it's always 3 operations. It's the same number of operations no matter what n is. So the time is pretty constant. It fluctuated, as you saw when we were working on such a small scale. It did go up and down. But overall, when we're comparing the two, this is significantly better. And if I run this last one here, I mean, take a look at that. As n grows, the time doesn't really change. Now, if we zoomed in, it would be slightly different, but it doesn't matter because this is a massive difference, 1.2 seconds versus a couple of milliseconds. So we'll be revisiting this tool to talk about some of these others as we go. But here are our first 2 generalized trends where we're comparing 2 algorithms that do the same thing. And you can see that they have vastly different big picture overviews of their performance. All right, so we finally actually introduced the term big O. We've basically been talking about big O without actually saying the term big O notation. So let's actually, let's reveal it now. So big O is just a way of formalized fuzzy counting. It allows us to talk in a very formal way about how the runtime of an algorithm grows as the inputs grow. That's it. It's a way of describing the relationship between the input to a function or as it grows and how that changes the runtime of that function, the relationship between the input size and then the time relative to that input. So we don't care about the other details, only the broad trends. So we've already been talking about broad trends. We talked about, okay, as n grows here, in this first solution down here, it doesn't matter. It doesn't impact the time that it takes. But in our second solution, which is confusingly called add up to first, as n grows down here, the runtime also grows in proportion, roughly in a linear 1-to-1 pattern with n. So that is big O, what we've been talking about. We just haven't actually been using the correct label. So here's a bit of scary text. We say that an algorithm is big O of f of n if the number of simple operations the computer has to do is eventually less than a constant times f of n as n increases. It's a bunch of gibberish, really. What it's saying, though, is that there's a bunch of these. I'm just going to put them all out here for now. There's a bunch of options. If you haven't seen this notation, by the way, this just means a function with an input of n and then the output. So we're describing the relationship between the input and then the runtime. So it could be linear, meaning that as n scales, the input, the runtime scales as well, which we've already seen. It could be something different. It could be quadratic, where as n grows, the runtime square is related to the square of n. Or it could be constant, which we've already seen as well. As n grows, it doesn't really have an impact because runtime is always constant, which we simplify down to 1. Or it could be something entirely different, and we'll get to some of these other options later on in the course and later in this section. You can always come back and just think about it as when n grows, as an input grows, what is this chart going to look like? Is it going to grow roughly proportionately with n? Is it going to be constant? If we had a square, it would, be a lot steeper than this. One thing I want to highlight is that when we talk about big O, we're talking about the worst case scenario. So we're talking about basically the upper bound for runtime. So let's revisit our examples from earlier. This first add up to, where we only had 3 operations, and it's constant. It's always 3 operations. So the line we looked at was this one down here that roughly is constant. Remember, in the real world, it's not. It goes up and down a little bit, and runtime does vary, but overall the trend is that it's flat. So we could say that this has a big O of 1, and this is the notation that we'll see. So when you see a big O and then in parentheses, you see 1 or you see n or n squared or n log n or log n, things we haven't gotten to, that is telling us that as n grows, as the input to this function grows, in this case, it has no change. It's not reflected in the runtime. But if we take a look at this one, add up to n, same name, this was the one that had a bunch of operations that are happening where we said that it grows as n grows, the runtime grows, basically in a 1-to-1 ratio. The number of operations is eventually bounded by a multiple of n. It doesn't actually matter if it's 1n or 5n or 50n, because at the end of the day, we simplify it down just to n. And we're going to talk about the rules for simplifying these expressions. But basically, we're concerned with just the order of magnitude. So we don't care if it's 5n or just plain old n. It's the same when we're charting it on a massive chart and we're zooming way out and we're just carrying in a fuzzy way, I guess is what you would say. So here's another example we haven't seen. It's called count up and down. And all that it does, I'll just copy it over. I don't actually have a snippet for it, but let's just plug in 10. Okay, so our output is going up 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. At the top, going down 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Back down. All right, so if we were trying to figure out the big O for this function, we'd start by saying, all right, so here, as n grows, we have roughly n operations. We have a loop, so there's big O of n here, because this, as n grows, this loop grows. Same thing down here. As n grows, this loop grows. It's just doing the same thing in the other order, going back down. So you might think that the big N is 2n, but remember that we don't care about that. We care about the big picture, so we simplify it to big O n. So if we go back to our performance tracker, I do have count up and down added in here. So let's plot it out with 100. Let's do 1,000, 10,000. And you'll see, I think that's the last one I'll do. It's taking a while. The next one will take forever. There we go. And you can see there, we get that chart that we discussed. This is the big picture of anything that has big O of n. And we have one more example. And this one's different. We haven't seen this yet. So we have a nested loop. So what it does, it's called print all pairs. And if I plug in 5, it's going to print every pair of the numbers 0 to 5. So it'll be 0, 0, 0, 1, 0, 2, all the way up to 5, 5. And I won't show you the example, but you can trust me, that's what it does. And there's 2 loops. And just like we discussed with the loop, this loop is based off of n, this first one. So that's big O of n, right? As n grows, this is going to be n number of operations, roughly. But then we have a nested loop, which is also the same thing, O of n, which just means that as n grows, this loop. The number of times it runs grows as well. But this is not O of 2n, which simplifies to O of n, because it's nested. And that gives us something else. An O of n operation inside of an O of n operation is O of n squared. So what this means is that as n grows, the runtime roughly grows at the rate of n squared. So that's a pretty significant difference. And if we plot it out, which we will in just a second, you'll see that. But hopefully that makes sense. I don't know why I paused there. Hopefully that makes sense of why there's such a difference. Because if we step through this, if n is, let's just think about the number of pairs. If n is 2, we have the pair 0, 0, we have 0, 1, then we have the pair 1, 0, and 1, 1. So there's 4 pairs. But if we increase n to 3, all of a sudden we have 9 pairs. I won't go through them all, but it increases very quickly. If we increase to 4, we've got 16 pairs. So I said I wouldn't do this, but I added it into my console, print all pairs. If we do 2, there you go, we get the 4 pairs. If we do 3, we get a lot more, 9. Now if we go here and plot this, print all pairs, I'm going to start pretty small and do 10. I'm not even going to go to 100 right away. Let's do 50. Now let's do 100. Let's do 120, 150. All right, so you can see what we're working with here. And I'll try 200. It might take a little while. Okay, I'll leave it at this. This is a different overall trend, a fuzzy version of the chart. We're not looking at a linear thing where as n grows, the runtime is roughly proportionate. It's proportionate to n squared. So as n grows larger, the runtime grows even larger. It grows n times n larger, roughly. And just to show you this, if I increase this to 300, it's going to take a lot longer. And I think I was playing around with 500 earlier, and that was about as much as my computer browser wanted to do at the time. Oh dear. Okay, so there you go. You can see that this, what used to look very steep, now that we've added in 500, it doesn't look so bad, and now it looks really steep, which is the exponential curve. Remember that it's just a generalized way for talking about how efficient an algorithm is. As an input n grows, how does that change or reflect in the runtime? So we've seen a couple of options. We saw add up to first, which was basically big O of n. As n grew, the output, the runtime grew relative to n. Then we had up to second, add up to second, which was constant. It always took roughly the same amount of time. Then we had count up and down, where it was the same as add up to first. If n grows, if it triples, then our runtime is roughly going to triple. And then finally we saw print all pairs, which was our first quadratic, O of n squared, where as n increases, the runtime increases roughly at the rate of n squared. So I'm hoping I didn't lose you there. If I did, well, we have some exercises after this. Hopefully it will help out a little bit. I recommend that you play around with that tool, but be careful because if you plug in super large numbers, it will take forever and or crash your browser window and you'll have to quit that window. Just a word of warning. All right, welcome back. So now we're going to talk more about simplifying big O expressions. We've already seen a little bit of this. I'm going to rewind. Here we go, a couple slides back. If you remember this slide, where we talked about how counting all these different operations can be tricky and that it doesn't really matter the exact count. All that we care about is really the general trend. And so we simplified this from 5n plus 2 to just n. We said that as n grows, the runtime grows proportionately with n. And it doesn't matter if it's 2 times n or 10 times n or 1,000 times n. The trend, the line that we're drawing on that chart, is proportionate with n. So now we're going to talk about some actual rules we can use to help us when simplifying these expressions. There are some helpful rules of thumb that we can follow. Rule of thumbs? Rules of thumb? Rule of thumbs. Okay, whichever one it is. These rules are consequences of the definition of big O, once again, that we only care about the broadest, fuzziest, big picture view. So constants don't matter. So if we have something like O of 2n, we simplify that down just to O of n. O of 500, we simplify that just to O of 1. Because O of 500, remember, is just That's basically saying there are 500 operations every time, no matter what n is. And so that line, that chart, is going to be flat. And instead of saying it's going to be flat at 500, we'll just simplify it down, saying that it's O of 1. That's how we say something is constant runtime. O of 13 n squared. Well, we don't need that constant. We just do O of n squared. Because the difference, when we're looking at this, basically if our graph went all the way to infinity as far as n, and we're looking at the difference between 13n squared and just n squared and 1000n squared, they're all going to look very, very similar once we elongate that chart to that level. So it doesn't really matter. So we just get rid of them, because now we can compare these and we know that, okay, this is going to be faster than this, and this is going to be the slowest, just based off of their charts, the general fuzzy trends. So smaller terms also don't matter. The constant's out front, in front of n, but smaller terms like this, O of n plus 10, just get rid of the 10. It's O of n. Or in this case, O of 1000n plus 50, can simplify that just to O of n. We don't need the constants, and we don't need the small term at the end. Now, how about this one? N squared plus 5n plus 8. Well, once again, look at it from a huge, like imagine we're in outer space looking at this chart, and we have to figure out what really matters. What's the trend? At the end of the day, 5n plus 8 is meaningless compared to n squared. When we're dealing with a number, like if you just plug in the number 1000, 5 times 1000, 5n, gives us 5000. But n squared, 1000 times 1000, is 10 million. I think I did that right. So if we're talking about 10 million plus 5,000 plus 8, just as an example, the difference between 10 million, 5,000, and 8 versus 10 million is so small. And that's just when we plug in 1,000. But now imagine we plug in a billion for n. That difference is going to be meaningless from the big picture view. So we just simplify it down to O of n squared. So a couple things that you can keep in mind. When analyzing complexity with big O, things get complicated and you can nitpick and stress out about the individual details. But there are some rules of thumb, again, that can help. And they don't always work, but it's a good starting point. The first is that arithmetic operations are constant. So if we're adding something or subtracting or dividing and so on, that's going to be constant time. It doesn't really matter the size of the number. Your computer takes roughly the same amount of time to do 2 plus 2 as it does a million plus 2. Variable assignment is also constant. So your computer takes roughly the same amount of time to make a variable, x equals 1,000 compared to x equals 20,000 or a million. It's roughly the same. Accessing elements in an array using an index. So if I have an array and I want to find the first item or the 10th item, as long as I use the index, or I'm working with an object and I have a key that I'm using to access data, that's constant runtime as well. The next rule is that in a loop, the complexity is the length of the loop times the complexity of whatever happens inside the loop. So if we're working with a loop that's looping over a list, or it's looping through, like we did earlier, 0 to n, as n grows, that loop grows. But then whatever happens inside that loop is also consequential, because if we have nested loops, as we've seen, then we end up with potentially n squared runtime. So again, you don't need to memorize these, but it's just nice to, I'm going to throw them out there so I can come back to them. So let's see a couple examples. Here's a new function. It's called log at least 5. Let me just copy it over. I paste it in, and if I call it, I pass in a number like 10, and it's going to log 10. But if I plug in 1, it prints 1, 2, 3, 4, 5. So all that it does is it prints numbers up to n, but at a minimum, it prints 1, 2, 3, 4, 5. So if I give it 3, we still get 5. But if I give it 7, we get 7 printed out. 1, 2, 3, 4, 5, 6, 7. So what's the big O here? How would we categorize this? So we have a loop, and this loop is going to go from 1 to either 5 or n, whichever one is larger. So we could worry about the 5, but we only really need to worry about that as n is small. And what we care about is what happens as n grows larger. So as n continues to grow and grow and grow towards infinity, what happens to the runtime? Well, if n is 10 million this loop is going to run 10 million times. This 5 doesn't matter. So we can just simplify this and say that the big O of this is O of n, because as n grows, the number of operations grows in proportion with n. So here's another one. This is the opposite. Log at most 5, paste it in, and if I try, there we go, at most 5, if I plug in 30, it still only gives me 5. If I plug in 3, it gives me 3. So it's going to take whatever is smaller. If I give it a large number, if it's larger than 5, it's only going to log 5. If I give it something less than 5, then it will log. Oh, it's also important, it's only with positive numbers. So if I give it 0, it doesn't do anything. And that is important to note, because as n grows here, it kind of doesn't matter, because we're going to take the min, which is 5. So if n is approaching 1,000, this loop runs 5 times. If n is approaching 1,000,000, the loop runs 5 times. If n is 2, then the loop runs 2 times and 3 times. So the graph would actually look like, 2 and then 3 and then 5, and then it would stay static at 5. And we can simplify that by saying that as n grows, which is what we care about, the big O of this is just constant. It's O of 1. So rather than O of 5, remember, we can simplify that down and say O of 1. So if we were to plot both of these out, what we see, the general trend, is something like this, where, I forgot I have all those little transitions. We can ignore all these other ones. We haven't talked about things like log n and n log n, but what I've done here is just put them all on a chart. So we can see, first of all, O of 1 is a flat line. And that's great. If we can have runtime O of 1, that is fantastic to have constant runtime. It's pretty rare when we're dealing with some more advanced algorithms. Something like O of n is okay. You can see the general trajectory. It's much better than something like quadratic n squared runtime. So when we have something like log at least 5, as n grows this direction, the runtime is also going to grow. And when we have at most 5, the second one, which we said had constant runtime, as n grows, once we get past the first little 1, 2, 3, 4, once we get past the first 4 and we approach infinity, n is going to always be 5, which we just say n is always constant. So I know that this is a lot, and some of you might be struggling with it, and that's to be expected. What I think is most important going forward is that if I say something like this algorithm that we've just written has a runtime of O of n squared, that you could identify that that is not as good as something like O of n, for example. And I could show you this chart, but I just hope that you can understand after the end of this section, we're not done yet, but by the end of this section, what it means when I say that something has O of n or O of 1, constant runtime, and how that compares to some of the other options. And like I said, we haven't gone over all of these yet, so we'll get there. Next up, a couple little exercises simplifying expressions. All right, welcome back. So now we shift gears a little bit, and we're going to talk about something called space complexity. Everything we've talked about so far, we've been worrying about time, about how fast algorithms run, what the runtime is. That's called time complexity. We've been analyzing the runtime of an algorithm as the size of the input increases. Now let's talk about what happens to the space that an algorithm takes up as the size of the input increases. So we can still use big O notation for the same thing, use the same formal syntax for describing what happens, but now we're going to focus on space, the amount of memory that's taken up. So there's some basic things we have to get out of the way. One is that obviously as n grows, if we're approaching infinity, the size of the input itself, which is n, is going to grow. So we're going to ignore that part. You might hear the term auxiliary space complexity if you do some research, if you read Wikipedia or something. That refers to the space required by the algorithm only, not including the space taken up by the inputs. That's what we're going to talk about. We care about the algorithm itself because our n is growing. That's the in big N or in big O. That's kind of the point. We're going to say that as n grows, we assume that the input n is going to grow. So let's not care about that space. Let's care about what repercussions that has inside the algorithm. So unless otherwise noted, when we talk about space complexity, technically we're talking about auxiliary space complexity. Hopefully that's not too scary, but basically it just means we're focusing on what happens inside the algorithm. So some basic rules of thumb. The first is that most primitives, things like booleans, numbers, undefined, null, and JavaScript, are constant space. So it doesn't matter what the size of the input is. If the number is 1 or the number is 1,000, we can consider it constant space. It doesn't matter if a Boolean is true or false, it takes up the same amount of space. Strings are a bit different because they require O of n space. So if n is the length of the string, if we have, the input grows to 1,000 characters, well, that's a bad example. If it grows to 50 characters, the string takes up 50 times more space than a single character string. Same thing with reference types, arrays, and objects. So generally, we're talking about O of n, where n is the length of the array, or the number of keys for an object. There's not really a length technically, but so if the length of an array is 4, compared to another one that is 2, it takes up twice as much space as the shorter array. So let's take a look at an example. So here we're focusing on not time complexity, we're focusing on space complexity. So this function called sum, it takes an array and it just sums all the items in the array. So we have a variable total, starts at 0. Then we have a loop that goes from 0 to the end of the array, and we're just adding in the value of each item in the array to the total variable, and then we return it at the end. So again, space, not time, is what we're concerned about. So what are the things that take up space? Well, no matter what the array length is, we have one variable called total, one number. And then we're looping through, but we're not concerned about the time again. And then we have a second declaration inside the for loop, let I equal 0. So that's another number. And that's it for space. We're coming back to the total variable, we're adding into it, but that doesn't matter. That takes time, but the space is already there. So no matter what the size of the array is of n, or in this case ARR, as it grows, it might be 1,000 items, it might be 1,000,000 items, well, it might be 10 or 50 or 1,000. Let's start with simple. It doesn't have an impact on the space that's taken up because we only have these two variables and they exist no matter what. We're not adding new variables based off of the length. We're adding to the total variable, but we're not making a new variable. So that really just means we have constant space, O of 1 space. It's always the same no matter the size of the input. Here's another one. So this is called double. It takes an array, and well, why don't I just copy this one and show you? So I've copied it in, and it's called double. I'll pass in an array of 1, 2, 3. What does it return to me? An array with 2 items. What am I saying? An array with the 3 items, the same length, but each one has been doubled. And what's important to note, it is making a new array. So it starts with making that new array, then it loops over the length of the first array, and then it multiplies each item and pushes that on to new array. And then it returns new array. So what does that mean for the space complexity of this? As the array length grows, as the input approaches infinity, let's ignore the fact that JavaScript can't handle that, what happens to the space that this algorithm takes up in here? So yeah, we have this, where we're going to make a new array no matter what every time. But that's not that significant when we consider this right here. We have this new array, and it's getting longer and longer and longer directly in proportion to the length of the input. So if the array is 10 items here, we're storing 10 items in a new array. If this is 50 items, we're storing 50 items here in a new array and returning that. So the space that's taken up is directly proportionate to n, to the input array. So n numbers, we get O of n space. So we don't need to care about things like this. We can simplify it down just to the fuzziest level, which is O of n, rather than O of n plus 1 or something like that, or actually plus 2, because we also have this. Those don't matter. So I know it's a lot, and it's hard to understand right away, and it might not click. That's okay, though. We have some exercises, but I want to make it clear that you do not need to master this before we move on. I should just, the whole point is that I should have, in 10 sections from now, we'll have a couple solutions, and I want to be able to say, hey, the space complexity of this one is great, and the time complexity of this one is terrible. N squared time complexity, but constant space complexity or something. And you should hopefully be able to understand what I mean by that. Hey, welcome back. So I said at the very beginning of the course, we had a little math. The whole section's pretty mathy, but this last video in particular is condensed with some math. We're talking about logarithms, as you can see. Whether you learned about logarithms at one point, or you learned about logarithms at one point and forgot it all, or you never learned about it, I'm going to try and just make it pretty simple and also quick, because it doesn't actually matter that we're masters with logarithms. The reason I'm even showing it to you, I guess that's where I should start, is that some algorithms that we'll see have a big O that isn't simple. It isn't big O of 1 or of n squared. These are very common complexities, and we've seen them, and I think they're pretty easy to comprehend, hopefully. But there are some big O expressions that involve some more difficult math or less common expressions. And something that comes up more than I personally would like are logarithms. So that's why I'm showing it to you. We will have, and I'll show you in a bit, some algorithms in this course where their time complexity, instead of being O of n, might be O of log n. So let's start with what's log? What's a logarithm? So put simply, a logarithm is the inverse of exponentiation. So just like division and multiplication are a pair, logarithms and exponents, exponentiation, are a pair. So here's what you might see. You would read this as log base 2 of 8 equals 3. And what we're really asking or calculating here is 2 to what power equals 8? So if we take 2 and we raise it to some power, what power will give us 8? 2 times 2 times 2, it gives us 8, so the answer is 3. So 2 cubed equals 8. Here's just that same thing written down again. Log base 2 of a value equals the exponent. You can switch it around and say 2 to the exponent equals value. Just like if we had 1 divided by 2 equals 0.5, you could switch that around and say that 2 times 0.5 equals 1. We can move things around. They are the inverse, exponentiation and logarithms. Now, logarithms aren't always working with base 2. You could have log 3 of something. 3 to what power gives us 8, or log 5, or log 10. The most common ones, though, are the binary logarithm, which is log 2, so 2 to what power. Then there's also the base 10, so 10 to what power gives us some answer. Then there's also log e, which I'm not going to go into, but I probably shouldn't have said that anyway. There's a third very common algorithm. However, for what we're concerned about, we care about the big picture, and we're going to omit the 2. We're just going to say log, because first of all, it's annoying to write all this. Is this subscript? I think it's subscript, not superscript. It's annoying to format this, but also it doesn't really matter at the end of the day, because if we're comparing the graph of a constant time and a quadratic time and log n time, it doesn't really matter if it's log base 2, log base 3, log base 10. It's going to be the general trend that we care about. But just so that we're clear, this isn't actually a mathematical operation on its own. You can't just take the log of a number. You need to have a base. So we need to say log 2 or log 10. But in the slides and in literature, that sounds stupid, in literature, in things that you'll see online around big O notation, the shorthand is just log. If you want a rule of thumb, just to calculate it roughly. The binary logarithm of a number roughly measures the number of times you can divide that number by 2 before you get a value that's less than or equal to 1. So if we have 8, we're going to divide it by 2, and it's still greater than 1. So we're going to divide by 2 again. It's still greater than 1. Divide by 2 again. Now we hit 1. So that means 3. We divided 3 times, so the answer is 3. 25, however, it doesn't go cleanly. There's no way of dividing it by 2 evenly. So we divide by 2, and by 2 again, and again, and again, and then we're finally below 1. So this tells us that it's 1, 2, 3, 4, somewhere between 4 and 5. And the answer is 4.64. So the actual calculation is not that important. What matters here is if we take a look at it on a chart. So logarithmic time complexity is great. If you have an algorithm with log n time complexity, I'll show you which one it is here. Here we have constant time in red. And then right above that in orange, we have big O of log n. You can see that up front, it's a little steeper, but then it really tails off and is very gradual. And this is great. If you have an algorithm with log n time complexity, fantastic. So that's why I'm showing it to you, because it compares very favorably to things like O of n. There's another common one we'll see, n log n. I'm not going to go into examples just yet, but both of them involve logs, so I figured I should show you. It's not as good, but it's still better than something like n squared, the quadratic time complexity. So really the point at the end of this section, even if you're stuck on some of the math, what I hope we have is that later in the course, I'll show you two algorithms. I want to be able to point to one and say, this one has log n time complexity, this other one has O of n time complexity. And I hope that you can look at this chart and understand that, cool, the first one is better. It's at least more efficient, it's faster, because log n is much better than O of n. The larger n gets, it doesn't grow that much, the runtime, with log n, but it grows a lot in proportion with n for O of n. Okay, so that's why I'm introducing it here. We have a bigger picture of, these are the most common big O expressions. Like I said, the math, we don't have to worry about too much, but I just wanted you to know what a log is. Let's talk about where this will come up. So certain searching algorithms do have logarithmic time complexity, and we will see those as we go and progress through the course. Also, efficient sorting algorithms involve logs. So not all sorting algorithms, but some of the more efficient ones do. So we'll see that as well. And then finally, recursion, another topic. So basically there's three reasons here, none of which we've actually discussed. So this might not make a lot of sense. I'm basically saying in the future, we're going to see it at this place, and this place. Searching algorithms, efficient sorting, and recursion. And that has to do with space complexity with recursion, not time. So hopefully these will make more sense once we get there. Really, again, it comes down to just having this nice picture here. If I was teaching this in a classroom, I'd have this up on the wall at all times, like laminated, printed out, and I'd have a long stick, and I'd whack it on the wall and point it for every algorithm, point at one of those lines. And I'm going to try and kind of do the same virtual thing in this course online. Okay, so let's do a quick recap. We covered a lot. To analyze the performance of an algorithm, we use big O notation. It has to do with big, high-level, big picture trends. As the size of an input grows, we want to know how the runtime changes or how the space complexity changes. So big O can give us a high-level understanding of time or space complexity. It doesn't care about precision, just general trends. Time and space complexity as measured by big O depends only on the algorithm, not on the hardware. So yes, the actual time it might take to run one algorithm on my computer compared to some supercomputer will definitely be different. But the general trend won't be. Big O is basically measuring the number of operations that happen, whether an operation takes 10 milliseconds on my computer or 1 millisecond on another computer, which that's pretty slow anyway, but ignore that. And big O notation is everywhere, so we're going to get a lot of practice, and that's why it's coming first in this course. I feel kind of bad about it, like I've said before, because it's not the most welcoming topic, and it's kind of a rude awakening, but it gives us a context to discuss things. I'm going to go back to that terrible analogy of the Richter scale with earthquakes. It gives us a way of discussing how earthquakes compare their magnitudes. It's the same idea. We can compare algorithms now and say, oh, this one's great, this one's terrible, because its space complexity is X, or its time complexity is X. Anyway, let's call it a day here. Let's stop now, and we'll see you in the next section. Hey everyone, welcome back. This is going to be a really quick section. I just want to take what we just learned, talking about big O notation, time and space complexity, analyzing code performance, take that content and apply it to the stuff we already know. So before we get to the advanced algorithms and sorting and crazy data structures, let's just talk about what we get for free, the basics in JavaScript. So things like arrays and objects, built-in methods, loops. How do they perform? What are the easy things, the fast things we can do to an array? What's a method that might be slower than you would expect? That's what we're going to talk about. And it's going to be really quick. Again, I'm not going to teach these things from scratch. I'm not showing how an array works or what it is. We're just going to talk about how it performs. So first, our objectives. Understand how objects and arrays work through the lens of big O. So various operations. Is there a fast way to insert to an array? Is there a slow way? That sort of thing. Explain why, explain why adding elements to the beginning of an array is costly. Gave it away. And we'll talk about why that is and how it works, and if there are alternatives, if there's a better way of inserting. And then we'll compare and contrast the runtimes for arrays and objects, but also their built-in methods. There's a lot of these methods we get for free, like the built-in JavaScript sort for an array, for each, object.keys, object.hasOwnProperty, all that stuff we're going to discuss, but it's going to be quick. And this isn't, I should set out and say, this isn't something you need to memorize. It's not something that, you need to refer to these slides. I just want to give you a chance to take what we've learned about Big O and apply it to something tangible before we dive into these crazier algorithms. All right, so let's start. First, we're going to discuss objects. It'll be nice and quick, so don't go anywhere. I'll see you in the next video. All right, welcome back. So let's begin by talking about objects, talking about them through the lens of Big O and performance. Hopefully you're familiar with them. If not, I don't have time right now to teach them, but I may or may not have some courses on them. So they are unordered data structures, and everything is stored in key value pairs. For example, like this object literal, I'm storing in a variable called instructor. We've got 3 key value pairs. All right, so objects work well when you don't need order, of course, and also when you want fast access and insertion and removal. So no order, but everything else, almost everything else, is very quick. And when we say quick, I'm talking about constant time for insertion, removal, and accessing data. So objects are very fast. I mean, that's the fastest we can go, constant time. We'll come back to searching in a moment. If we hop over here, here's the same exact object. We later in the course have a section called hash maps where we actually learn a data structure that explains how objects work behind the scenes, how things are actually stored. So what happens when we say instructor should have first name set to Kelly? What does JavaScript actually do? A computer can't necessarily just access a place in memory called first name. So there's some additional steps involved along the way. There's something called hashing. We talk about it later in the course. But all that you need to know is that JavaScript is able to add something into an object, store a new piece of information in constant time. It's also able to retrieve something in constant time, and you could also update something in constant time, which is really the same as retrieving it. You're just changing it. Same with removal. So it's quick, it's fast for all the basic operations. There is no order, so there's no beginning of the object, there's no end. So it doesn't matter where you insert because there is no where. That's a bad way of putting it, but you can't insert at the beginning or in the middle or the end of the object. There's no repercussions. You just add in using a key. All right, so insertion, removal, and access are all constant time, very quick. If you want to learn more, remember there's a section on hash tables and hash maps where we go into that, and you'll hopefully understand how it is constant time. Searching, however, is O of n. It's linear time. And when we say searching, it doesn't mean looking for a key, for example, first name, because as we've already seen, accessing information with a key is constant time. What I'm talking about is checking to see if a given piece of information is in a value somewhere. If it's on this side of the colon, we have no easy way of doing that. We would potentially have to check every single item, every property. So that's what this little black box is signifying, or green box, I guess. If we wanted to know, is true stored in our object somewhere, we'd have to check. First name, what's your value? And then we look at it, it's Kelly. All right, that's not it. Is instructor, what's your value? True. All right, so there is true in here. But potentially, as the number of properties in there grows, as n grows, so does the amount of time it takes to do that. So now let's go on to some of the methods that objects come with. Things like keys, values, and entries. Those 3 are all O of n. So if we hop over back to Chrome and we take a look at keys, so it's object.keys, and then we pass in the object. So if we do it for instructor, we get this array with the keys. This is O of n time, because as the number of items in there grows, we're going to have to visit every single thing once and add it to this array. We're not going to, but the source is going to do that, the code. Same thing with values. Hopefully that makes sense. If we have 100 elements or 100 properties in our object, there's 100 things, 100 operations we need to do. There's usually more, but it runs roughly in line with n. It might be 2n, it might be 50n, but that still simplifies to O of n. And then that also is the same for entries, right? And technically entries is a little more work, potentially having to compile the key and the value, but it all just simplifies to O of n at the end of the day. Remember. Okay, so lastly, we've got has own property. And has own property is a little different. We pass in a property like first name, and it just tells us it has first name, or it doesn't have first name. And this is constant time. And hopefully that makes sense why it's constant time. If we're able to access information in constant time, if we have the key first name, we want the value. We should also be able to check if a key exists in pretty much the exact same time. So in summation, objects are really quick for pretty much everything. However, there's no order. And as we'll see coming up with arrays can be pretty fast for a lot of things, but the order also can slow them down depending on what we're doing. So objects are basic. They work very well in a lot of situations. Key value pairs, all the main operations, inserting, accessing, updating, removing, all constant time. Searching is pretty rare, but it is O of n. It grows as n grows. It's linear. And then the methods like keys and values and entries, where we're creating an array based off of the data inside the object. Well, as the object grows, so does the number of operations, the amount of time it takes to compile those. So those are O of n. Okay, so next, arrays. A little more interesting because there's some variation. There's some nuance to it. That's coming up. All right, welcome back. Let's talk about arrays through the lens of big O, performance, and how do they compare to objects. Quick side note, if you've never seen arrays or you're not familiar with them, definitely go learn about them first. I'm not teaching them here. We're just talking about them and how they perform. All right, so the big selling point of arrays, of course, is that they are ordered. There is an intrinsic ordering to the data, unlike an object where things just float around in a gelatinous mass. And that's often very useful if we need order, but it can come at a cost for some of the operations. Anyway, here are two different arrays. Of course, we can store whatever we want in there, different types of data, mix it up. And each element has an index, a numeric value that corresponds to it. So this is the 0th item, the first item, the second item. And in general, arrays, you use them when you need order. If you don't need order, then you probably don't want to use an array. If you're just trying to store random data together, you could still use an array, but if you're really trying to optimize for performance, there are other options. And even if you do need order, we're going to see some other structures coming up, like a singly linked list and a doubly linked list that still encode order. It's a list structure where each element is in a particular spot and they're all connected in an order, but they sometimes can perform better than arrays, depending on what you need. So arrays are not the only ordered data structure on Earth. They're just the only one that we get for free in JavaScript. Anyways, linked lists come later. So when you need an order, you can use an array, of course, but often that can come at a cost, depending on what you're trying to do, especially around insertion and removal. It can complicate things. So accessing data in an array is always very quick. So you can see here, access is O of 1, just the exact same as we talked about with an object. When I say access, what I mean is if we have this array with 3 items called names, if I ask for names of 0, or maybe that one's too easy because it's the first one. Let's say I ask for names of 2, it's constant time to give me Andrea. So a misconception that I've seen a lot of students have, when you have a 10,000 element array and you ask for the 9,000th element, let's say, JavaScript isn't going through every single element and counting all the way up to 9,000 and accessing every element and then getting to the one you need and giving it to you. You can think of there's a direct shortcut to each element. If you have a number, if you have an index and the array goes that far, of course, that's the one condition, it's a valid index, you can jump immediately to the data. So it doesn't matter how long the array is. It doesn't matter if you're looking at the last item, the middle item, or the first item. It's constant time. Okay, so now that that's out of the way, let's talk about insertion and removal. So it really depends on where we're inserting. Let's start with insertion. And it has to do with this order, as I've mentioned. Each element has an index that corresponds to it. And if I want to add something in, let's say I want to add in the name Raj. Well, if I add it to the very end, like right here, by pushing onto this array, that is constant time. It's O of 1. And that's because there's nothing difficult about that. We can add to the end of the array and we give it a new index. It's sort of like adding into an object. It's constant time. It's super simple. It doesn't require much work. The problem comes when we try and insert at the beginning of an array. And the reason for that has to do with these indices. If I tried to insert Raj here, you can already kind of see what happens. Our indices are totally messed up. Michael is no longer element 0. Melissa is not element 1. Andrea is not element 2. So we have to re-index every single element in the array. And this is simple for a 4-element array. But if we're talking about thousands and thousands of elements, re-indexing every single one is not a trivial task. So if we're inserting at the beginning of an array, we're talking about O of n time, because we have to do something once, roughly once, for every single element. Now that doesn't mean that it's exactly one operation for each element. Remember, O of n It could be O of 10n, O of 2n, O of 0.5n. It's just that the amount of time it takes roughly grows in proportion with the size of the array, n. All right, so inserting at the beginning is problematic. The same goes for removing from the beginning. So if we do have Raj at the beginning, let's say this is our setup now. Oh, this is so annoying, having to type all of this like this. If we remove Raj like this, everything's wrong, right? We have to reindex again, just the other direction. We need to set Michael, its index, or his index is 1, Melissa goes down, 0, Melissa goes to 1, Andrea goes to 2. So you can see how this becomes difficult. Adding and removing from the beginning of an array is best to avoid if you can. But often it's meaningful to add to the beginning of an array. If you're trying to put something at the beginning of an order, for example, you may need to, so I'm not saying you should avoid it at all costs. It's just good to be aware that it's not as efficient as adding and removing at the end. So push and pop, always faster than shift and unshift. Unless, of course, it's an empty array, in which case adding to the beginning or end is the same thing. All right, so we talked about insertion and removal. It depends on where we're inserting. Always inserting, removing from the beginning is worse than adding to the end and removing from the end. Accessing is fast, no matter where. If we're talking about 10,000 elements, accessing the middle element is just as fast as accessing the second element. And then searching, the fastest we can do is O of n. We'll discuss this in the searching section. We'll write our own basic JavaScript search. If we're talking about an unsorted array where there's no order to the data, if I wanted to know, if I had, let's say, another 10,000 names in here, and I wanted to know if Robbie was in there, we have to check potentially every single element. So as the number of items grows in that array, so does the time potentially that it takes to find that item. So search grows O of n, it's linear. And we spent a lot more time talking about search and potential optimizations you can make, specifically when your data is sorted, but that comes up later. All right, so next we'll talk about some built-in array methods and their performance, and then we're pretty much done. All right, welcome back. This will be really quick. I just want to touch on some of the built-in array methods. There are many of them, and I want to stress that you do not need to know or memorize any of this information, but hopefully it makes sense as to how we arrive at the numbers when we're talking about big O notation. So again, I have a little emoji. You don't need to know all of this, but let's take a look. The first four we've already discussed, maybe not by name, but push and pop are constant time, adding and removing data to the end of the array of any array, whether it's one item or 10,000 or a million items, is constant time. It's easy. There's no re-indexing involved. We just put it at the end and give it a spot. That's basically it. Shifting and unshift, on the other hand, are a little more troublesome because we potentially have to re-index, well, not potentially, we have to re-index every element in the array if you're adding to the beginning or removing from the beginning. So as the number of elements grows to 10,000 or a million, then the number of things we have to re-index grows in proportion with that. So it's O of n, it's linear time. So those four, adding and removing, we've discussed. I'm trying to highlight the top four. Well, no. Okay, well, that's the best I can do. So next up, we've got this little chunk of concat, slice, and splice. So all of these are O of n, linear time. And there can be some confusion. Something like concat takes multiple arrays and merges them together. And when we say O of n, you might think that that just implies, one array of n elements, and we're acting on that one array. What happens when there's two? Technically, you could argue that it should be, O of n plus m, where m would be the size of the second array. But O of n is fine. It's basically just expressing the fact that as these arrays grow that you're merging, so is the time that it's going to take. And it grows in proportion with the size, the total size of the new array at the end. What else did we have? Slice and splice. So slice is going to return a copy of part of an array, or the entire thing if you want it to. So O of n in this case refers to the fact that if we're trying to copy 10 elements versus 1,000 elements from an array, the amount of time it takes grows in proportion with that size, how large of a copy or how many elements we're trying to copy. So that's O of n. And then lastly, what we have? Splice. Where are you, splice? There you go. And splice is going to remove and add new elements. And splice is a little different because it's quite versatile. So we can insert at the beginning of an array. We could also insert at the very end of an array. We can replace given elements, but in general, it's O of n. If we're inserting in the middle of the array, we just simplify that to O of n remember that does mean shifting and re-indexing everything that comes after it. So even if it's only in the middle, we would still say it's O of n, even if it's O of n divided by 2. We just don't care about that. So in general, a lot of things working with arrays are O of n. You may have noticed this one down here, sort. Array.sort O of n log n. So we're not going to talk about how this is derived, where the log comes in, where the n comes in, why they're multiplied. We spend a lot of time talking about sorting algorithms, and there are many of them out there. We talk about 6 or 7. I think it's 7, but I'm not positive. We talk about a lot of them. And some of them we talk about have a time complexity of O n log n. So we'll explain how we get there. But just know that the time it takes to sort an array is larger than just O of n. We have to make comparisons. We have to move things around. It's not enough just to look at every element once, and that's not enough just to sort it. It's a little more, sometimes a lot more complicated. So just keep that in mind. Again, we're not explaining how we get this, what the math is just yet, but it will make sense in due time, I promise, if you make it to the sorting sections. So sort is the slowest thing on here. And then things like map, filter, reduce, for each are all O of n. Those are looping over each element or doing something with each element, tallying it, doing a Boolean test, or just printing them out, or whatever we're doing. It just involves acting on each element or with each element. So as the size of the array grows, so does the amount of time it takes, O of n. So you can see almost everything that we could do with an array, all the built-in methods, not all of them, but all the ones listed here are O of n. Sorting takes longer. And then push and pop are super fast, just like with basic accessing using an index, super fast as well, constant time, and they're much faster than adding and removing from the beginning, as we've talked about. Okay, so that's a lot. And remember, you do not need to know all of this. Really, the main takeaways here between objects and arrays: 1, objects are fast at pretty much everything, but there's no order. 2, arrays are great when you need an order, but still be mindful that it's better if you can do it to add and remove from the end and avoid adding and removing from the beginning, because that starts this cascade effect, hence the term shift and unshift, and everything has to be re-indexed. And the same goes to adding and removing from the middle. You start another cascade, a little tidal wave, and things have to be re-indexed after whatever you added or removed. All right, so hopefully that makes sense, how we get to these numbers, what the values mean. If not, we'll be spending a lot more time talking about big O as we go. And this is really a primer for later on when we get to things like sorting, or when we talk about linked lists and how they're also an ordered data structure, but we can add and remove from the beginning and there's no problem. It's constant time. So how does that work? So we'll get there. That's coming up. That's all I have to say about arrays and objects. We're done for now. Hey there, welcome back. So this section, as well as the next section, they're really one massive section, but I split it in half just so I don't end up with this one behemoth section. But both of them have to do with algorithms and problem-solving patterns or strategies, game plans, approaches, whatever you want to call it. Basically, you're faced with a tough challenge, some code or a problem you have to solve, and you don't know how to do it right off the bat. What are the steps you can take to make it solvable? And it really falls into 2 categories. This first section is more about the basic approach to solving a problem you don't know how to solve. Steps you can take, things you can do to make it easier. And then the second section that comes after this is about specific blueprints or archetypes, little strategies you can keep in your back pocket that help solve a lot of problems. So it's more code specific in the next section, but both are equally important. But first, objectives, really quickly. We're going to start by defining what an algorithm is in like 10 seconds. Devise a plan to solve algorithms, and then compare and contrast problem-solving patterns, including things like frequency counters, 2-pointer problems, and divide and conquer. So that's coming up in the next section. Like I said, this section is really more focused on devising a plan, sort of an approach to solving problems. And then afterwards, we'll dive into specific named patterns. Okay, quickly, what is an algorithm? Well, in today's world, it's like the trendiest of the trendy buzzwords. I was watching an ad the other day I was on Instagram, and there was an electric toothbrush, and they were advertising, this finely tuned algorithm for the vibrations in the toothbrush. It's a word that you can't escape. Really, it just means a process or set of steps to accomplish a certain task, a rather underwhelming definition. But that's all that it is. So when we say algorithm, I mean, we could be talking about, a set of mathematical steps that we need to do to solve a problem. We could be talking about Facebook's algorithm that, suggests certain ads to you, or Google's algorithm when you search for something, where it's a matter of, 50 developers working together. It's probably vastly underestimating it. Maybe 100 developers who are working on search result algorithms over, 10 plus years. So it really runs the gamut. But at its core, it's just a set of steps to accomplish a task. So that could be something simple like, calculate the first 100 prime numbers. There's many ways of doing that. Or it could be something like, Instagram's algorithm that used to just show you results in chronological order, and then they decided to change it, and now you miss a million posts about your friends. Anyway, why do you need to know this? Well, hopefully this is sort of clear already. Almost everything that you do in programming involves some sort of algorithm. Whether it's super basic things that you're doing or you're building a complex application, you have to make these decisions. You have to come up with a way of solving problems. So this stuff is super important. But I do want to sort of constrict our definition of algorithm for now. We're not going to learn how to solve Instagram's timeline algorithm. We're focusing on really a much narrower category, and that is things that come up in interviews. So this is probably why a lot of you are taking this course. Yes, this stuff is good to know. It, especially this section, applies to a lot of programming, pretty much everything, but it also really applies to interview settings. Being able to, sit in an office somewhere you've never been and answer tough questions or solve a problem you've never seen before. So just to reiterate, this stuff comes up all the time in interviews. Oh boy, how many of these did I do? Okay, interviews. There we go. So how do you get better at this stuff? A lot of people think this is just inherently, people are good or bad at it. And I've seen that a lot when I'm teaching. Some people are just naturally better at solving problems, I would say, or they're more their brain works right out of the box at solving problems. But that doesn't mean that it's hopeless for people who struggle. I've seen it many, many times in my classes during our interview weeks towards the end where we're doing computer science and sort of what this course is based off of. Some people pick it up much faster. Other people have to work towards it, just like anything in life, honestly. But I've seen many people turn it around and struggle during our first mock interview and have a panic attack basically in the middle of our conference room. And then a week or two later, brand new problem they've never seen before, equally as difficult, they're able to sit there calmly and solve it using some of the steps I lay out here. So how do you improve? There's two things. I've already mentioned this. First, devise a plan for solving problems. So this is more of a non-technical, it still is technical, but it's more about how do you approach a problem, strategies for breaking it down. There's a couple steps that I recommend. And then afterwards, master common problem-solving patterns. So a lot of algorithms, especially in interviews, a lot of these problems that come up can be broken into sort of different categories. And if you can identify some of those categories, there are some steps you can take in your code, some recipes you can keep that you can pull out and that will help you solve the algorithm or the challenge. We're starting off with this first one. Problem-solving strategies. So this section is focused on a simple, foolproof, magical, miraculous, fail-safe approach to solving every problem ever, which can be yours for only 2 payments of $999.99. Call now. No, not really. This is not at all what this section is about. This is just laying down a set of steps that can help you, but of course, it's not going to solve the problem for you. It's not foolproof. But I've seen many people, like I've already mentioned, turn their problem-solving approaches around. Many people who have gone from feeling really apprehensive about solving new problems and lock up in the middle of an interview setting, and giving them sort of a game plan, a set of steps that you can keep in your mind is a concrete thing to refer back to, step by step, what you should do. And I've seen it help a lot of people. So it's not miraculous, it's not magical or foolproof, but still is pretty helpful. So what are those steps? Well, first, understand the problem. So each of these bullet points will get its own video. Understand the problem, explore concrete examples, break it down, solve/simplify the problem, and then look back and refactor. So these are the different videos we're going to have in this section. Each of these points, there's a lot more behind it, and each one is part of this plan, this game plan, this recipe for solving a challenge or a problem. So that's where we're going here. And then the next section is on more concrete archetypes for algorithms. But we're starting here. All right, so problem solving. Hopefully you know why this is important. Don't make me go back to this slide. It's too many button presses. Interviews. Yeah, great stuff. Okay, let's get started in the next video. Welcome back. So as I mentioned in the last video, one of the biggest challenges for new developers, new programmers, has to do with solving problems. So I think for most people, it's easy enough to learn the syntax. It might take a little bit of time, but you learn the syntax and you're done. You can copy, other people's code or remake an application following step-by-step instructions. But the hardest thing has to do with solving new problems and new challenges. And you do get better with time, regardless of the technologies you use, the language that you're working in. It's really important to have a strong problem-solving skill set. And a lot of it will come naturally with time, but it's worth being deliberate. It's worth having a game plan to follow, step-by-step guide. It's not going to solve your problems for you, but it helps you sit and think about and break problems down, and it helps solutions come about more naturally. So I mentioned these 5 steps that we're going to talk about. This video is going to start with understand the problem. Before I go any further, I should mention that many of these strategies are adapted from a really good book on problem solving in general. It's sort of more slanted towards mathematics, but it's by this guy named George Polya. The book is called How to Solve It. It's a great resource, and it's where a lot of these tips come from. Okay, so we're starting with understanding the problem. So imagine you're sitting in a room. It could be a beautiful room, or it could be like a prison cell made of cinder block, and there's an interviewer ahead of you, and he or she asks you a question, and you don't know how to solve it. And it doesn't come to you right off the bat. It's not one of the practice problems you memorized over the weekend studying before. So the first couple of things I would do have to do with understanding the problem. And it can be tempting just to dive right in and start solving something, in particular when you're under some sort of time constraint, like in an interview. So most people just their heart starts racing, they just want to get started immediately. And this is true in programming in particular. You can make progress. Even if you don't get it right, you can just type a bunch of code pretty quickly and feel like you're making progress in a short amount of time. But before you start typing or whiteboarding or whatever you're doing, I think it's really important to take a step back and just make sure you understand the task ahead of you. And that sounds silly, it sounds trivial, but there are some very deliberate questions that you can ask, a thorough investigation of the problem or of the question, and it can really help clarify things. And sometimes will give you an aha moment, although not always. So here are some of the questions that I recommend you ask yourself, or if you're in an interview setting, ask the interviewer. But also if you're working on your own challenge, you're trying to build something out and you're not sure how to approach it, ask yourself these questions. So can you restate the problem in your own words? This is always the first thing I ask my students to do in an interview setting. You get a new question, just make sure you can restate it back, not word for word. Don't just copy what the interviewer said, but change it a bit in your own words to make sure that you actually understand what the question is. What are the inputs that go into the problem? So this is a really important one. What about the outputs? So what are the outputs that should come from the solution to the problem? What should the output look like? And we're going to dive into an example in just a moment. So what are the inputs? What will the inputs look like? What are the outputs? What should come from my solution? What should be returned from my function? Can the outputs be determined from the inputs? Meaning, do you have enough information to solve the problem? You have the inputs. Can you get the outputs that are expected just using that information? And sometimes you need to wait a bit until you can figure that one out. How should I label the important pieces of data that are part of the problem? So this would be, what are the things that really matter in this problem? What should you call them? What's the terminology that you should use? So it might seem like a lot, and it is, but if we walk through an actual example, we're going to do a really simple example, which is write a function which takes 2 numbers and returns their sum. So imagine that someone asks you this in an interview setting. Let's explore sort of understanding the problem through this lens. So let's walk through some of these steps. Write a function which takes 2 numbers and returns their sum. Can I restate the problem in my own words? All right, well, this one's nice and simple. We could just say something like write a function that adds 2 numbers or implement addition, something like that. Okay, easy enough. What are the inputs that go into the problem? Well, this might seem like an open and shut case, just add 2 numbers, so we need 2 numbers, right? But if you start to really think about it, it really depends. I mean, are we talking about integer numbers? Are we talking about floating points exclusively? It depends on the language that we're working in, of course. How large are these numbers going to be? Because in some languages, most that I've worked in, there's an upper bound for the size of numbers. And if you're trying to add really, really large numbers, it doesn't work well. For example, if we tried to do this here, it's a really large number plus, there you can see it's a plus sign, another really large number. Totally valid mathematical operation. But in JavaScript, what do we get? Infinity. It just gives up and gives us infinity. So in other languages, you might be able to represent this better as a string. Each one of these numbers, I mean. I won't actually do it for both, but and implement addition using the strings. So it actually really does matter, right? It's not a trivial question. It's silly to just add two numbers together. We already have addition. Why do that? But if we just think about it, we already start to figure out that there are some important distinctions between these inputs. And if we are trying to add these really, really large numbers, suddenly the problem becomes a lot harder because in JavaScript, we can't do that just with plain old numbers. Another thing is, are we only working with two inputs? Is it always two? What happens if someone leaves an input off? Or what if someone wants to add 4 or 10 numbers? Like, that's totally valid to add 10 numbers together mathematically. Is our function only going to work with two numbers? And the same applies to the third question, which is outputs. What should the output look like? This is simpler in this case. We still would have the question of, should it be an integer? Should it be a float? Depending on, if you pass in two floats, do we want a float back? If you pass in an integer and a float, are you even allowed to pass in a float? Or what about a string, returning a string if we're doing this massive addition? So it's sort of the same question. Well, it's not the same question, but it's a lot of the same issues. Next up, can the outputs be determined from the inputs? Basically, do we have enough information to do the problem? And in most cases, the answer would be yes. But if you think about it, what happens if someone only passes one number in, as we already discussed? We don't have enough information to do addition at that point. So do we add 0? Do we return like undefined or null or something? What do we do? And that depends. You ask your interviewer that, or in most interview settings, they might just tell you to ignore that for now. But also in most interview settings, they probably wouldn't ask you to write a function that takes two numbers and returns their sum. And lastly, how should I label the important pieces of data that are part of the problem? So I like to put this in here because it's important to start thinking about this. What matters? So we have the inputs and we have the outputs, and that's pretty much all we need. So maybe, we'll name our function add, and then we'll have num1 and num2 as the arguments, and then sum is our result that we return. So this is simple, but once you start getting into more complicated problems, thinking about this step by step really can make a difference. And I'll show you some examples where it helps. But first, let's move on from understanding the problem to exploring concrete examples. So this was only the first step, but there were still multiple questions that we can ask ourselves or ask our interviewer about the problem. All right, next up, exploring examples. Hey, welcome back. This is part 2 of the simple 5-step program to changing your life and realizing your dreams, as long as your dreams have to do with solving problems. That doesn't include family problems, medical problems, personal problems, problems with your pets, peeing on your brand new furniture. It only applies to code programming challenges, unfortunately. And I've been viewing this through the lens of interviews, but it really does apply to any sort of code challenge that you're trying to solve on your own. Okay, so step 1 was understand the problem. Step 2, after you've done that, explore concrete examples. So we're back in our cinder block cell. Our interviewer has asked us a question. We have a moment of panic. We start by understanding the question, trying to figure out and make sure we understand the inputs, the outputs, all that stuff we talked about. The very next thing that I do, and I recommend all my students do when we talk about interview prep, is come up with concrete examples. This is tied very closely to understanding the problem. So coming up with examples can help you, can help you understand the problem better. Examples also provide sanity checks so that your eventual solution, once you have a solution, you can tell if it works how it should, because you'll know at that point, you already have the examples. You know the inputs and the outputs that you should get. So if you have those examples, you can check your work. But also you can learn more information by doing these examples. And this applies on a larger scale. Things like user stories. These are examples. If you're not familiar with user stories, it doesn't matter that much, but if you're working on a product, like at Instagram, when they're solving a challenge, they're building a new feature, you bet that they start with user stories at some point they do, which is basically Given an input, what is our output? Except the input is, a user action. What should happen after that? Or unit tests on a smaller scale, but still, bigger context than an interview. Unit tests are used all the time to help lay out, how something should work for a smaller feature. Okay, so here are the steps that I take around exploring concrete examples. So you're faced with a problem. The first thing that I do is start with simple examples. And I literally, if I'm in an interview or if my students are in a mock interview, I tell them, all right, you restated the problem already, you understand it. Now write down 2 or 3 simple examples with an input and then the output. And I really actually like to write this down so I have it and I can look back at it. So simple examples, the ones that should make the easiest use cases. Then progress to more complex examples. And then what about edge cases? Explore examples with empty inputs. That will often give you some insight into how the problem should work, especially in an interview setting. Explore examples with invalid inputs. So this is more useful, I'd say, in the real world. What happens if a user enters something that is invalid, right? We have to think about this all the time. So let's explore this with a concrete problem. So our interviewer asks, write a function which takes in a string and returns counts of each character in the string. So relatively straightforward problem, but there are many questions, many examples that we could try out and use to learn about the problem. Okay, so someone just asked me to solve this problem. I'm in an interview. I want to check that I understand it first, so I try and restate the problem, do all the stuff from the last video. Then I like to come up with a couple simple examples to make sure I understand it. So let's say our function is called char count. I would literally write this out. So char count of like A with 4 A's. Well, that should return something that looks like this, I would assume. Returns counts of each character in the string. This is, we've already gathered that it needs to return an object, let's say, instead of an array or some other data structure. So I would try this, and that's how it should work, I guess. Char count of hello should return something like this. But already there's a question that I have, which is, should it just return the letters that are in there? What about the letters that aren't there? Do we want to include, B0 and C0? Because if we did that, it might make our code a lot easier. If every letter was already in there set to 0, then it makes it simpler as we go. We don't have to add in A or B if it's already in there. We just have to increment it. So that's a question that I would try and clarify. So the next step was progress to more complex examples. So what about something like this? If somebody did something like my phone number is blah, 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 and that's not a valid phone number as far as I know. So if this was an input, what would we expect to return? Do we want to account for spaces? That's an important one. What about other characters, $signs, underscores, numbers? That's a big one. Are we going to put numbers in there? And an even more important one that definitely would come up, what about this? Hello, hi. Are there, do we store an uppercase H and a lowercase h? Do we ignore casing? How should this work? Should our object have H uppercase 1, H lowercase 1, or just H2? So these are more complex inputs and examples that it would really help to understand, and it would help us to simplify the problem or understand it better by asking these sort of questions. These examples are really just another form of understanding the problem better before we tackle it. So it ties into the previous video a lot, understanding the question. Next up, explore examples with empty inputs. So what if, somebody does char count and doesn't pass anything in, like this, or an empty string? What do we want to return? Do we want to return an empty object at the end? Do we want to return null or false or undefined, or maybe an error? And that's tied to exploring examples with invalid inputs. So what if somebody passes in something that isn't a string? They pass in a number, or they pass in an object, or they pass in null. There's all sorts of these edge cases. And understanding these edge cases in an interview setting, often it's not that important usually, but it can be really important in the real world to help you build a more robust solution, something that is more foolproof. So it's still important to keep that in mind. And sometimes it can give you a bit of insight into how the problem works or how you should solve it. Welcome back. So let's move on to part 3, step 3 of solving a problem, or at least trying to. So we understand the problem, we explored concrete examples. Now, before we start typing code, I like to break it down. And I actually like to do It sounds like, yeah, I don't start dancing in the middle of the interview. By break it down, I mean take the actual steps of the problem and write them down. It doesn't have to be full pseudocode. It doesn't have to be valid, syntax. I like to do just little comments as a guide for the steps I need to take. And especially in an interview setting, this is really important. What a lot of interviewers are looking for is, you to communicate what you're doing. You don't want to just like start typing right away or start writing code on a whiteboard silently with your brow furrowed, angrily writing code. It's much better to say, all right, here's the steps I'm going to try and take. Sometimes you can get a little hint too. You can throw in, do you think that'll work? Or, does that sound crazy to you? Or could this be the right way of doing it? And sometimes they'll give you a little hint. So breaking it down can be really important. So I recommend explicitly writing out the steps that you need to take. It doesn't have to be a ton of detail. It doesn't have to be line by line, every line you need to write. Just the basic components of the solution. So this forces you to think about your code before you actually write it, so that you're not just freewheeling and trying to come up with it on the fly. And it also helps you kind of catch or figure out any lingering questions or parts that you're scared of or that you don't understand. So that's why I really recommend doing this. It helps you just lay out your steps, and that's always nice, and it helps you stay focused. But also it helps you highlight the problems you might still not be confident about. And then you can just dive in and start writing the code. So let me show you what it looks like if I were to break down this same problem. Write a function which takes in a string and returns counts of each character in the string. So the same problem from before. All right, so I have a sheet of paper or a whiteboard or whatever it is in my interview. I've written down some examples, and now I'm going to type up the skeleton of my function. So we'll call it char count, and we know that it accepts a string. It's called str. And then I'm going to stop with the actual code, and I'm going to start writing some comments. I'm going to break it down for myself. And the simplest thing we could start with is just do something, and then add in our return value. Return an object with keys that are lowercase alphanumeric characters in the string. So just to clarify, I've decided, or my interviewer decided, that we only need to care about alphanumeric characters, lowercase as well. So that means, in this example, your PIN number is 1234. We are keeping track of the numbers, and we are keeping track of all letters, but only lowercasing them. So PIN, PIN, we're going to keep that, a one lowercase p, two lowercase i's, this one here, and this one here. Okay, so we could start with something simple like this, put our return value down there. I'm going to duplicate this and expand upon it. So if we think about the actual steps of what we want to do, well, we're going to need to do something once for every character in the string, right? We're going to need to go over it. At some point, we also need to make an object that we're going to return at the very end, right? That one's simple. We need to make the thing that we're going to return. We need to return it at the end. But the bulk of the logic involves looping over every character in our string and doing something. So I might start, let's get rid of this and simplify this a bit. I would start with something like make object to return at end. Then after that, I would do, loop over string, and we'll come back and fill in the detail, and then return object at end. So now we have the very basic steps, and we can fill in the blanks, but looping over string is definitely the bulk of our logic. So what do we need to do? Well, if we loop over the string, we know that we're going to need to look at each character, and let's start with y. We're going to need to look at y and lowercase it. So we could lowercase the entire string at the beginning. That's one option. Or we could lowercase each character as we go. But we're going to start by taking a look at this character. And what do? We check, well, are there any in our object already? And technically it's going to start out empty, so there's nothing in there. So then we would add y in and set its count to 1. But if there already was a y in that object, then we would add 1 to it. So that's really the logic. We're going to loop over string for each character. Then we'll do something like if I'll just do char, is in our object, let's say is a key in object, add 1 to count. If the character is not in our object, add it and set value to 1. So that makes sense. Although this isn't accounting for the fact that we only care about alphanumeric characters. So the spaces we're not going to add in. The exclamation point we won't add in. So we should clarify that. We should say if the character is a number / letter and is a key in our object, add one to count. If the character is a number / letter and not in our object, add it to the object and set value to 1. And then otherwise, we'll say like if character is something else, a space, a period, etc., don't do anything. And then at the very end, we return our object. So we make our object at the beginning, then we go character by character. We have our main logic. It will just be a loop, probably a for loop. And then we'll take each character, look at it, make sure, check, is it alphanumeric? Is it a number or a letter? If it is, then we will add it into our object. And that means either incrementing an existing part of our object or adding it to the object and setting its value to 1. And if it's not alphanumeric, we just don't do anything. So we build up our object one character at a time, and then we return it at the very end. And now that we have these basic steps, we can now go fill in the blanks. And I highly recommend, this is a simpler problem. Some of you probably could have, a lot of you probably could solve this without having to do any of this, pseudocode. And this isn't even full pseudocode, but just writing these comments out. But for more complicated problems, it really can be a lifesaver. Because if you write out the steps, especially in an interview, you write out the steps, you know what you need to do, even if you're not sure how to accomplish it. It demonstrates to your interviewer that you at least have formulated an approach. And if you run out of time and you only get halfway there, but you have the layout for what you would have done. So like if we stopped here, for example, this is a short problem, but let's say this is where we ran out of time. Everything is implemented in code. If we have these notes down here, our interviewer could see that we knew where we were going, or we had a general idea. And that can often make the difference in demonstrating that you are competent, even if you don't finish the problem. I've seen many people get jobs who didn't, they thought that they failed the interview because they didn't finish the problem. They didn't have the right return value at the end. But often these problems are made to be so difficult or so time consuming that you're not supposed to finish. And it's really about seeing your process. So that's what all this is about, the process. Welcome back. So we've talked about the first 3 components, the first 3 steps in this 5-step problem-solving approach. Understand the problem, then go through some concrete examples. Talk about edge cases, inputs, outputs, that sort of thing. Next, break down your approach, your solution into a couple of steps that you can follow. It doesn't have to be insanely detailed, but it does help if you can come up with pretty thorough steps. And then sometimes, if all of that went well and you feel good about it, you can just solve and you write your code right away. And I should note that's not the last step. Even if you do solve it, there's still a step after this. But sometimes you're not ready to solve the entire problem at this point. You might feel good about 80%, but then there's this one thing you're not sure how to do. Or there's, 2 things that are really challenging. So that's where simplify comes in. Solve or simplify, or solve/simplify. Okay, designated slide. So solve the problem if you can. And if you can't, solve a simpler problem. Now, that doesn't mean changing the subject entirely and picking, let's solve 1 + 1. That's stupid. I don't know why I said that. What it really means is trying to ignore the part that is giving you a really hard time in order to focus on everything else. So why is it even worth doing this? Well, first of all, in an interview setting, often you want to have something to show for yourself. So instead of getting stuck on one difficult part of a problem and making 0 progress at all because you're putting all of your eggs in one basket of being able to solve it 100% before you even start writing code, that often can look bad. It's much better, even if you know there's some part that you're going to get stuck on, it's much better to just start writing code to do the stuff you know how to do, all the while keeping in mind that you do need to incorporate that harder part back in. Secondly, it's pretty common that in simplifying a problem, you'll gain insight into the actual solution, into the harder part of the problem, and something will click into place. So I really, really recommend that if you do get stuck on something, but you know where to start, or you know a place to start, you should just go for it. Once, of course, you've done the first 3 steps. You've understood the problem, you've done concrete examples, and you've broken it down into steps. So as far as the simplification, I like to think about it this way. So you find the core difficulty in what you're trying to do, the thing that is tripping you up, that you're panicking about. Temporarily ignore that difficulty, write a simplified solution, and then incorporate that difficulty back in if you can. And along the way, often at this step, you'll gain insight into how this part works. So one more time, let's return to this example. Write a function which takes in a string and returns counts of each character in the string. All right, so char count, remember, should return an object that contains all the account for every alphanumeric character in an input string. So ignoring every non-letter or number, and all the letters should be lowercase. So there's a couple things that could present difficulties here. To start off with the really simple, obvious ones, if someone has trouble with looping, then this could be problematic. And if you did have trouble with looping, then I would, if it were me and I struggled with looping, I would start by creating an object and just working with the first character in that string, or hard coding in the first 5 characters. Probably, not going to get me a job, but at least it's a start. And then once you figure out, how to handle it for one character, the very first item in a string, like right here, you lowercase it, or you add it to the object, or you check if it's in the object, and then you do it for the second character, then the third character. Then you find a pattern that you can turn into a loop. Another thing that could be problematic is someone might not be comfortable working with keys and values in objects. Again, a very simple problem, and you're probably not going to be interviewing for a job if you have trouble doing that. But if you were trying to solve a problem anyway, maybe you're at home and you don't feel good about using keys and values and manipulating objects, you could start with a loop and loop over every character in the string and maybe just print out that character. Or probably a more realistic thing is that you may not be comfortable working with uppercase and lowercase strings. Or if you're in an interview setting, you might not remember. Sometimes, you don't have access to a computer if you're on a whiteboard. You might not remember the exact method that lowercases or uppercases a string in JavaScript. So I would just ignore that. I would just start with the main logic and then, put uppercase and lowercase characters in there and just deal with it later. And just say out loud, like, I can't remember exactly how to do this, so I'm just going to skip that part. And then at the end, I'll go back. Or if I had my computer, I would just quickly Google how to lowercase something in JavaScript, and I'd lowercase everything at the beginning. Something like that. Now, if I did actually face this in an interview, which, to be fair, it's a pretty easy problem, at least on the surface, the thing that would probably trip me up the most and trip up most students that I've worked with is making sure a character is alphanumeric. Making this object to return at the end, simple enough. We could just call it like frequency or count result maybe. It's an empty object. Loop over the string for each character. So I'll just do for var I equals 0. I is less than string.length. All right, then this gives me each character. And we could start off by just adding each character into that object or checking if it's in that object. So ignore the number letter part, ignore alphanumeric, ignore the casing even, and just check if that exact character is in the object. So I would just do something like if result of, let's make a variable here to make this a little more legible. So let's make a variable called char equals string of I, instead of having to put string of I all over the place. So if result of char is greater than 0, meaning it's already in there, then I'm going to just copy this and do ++. Else, we're going to set result of char equal to 1, because that means it's not in there yet. And this is basically where I would start, assuming I don't have a typo. So if we put my pseudocode, let's move this here. If the character, we haven't conquered this number letter problem, but we're at least getting 90% of the way there. Just put my little bits of pseudocode here. And we're not tackling this. Return the object at the end. So then return result. And let's see if it works. Okay, I ran my solution. And if I run char count, is this large enough? Char count of hello. Let's make this a bit larger. It works. You can see that we get H1, E1, L2, O1. If I instead do hi there, like this, you can see we're also getting uppercase H. We're getting What else? Exclamation point. We're getting space. So that's not ideal, but we're really close. So now, if we have this done, we could at least figure out the lowercase part, or, maybe our interviewer gives us a hint, or we have access to figure out how to do the lowercase. It's just a method to lowercase, or we could uppercase everything. But it's a matter of if we want to lowercase the entire string first, or we could do it, one character at a time. So we could come in here and just do 2 lowercase like that, rerun our code, and now if we look at char count of hi there, it all works. We have 2 H, E's 2, casing doesn't matter. Now we still have the non-alphanumeric characters, but this gets us most of the way there. And now we could do some additional research. We could ask our interviewer if they had suggestions. We could just start spitballing on how to do that alphanumeric component. So to tell if a number or if a character is alphanumeric, there's a couple options. We could define, an array essentially containing every valid character, which would be really annoying. So we could have an array that was massive that had A, B, C, D, uppercase and lowercase, and every alphanumeric character, which I guess is not that many, but still, it would be a long array. We could use a regular expression, which is probably what I would do, and I'll show you a solution with that in the next video. You could also probably do something with the character codes, the ASCII codes. There's a lot of different ways you could do it. And all that we would need to do is plug it in to our existing code. So if we were checking if it was a valid character, I would maybe just add an additional if statement and nest these inside of that if statement. So all of this logic stays. We wouldn't be deleting anything. We're just adding in that one little component. So to wrap this up, this isn't a particularly challenging question in all honesty, but there's still a lot of different approaches that we could take, a lot of different ways of solving it. And like I said, the next solution I'll show you in the next video, as well as a couple refactored versions, vary quite a bit. But at the end of the day, we write what we can, right? We loop, we add things into the object, we have a couple conditionals. Even if it's not perfect, we're still 90-something% of the way there. We just need a way to check if something is alphanumeric. And in an interview, if you can get 90% of the way there, and you just have this one little thing that you need to complete, you tell the interviewer, there's 3 different ways, I'm not sure which one's best, or I'm not sure how to do this. Do you have any suggestions on what I could do to check if something is alphanumeric? That sort of line of questioning, if you get 90% of the way there, it demonstrates a lot about your problem-solving ability, rather than just fixating on that before you even begin. So it's much better to write something, not just like rashly put stuff on the page and hope it works, but get the right pieces in place so that once you figure out the hard part, you can just plug it in. All right, welcome back. We've made it to the final step out of 5, and this is probably the most important step when it comes to improving, becoming a better developer. So we've understood the problem, we've talked about concrete examples, broke it down into steps, we solved it or simplified it to help us solve it. And then once we have something, whether it's an amazing solution or super scrappy, it's time to look back and refactor. I know it's tempting that once you have something workable, something good enough that does what it needs to do, it's tempting to just, shut your laptop or close the book and go, play video games or do something else. It's really tempting because often you can get by with something that just works. And in a lot of jobs and a lot of scenarios, all that matters is that something works. It doesn't have to be beautiful. It doesn't have to be the most efficient code on earth. But it's really, really important to strive for those goals. Obviously, if you're a one-man team or a one-woman team and you're creating a company on your own and you have a deadline of tomorrow and you have to just write code that works, then yeah, it's fine to be scrappy. But it's really important to try and improve your code. And it's a missed opportunity if you don't take the time to look at your code, look back and reflect on it. And I don't just mean, longingly in a poetic way. I mean, look at the individual components line by line. Talk about the parts you don't like, or what do you not like about how the code itself looks, how it reads, how easy it is to understand. Obviously, what most people care about is efficiency when they're looking at code, but there's often a balance that needs to be struck too between those two polars of efficiency and legibility. And in an interview setting, it's really important to ask these questions often out loud. You have a finished solution, You can be proud of that. Something works. I like to then take a moment and sort of go line by line and think, oh, this is not ideal. I think maybe there's a better way of doing this, but I'm not confident. I would Google if there was a faster way of doing this, that sort of thing. So I'm going to go through that, but here's sort of a checklist of questions you could ask yourself. Can you check the result? So that one's obvious. We need to make sure our code works. Can you derive the result differently? So this is referring to the fact that there's rarely one solution and only one solution to a problem. So can you think about different approaches? Now that you've solved it one way, is there another way that seems viable that you couldn't think of earlier? Can you see it at a glance or understand it at a glance? So how intuitive is your solution? Does it make sense when you look at it on paper, on a whiteboard, in your code editor? Can you use the result or method for some other problem? One of the great benefits of solving a problem is that it helps you sort of develop a spider sense, an intuition for solving other problems. So whenever you write down a solution, it's worth pausing and asking yourself if there's any similarities between this solution or this problem and others you've encountered in the past. So maybe not in an interview setting necessarily, but this has happened to me a couple times. I solve some problem and it sort of unlocks the solution to another problem on a different project or a different company or something like that. So it's something to keep in mind. Okay, next up, can you improve the performance of your solution? So this is one that, like I said, is probably at the top of a lot of people's minds when they write a solution. So how can we make it perform better? Mainly, time complexity and space complexity. And that's something we talk a lot about in this course. So if you're not super comfortable measuring that or calculating it, that's okay. But we can still identify certain things that might be poorly performing or slow. For example, like a bunch of loops that are nested. Try and avoid that. Can you think of any other ways to refactor your code? If you're working for a company, does your code follow company guidelines, a style guide? Does it follow conventions of the language? Is the spacing consistent? Just minor things, but this is important to show, even in an interview setting, at least acknowledge the fact that your code isn't neat and that you would prefer to make it neater if you didn't have time. And lastly, how have other people solved this problem? So in an interview setting, often, the interviewers ask the same question to many different candidates. Some companies I've seen have used the same question for like years. And so they've probably seen a lot of candidates and a lot of solutions. So in an interview, it can be really beneficial after you have something, whether it works or doesn't work, at the end to pick their brain. Say, what other approaches are there? What did I miss? How have you seen people solve this? And sometimes people like to share the most effective or simplest solution. Other times, people like to talk about the craziest, most eccentric solution, the most unexpected way of solving it, even if it's not the most efficient. But you can learn a lot from looking at how other people have solved the same problem. Now, if you're on your own, you're working on a project, an application, and you're solving a problem, often you're solving something that other people haven't solved before. Otherwise, you may not be prioritizing solving it yourself, right? If you need to, you're not going to build your own database from scratch. You can use someone else's database. But sometimes there are certain things that you do implement on your own, and it's worth looking at other implementations. Whether it's in a different language, this happens pretty frequently to me. If I'm writing something, you may not find it in JavaScript. You can search around and you might find someone else's code in Java or in Python. And you can take that and compare it to yours, depending on how comfortable you are doing that. And it can be really useful, and you can find ideas and different approaches. Anyway, so these are a lot of questions here that you can ask yourself. But my point is that refactoring is really important. And it doesn't even have to be refactoring, which is why I called it look back and refactor. Because sometimes you could be happy with your code or you might not want to make changes, but it's worth thinking about it. It's worth analyzing your code and reflecting on it, looking back on it, rather than simply writing something that works and calling it a day. So let's go through a simplified version of that process with my solution here. So I changed my solution a bit. Here it is, by the way. Everything's the same as what we saw in the last video. I added in a simple regular expression to test if a character is alphanumeric. So if it's a lowercase a through z or a 0 through 9. And this is how I'm weeding out all the non-alphanumeric characters, spaces, underscores, dashes, periods, commas, and only doing the letters and numbers. And I lowercase it first, and then I test each character. So if we make it to this point, it's the character is either a number or a letter. And then we just check, like we did in the last video. If the character is already in that object, meaning it's greater than 0, it's set to 1 or 2 or 3, for example, just add 1 to the value. Otherwise, initialize it to 1. I'm not sure where that extra 1 came from. And then we return the object at the end. So this works. And if I finish this at the end of an interview, this was my solution. The main pain points, the things that I would point out, there's a couple. One easy fix is I'm not really a fan of using a for loop. Obviously, for loops are great and they've been around forever. But in today's landscape, I would probably use a for of loop just to simplify this so we don't have to work with I. Because if we do for of on a string, it gives us each character immediately. There's no reason to go, this is an extra step. Loop through a range of numbers, then take that number to get an individual character. When I could replace it, so I'll refactor this, just keep this here, but slowly refactor it down here. And this isn't really a performance thing. It's just aesthetics, I guess. So for, I'd say var char of that string. Then we don't need to define char again. We're going to lowercase it. So let's do this. Char.toLowercase. So we no longer have to do string of I. We're just working with char. And this should work still. Let's just verify that. So I paste it in. Let's do it on hello, hi, and throw in some punctuation. And it looks like it's working. We have 2 H's, lowercased. Okay, that's all good. Now a small syntax change that we could make. This isn't a huge deal, but this kind of bothers me when I look at it. It takes up a lot of space to do a very simple thing. We're either adding 1 to a number or setting a number to 1 or initializing a value in a key. Oh my gosh, in an object, or initializing the value to 0. So we're initializing it to 0 or adding 1 to it, which is a pretty simple thing. And it's a simple if else. So often I look to combine these into a single line if possible. And it can be difficult if you're in a stressful interview situation. Often I just write this first thing that comes to mind, the simplest, most basic syntax, and then come back and clean it up. So we can replace this here with this line. So what this does is it takes a character like A, accesses the corresponding value in our object. So if it's truthy, we're going to add 1 to it, meaning if there's a value in there already. If there's nothing in there, we're going to set it to 1. So we basically have 2 scenarios. Object char equals this, object char plus 1, or if it's falsy, set it equal to 1. So this is a nice way of cleaning up our code, shortening it quite a bit. And just to verify that it still works, one more time, paste it in correctly, and it looks like it's working. So the last thing, and this is probably the most important thing that I would think about here, we did a couple stylistic changes. We could use some more ES 2015 syntax, replace var with let and const, and that's probably a good idea to do. But the most pressing thing in my mind that I'm unsure about, if this was in an interview setting, I would say, okay, well, I'm using a regular expression here because I know how to do that, and it's a quick way, a relatively short way of checking for a certain pattern, in our case, to see if a character is alphanumeric, a letter or a number. But I'm not sure how efficient it actually is. And I would say that. I'd say, I've heard certain things that in JavaScript, and this is true, in JavaScript, regular expressions, the performance can vary depending on what you're doing and depending on the browser that you're in. In particular, Chrome had some issues with regular expressions a while back. So I don't try and avoid them because they can be very useful. But for something like this is a very simple usage of a regular expression. Often people will use them to find patterns like credit card patterns or phone numbers or addresses or much more complicated things like matching a URL pattern, which would be a huge pain otherwise. But just checking if something is a letter or a number, I think there could be a better way to do this. So I would say that out loud, and this might not come to mind right away. It didn't come to my mind right away either. But what you can do, and I just did some research to figure this out, is use char at or character at. So if we, take a string like hi, and then do char code at rather than char code at, and give it an index, it gives us a number, 104, which is the character code for h, for lowercase h. If we did, let's just do I, it's 105. Hij comes next in the alphabet, it's 106. So these are in a range of numbers. And so what we could do is replace our regular expression with using a simple mathematical comparison. So we would do a character or char code at, and give it, let's just say always 0 for now. And then we would check if it's a valid character code. And I found someone doing this online, which is what sort of inspired me to look at this. This person wrote a little bit of a performance test where they're testing if something is alphanumeric down here using a regular expression. And here they're testing if something is alphanumeric using a character code. So you can see between 47 and 58 are the numeric character codes. Between 64 and 91 are uppercase alphas, I guess, the alphabet. And lowercase letters are 96 to 123. So we can just quickly, a couple Boolean comparisons, which are very, very easy and fast to do in any programming language. They're pretty much one of the simplest, if the simplest operation you could do, are these simple Boolean comparisons. And this person demonstrates actually that if you repeat this over and over and over again, you can see that the non-regular expression version is indeed faster, 55% slower using regular expressions. So I'm showing this to you not to say, I would have come up with this in an interview, because I probably wouldn't have. I might have considered it, but I certainly wouldn't know the character codes. I would have just gone with what I felt most comfortable doing. But then I would, at the very end, add a little note in to my interviewer saying, hey, maybe there's a better way. I would Google it. I have a feeling regular expressions might not be the fastest way. So what I did is actually turn this into a function called isAlphanumeric, but it works in a single character. So you pass in a character one at a time, and then we get the character code at index 0 because it's a one character string. Technically, you can actually leave this blank and it still works, but I like to be explicit, so I'll put the 0 in there. It gives us the first character, which is the only character. So if we're passing in hello like this, I would call isAlphanumeric on H, call it on E, on L, and it should return true every time. And then if we have a space or an exclamation point, it will return false. So I've created this function. Now what I'm going to do is get rid of this regular expression and refactor it to be if is alphanumeric of character, just like that. Another thing to consider is the placement of when we do the lowercasing. Is it better to lowercase everything at the beginning, the entire string, and then check each character to see if it's alphanumeric? Is it better to first check for alphanumeric characters so that we weed out all the spaces, the punctuation, everything that's not valid, and then lowercase afterwards? And I'm actually not positive on how I feel about it. I've gone back and forth. It depends on what your strings look like, what the inputs look like. If they are generally all alphanumeric versus if you have really weird strings that have a ton of random characters that aren't alphanumeric, I think that the answer would depend on that. But what I'm going to do is just run it like this. So if is alphanumeric, then we'll lowercase it and then add it into our object. So I like this solution. One, I like having this separate function so that this is pretty readable in my opinion, like for each character of our string. Like that's very nice and legible. For a character in the string, if that character is alphanumeric, we're going to lowercase it and then add it into our object or initialize it to 1 or add 1 to the current value. So I like this solution. I think it's clean and readable, but also, allegedly at least, according to some stuff we found online, is more efficient to use character codes compared to a regular expression like we had up here. So I know this is getting a bit long, but I just wanted to show you my process. This is the solution I wrote first, and then I've kind of just thought about it more and did some more research. And this is the solution I prefer, not just stylistically, not just because it's shorter. It's actually not shorter because of this code here. Of course, you could put all of this code right in here and not have a separate function, but I think it reads so much better like this. All right, so let's make sure it works. Char count of, sure, this one again. Hello world, hi. So there should be 2 H's. There's 1 E, what else? 3 L's, and we're ignoring case, and also we're ignoring non-alphanumeric characters. All right, so that was a lot there. Hopefully you agree. Maybe you don't. have some feedback on my refactor. But just in asking myself those questions about how did other people do this? How could I improve this? Where are the stylistic changes I could make? Our solution looks vastly different than it did before. Not that there's anything wrong with this one out of the box. Okay. All right, welcome back. This will be a 30-second video. I just wanted to summarize the steps. So to recap, sort of the 5-step protocol here, whether you're faced with a tough interview challenge and you're at a whiteboard and there's a bunch of people watching you, or you're trying to solve something on your own for a novel, challenge you faced, an app you're trying to build, trying to figure out how to sort search results, whatever it is, these are the steps that I like to go through. Make sure you understand the problem. And a lot of this, the way I taught it or talked about it was geared towards interviews, like I said, especially things like understanding the problem. So ask questions of your interviewer, of course. Clarify the problem. Make sure you understand it. But even if it's just you working on something, make sure you understand it too. Make sure that you really have thought out how your solution, how your application it should operate, how it should behave in every scenario. And that goes hand in hand with exploring concrete examples. These two are really both about understanding the problem, understanding the inputs, understanding the outputs, understanding edge cases. How do you handle errors? What happens when a user enters something invalid? All these different things all have to do with just sort of understanding from the outset how everything should work. Onset, outset, I don't know. Break it down. So at this point, if you like to write like totally perfect pseudocode line by line, you can do that. Or just break out a couple steps to lay out a game plan for the code you need to implement. This is really helpful, especially in an interview if you're timed and you know that you're going to run out of time. It can be useful to write your game plan out so you can show them, hey, this is where I was going. Even though I only actually implemented 40% of this, here's the other steps that I was going to do. So make sure you know where you're going before you just start typing code. Often that's a bad way. You can end up in a hole. You can confuse yourself. It's happened to me many times in interviews. If you just start, you think you know where to start and you'll figure out the rest as you go. Often you pigeonhole yourself into one approach, and then I start to panic because it's not working out. And I take a step back and usually erase everything I've done and start over and plan it out. So then solve, and if you can't solve the problem right away, solve a problem that you can, even if it's simpler. If you simplify, you remove some core difficulty, core challenge, try and solve something where you can then reincorporate that core difficulty back in. So we talked about in 2 videos ago, if you're not sure how to test for something being alphanumeric, ignore that part and just write the problem, write the solution, ignoring the alphanumeric part so that you could then plug it in later. And then finally, what I said was the most important for learning or improving as a developer, looking back on your code and sometimes refactoring it. Sometimes just looking back and analyzing it and patting yourself on the back. Most of the time, there's room to refactor. Even if you're a totally expert developer, it can be very useful to look at other people's solutions or to scrutinize your own and figure out what you could have done better. All right, so those are the steps I recommend if you're ever faced with a tough challenge, especially if you're in an interview. I would absolutely recommend always starting off with understanding the problem, exploring examples. Like 1 and 2, for sure, do that out loud. Make sure the interviewer hears you, bring them into the process, tell them what you're doing. Breaking it down, write the steps down, talk out loud. Solve it, of course, if you can, and then look back on your code and refactor if you can. All of these, honestly, they're equally important in an interview setting as well as in real life. But I think most of you care about interviews for the most part, so I'm gearing it towards that. Okay, so that's the wishy-washy part of problem solving, sort of the approach, the steps that you can take mentally to prepare yourself. Next, we're going to talk about some patterns for code. There are a couple of archetypes, blueprints for solutions that may come in handy. I honestly think this stuff is much more useful in the real world because it applies to all sorts of problems. What we're going to learn next is a little more specific, but for the types of problems it helps with, it really helps. Okay, that's up next. Hey everyone, welcome back. So this section is a continuation, or it accompanies the previous section. They're meant to go together. So if you didn't watch that one, I definitely recommend you start there. I say that about pretty much everything, but in particular, these two go hand in hand. So we're still talking about algorithms, difficult problems to solve. How do you even approach a difficult problem? How do you get better at solving them, whether it's in an interview or on a side project you're working on? So we talked about sort of two different steps, or two things. Devising a plan for solving problems. Before you write a line of code, how do you even approach a new problem? Something that's real head scratcher. And then the second thing is mastering common problem solving patterns. So the last section was devoted to that first point. Just make that clear. Lovely green color. So we're done with that. We talked about an approach. Now we're going to talk about some common patterns that sometimes can come in handy. And I want to say that this section can be a bit of a letdown. This material, I've seen a lot of students sort of get disappointed because they built it up as some sort of cure-all little notebook of patterns that they need to memorize. And then every problem they ever face, every interview challenge they ever face, they'll know exactly what to do. And that's not the case at all. In reality, there are some common patterns that we'll discuss that do apply to multiple problems. There are common approaches to writing code, sort of archetypes for a problem. But that does not mean that you cover every possible scenario on Earth. So it might help you in 1 out of 5, 1 out of 10 challenges you have to face. But even if it's only 1 out of 10, that's still helpful and worth knowing. So there are lots of these patterns, and some of them have names that are official. Some of them have not official, but names that are recognized by other people, like divide and conquer, for example, or greedy algorithms. But some of them are things that aren't necessarily well-known names. The concept might be well-known, but if you tried to Google something like frequency counter, as far as I know, you'll probably find more results about like a detector for counting the frequency of a sound or a waveform or something. That's not what that is. So some of these aren't really official terminology, but all of these are different approaches, different patterns for writing code. And when I say pattern, I think that can get a little confusing. I like to think of them as sort of programming mechanisms, different pieces that you can put in, or sort of a blueprint. I think I've said that a couple times. So we're going to start off with frequency counter. We're not going to cover all of these in this one section, but we're going to cover a couple of them. And the way it will work is I'll introduce the idea, explain it, and then do an example where I show you sort of a poorly written solution to a problem, the naive approach, and then the approach using the pattern that I'm introducing. And then I'm going to try and give you as many opportunities to practice on your own with exercises and solutions and that sort of thing. So first up, we're going to talk about the frequency counter pattern. So that's coming up next. Welcome back. So the first pattern we'll take a look at, it's not really called frequency counters. I don't think it's actually called anything officially, but that's the name I'm using because the idea behind it is that we use an object, usually in JavaScript, to basically collect a bunch of values and their frequencies. So this is useful in algorithms and challenges when you have multiple pieces of data, multiple inputs, and you need to compare them to see if they consist of similar values, if they are anagrams of one another, if a value is contained inside of another value. Anytime you're comparing pieces of data, 2 inputs or more than 2, and frequencies of certain things occurring. And I know that sounds really wishy-washy and not that useful, but I'll show you a couple examples. So what makes this a good approach and a nice pattern is that it's usually O of n time compared to the easier solution, which often involves nested loops, which is going to give us O of n squared quadratic time. So let me show you an example problem, because this probably doesn't make much sense yet. Okay, so here's a challenge. Write a function called same, which accepts 2 arrays. And the function should return true if every value in the array has its corresponding value squared in the second array. So in the first array, there's a bunch of values, and we want to know if the second array has the exact same values but squared. But the order doesn't matter. So it doesn't have to be identical, just squared. It could be mixed up. But the frequency of values must be the same. So here's an example. 1, 2, and 3, and 4, 1, and 9 should return true. So 1 squared, that's in here. 2 squared is in here, 4, and 3 squared is in here, 9. But the order is mixed up, and that's okay. However, something like this, let's look at the second one. 1, 2, 3, 1, 9 is false because it doesn't include 2 squared, which is 4. 1, 2, 1, and 4, 4, 1 is also false because the frequency needs to be the same. So just because 1 squared is in this array and 2 squared is in this array doesn't mean that the frequency is the same. So we need to have 1 in here 2 times because we have 1 and another 1. We need to have 4 in here 1 time because that's what we have over here, right? 2 is in here once. So the frequency matters. It's not just checking if there is a 1, if there is a 4, if there is a 9. It's making sure there's the correct number. So if you want to try this, go ahead and pause it. You don't have to try with this frequency counter pattern, which we haven't really introduced. But if you want to, you could try that or come up with a nested loop solution. But here is what I don't like calling solutions naive because they're often not that easy to come up with, even when they're labeled as naive. Naive more so just means not the best possible solution in this case. So here's a naive solution where we use nested loops. Technically, we're only writing one loop, but then we're using index of, which is itself looping. So I'm going to hop over and demonstrate how this works first, just to make sure we're clear on it. So the idea is we have 2 arrays. Let's say I call it with 1, 2, 3, and then my next array will look like, let's go with 9, 4, let's do 9, 1, 4, like this. Okay. And let's actually add another 2 in there and another 4. So this should return true because we have 1 squared, we have 2 squared, we have 3 squared, and we have another 2 squared, 4. Okay, so the approach here, the very first thing we can do to check, a nice little edge case, or it's not even an edge case, just we can tell immediately if the 2 arrays have different lengths, then we're done. There's no way for it to be true if there's an extra value in here that isn't over here, or vice versa. So we return false. That part's easy. That's a nice short circuit. But here, what we're going to do, I'm not sure where I added that S, return true. We're going to loop over this first array, or we could loop over the second one instead. And we're going to call index of, where we pass in the square of each value. So we loop over this array, we start at 1. And 1 is a silly example because 1 squared is 1. But we're going to ask, what is the index of 1 squared in array 2? So in our case, if we take 1, what's the index of 1 squared in this array? It's this index right here, which is index of 1. It's very confusing, a lot of 1s. And then what we do, we check if the correct index is -1, meaning it's not in there, we return false and we're done. Because if we had something in here like 5, and we're trying to see what index in array 2 contains 25, 5 squared. Well, nothing does. It returns -1. That means that we have a mismatch and we're done. But in the case of 1, if it is a match, and it is, it's right here, then we're going to call array2.splice that correct index, comma 1. And that effectively, what that does is it removes 1 from this array. So then we move on to 2. And then we're going to look at 2 squared. What's the index of 2 squared in this array? Well, there's 2 of them. It just gives us the first one. So it's going to return this index. So this is not true right here. We don't return false. We keep going. We live another day, another loop iteration, and we remove it from the array using splice. And then we look at 3 squared, and it's in there, so we remove it. Then we get to the end of the array, and we look at 2. What is the index of 2 squared? Well, that's 4. That's it. We remove it. We hit the end of the array, and we never returned false, so we return true. So you don't have to do this solution with index of. You could manually, iterate over the entire array yourself, which is basically what index of does. So we could have one loop and then a second for loop that loops over, let me Command Z a couple times, that loops over this array and looks for 1 squared. Is this 1 squared? Is this 1 squared? Yep. Okay. Now we look at 2 and we loop over the entire array, but we would need to still splice, or we'd need a way to remember how many times, we've already encountered this 4, so we can't also apply this 4 to this. We need to make sure that there's the same frequency of values. Anyway, just to show you how it works, as we go through, why don't I just do a console.log array2 so you can see it shrink as we go. And then here I'll call same on those 2, and let's execute it. And you can see the first time through, it looks like this. And then we're looking for a 1, so we remove 1, and now array 2 looks like this. Next time through, we're looking for 2 squared, so we remove 4, and we have this. Next time through, we're looking for 3 squared, which is 9. We remove it, we end up with this. And then next time through, we look for 2 squared, and then we're done. We hit the end of the loop, and we return true. Okay, so that's the naive approach, because it is O of n squared. It's quadratic time. This index of is iterating over the entire array, or potentially iterating over the entire array, which is a nested loop. So as n grows, the length of our arrays, this grows, as does this, and it's nested, so that's a quadratic relationship. We always want to try and avoid nested loops whenever possible. So this is where the frequency counter pattern comes in. Instead of looping over the first array and then checking for each value in a sub loop over the second array, we can loop over each array one time individually, which is what I'm doing here. So here's one loop, here's another loop. Remember that 2 loops is vastly better than 2 nested loops. 2 separate loops, this is going to be 2n. If n is 1,000 characters or 1,000 elements, this means 2,000 iterations. But if we have 1,000 on the outer loop and then 1,000 times on the inner loop, we're looking at 1,000 times 1,000, which is 1,000,000 compared to, what did we say, 2,000? Anyway, so I won't make you, study this in the browser here or in the slides. I'll show it to you and show you how it works, but it is O of n, so it's linear time, much better than O of n squared. All right, so here it is. Paste in my same line that already says same, very confusing. And let's step through the basic idea here. So we use an object, and there's actually 2 objects, and each one is going to it's going to count the frequency of individual values in the arrays. So we'll end up with 2 objects at the end. Let me just print them out so you can see. Let's do console.log frequency counter 1. So that applies to our first array, and then console.log frequency counter 2. And I'll just start by running this code so you can see what we end up with. This is so we get true, that's our return value, because these 2 are the same according to what it should return true. That's what we want. But if we look at these objects that were generated, we end up with each object has a value or a key, like 1, and then it tells us the number of times it occurs in that list. Then we look at 2. The number of times 2 is in that list, 2. We look at the number of times 3 is in that list, 1, right? If we look at this, we're compiling an object that just tells us how many times each value is in that array. And then same thing down here, except we're doing it for the second array. So we say there is 1, 9. There are 2 4s. There's 1, 1. Then the magic is, so constructing this only is 1 iteration over each array to make this. It's not that hard. But then the magic part is that we then just do 1 more loop, and we loop over either one. You could do it either direction, but we loop over the first object here. And for each thing, we take a look at 1 is a simple example. I shouldn't use that one. Let's take a look at 2. We look at 2, and we see that it exists, or it occurs 2 times. So that tells us that we need to have 4 occur 2 times in our other object. Or we look at 3, it occurs 1 time in our main first object, the first array. So that tells us 9 needs to occur 1 time, 3 squared. 3 times 3 is 9 in the second array. So that's what this logic is doing here. So to help me illustrate this, I've updated this. I've added a 5 and an 11. So these are the same length, but they're not the same as far as our criteria, because this 5 does not have a 25 corresponding to it. And we have an 11, we don't have whatever the square root of 11 is in here. Okay, so if I execute this now, I also moved my console.logs up so that we can see them, because I had them down here and we were returning false and we wouldn't see them printed out. Anyway, what's happening now is that we're looping over this first frequency counter object, this thing that we constructed. Constructing it was relatively simple. Hopefully that part makes sense. We start with an empty object, and then we just loop over every value in the array. Could use a for loop. I like using a for of. If you're not familiar with the for of syntax, it's just a nice way of looping over like an array or a string. We just make a placeholder variable like val, and that corresponds to each element in the array. So for each val in array 1, we're going to add 1 to the frequency counter if it's already in there, or we're going to initialize it to 1. So we end up with just this little object that tells us how many times each thing, each element occurs in that list. Then we loop over this first one, and we're going to look at each key. So we're going to look at 1, which 1 is boring, so I'm going to skip it. We're going to look at 2, and we check, is 2 squared? That's what this is. Is that a key in frequency counter 2? So 2 squared is 4. So is there any 4 in our second object? And there is. So this part doesn't return false. Then we check, okay, do the values correspond? If there were 2 2s, there needs to be 2 4s. And if there's a mismatch, we return false. So it's not just a matter of checking if there is a 4. We need to make sure there are 2 4s, as we've discussed. Then we keep going, we hit 3, and we check, is 9 in the second object? And it is. And do the values match? 1 matches 1. Then we get to 5. Is there 5 squared, which is 25? Is there a 25? Nope. So we return false. So hopefully you can see why this is better, at least in terms of big O complexity, as we increase the size of these arrays. We're talking about how many loops here? 3 loops over the entire size of the array. Whatever the largest array is, let's just say, they need to be the same size in order for us to even make it to this point. Because if they are mismatched, we quit right here. So our 2 arrays have to be the same size. Let's say 1,000, like we've already talked about, 1,000 elements. We have roughly 3,000 iterations. Here's 1,000, here's 1,000, and here's 1,000 more. And remember that it's very easy. It's quick to access data inside of an object. It doesn't matter how many things are in there. It's just the way that objects work. We actually talk more about this later in the course. So this is 3n, roughly, where n is the length of the arrays. And we simplify that just to O of n, complexity. Compare that to our naive approach, where we have n squared. So if we're talking about, 1,000, a length of 1,000 for each array, that's 1,000,000 iterations if we have a nested loop. Yes, again, we're using index of, but we're talking about a nested loop. That's what index of is doing. It's just a shortcut, so we don't have to type it all out. Inside of a loop, that's roughly 1,000,000 operations, worst case. So this is a lot worse when we put it that way. So the idea behind the frequency counter, usually use an object, and you use that object to construct a profile, sort of a way of breaking down the contents of an array or a string, usually some sort of linear structure like that, an array or a string, and then you're able to quickly compare that breakdown to how another object looks that was constructed from a string or an array. So we had 2 arrays. We break them down into objects that sort of classify what's in those arrays, and then we can compare those objects. And this allows us to improve our code significantly. So I'm going to show you another example coming up that has to do with anagrams. Hopefully it will help cement how this works, and then we'll move on to another pattern. Welcome back. I'm just here quickly to introduce the next problem if you want to give it a shot. So it has to do with anagrams, writing a function called valid anagram that takes 2 strings, and it returns true if the strings are anagrams of one another. Now there's many ways of solving this. Obviously some are better than others, but my idea or the goal here is for you to try and solve it using the frequency counter pattern or whatever you want to call it. This is a perfect use case where we have 2 strings, 2 items, and we want to compare the occurrence of characters in each one and see if they are the same. So not only if the letters are in there, but also if they're in there the correct number of times. The frequencies are correct. So for example, empty string, that should be true. That one's easy. AAZ and ZZA. So it's not a matter of just checking if they have the same characters, because this has an A, this has a Z, this has an A, this has a Z. It needs to be the same number as well. So this will be false. This is true. Anagram and nagaram. Rat and car, false, of course. I don't know why there's 2 falses. Sorry about that. And yeah, you can watch the rest of the examples or take a look at them. But basically, take one string, take another string, and see if they consist of the exact same characters in the same order, possibly, right? That should be true if we tried cat and cat, but most likely in a different order. And I recommend the goal is to use the frequency counter pattern. So create an object, or you could do it with 2 or just one object that is going to be that will represent the occurrence of each letter in one of the strings. So you'll have to have more than one loop. You'll need to create this object, and then you'll need to loop over the other string, whichever one you didn't use to construct that object, and compare it and sort of update the object with it. So I don't want to say too much. I'm going to give you a solution in a video that follows. But if you want to try it out, I have an exercise actually in the editor so you can test your code and see if it works. And then I'll be back with an actual solution walkthrough. Oh, and before I forget, you can assume all the inputs will be single words. So there won't be spaces, there won't be periods, any punctuation, there won't be numbers. You can also assume that they're all lowercase letters. And so you won't need to worry about, capital A and comparing that to a lowercase a. So everything is lowercase. If this were an interview setting, I would definitely encourage you to ask those questions. What about the edge cases? What about spaces? All that. But we're not. We're just focusing on lowercase words. Okay. All right. So here's my solution for anagrams. Again, there's many ways of doing it, but the way that I wanted you to at least try was to solve it with a frequency counter. Use an object, construct it using a loop, and then use a second loop that's not nested, so we still maintain our big O of n, time complexity. Here's my version. So it's called valid anagram, and it takes two arguments, first and second, is what I called them. And the very first thing I did, just like before, if the length of those two strings is different, if they don't match, then immediately we can throw it out. There's no way for it to be true. There's no possible anagram of two strings that are of different lengths. They have to be the same. So I returned false right away. Then what I did was made an object called lookup. You could call this frequency, counter, just object, obj. I wouldn't call it object. It's a bad idea, but obj is okay. So lookup, and I'm going to loop through the first string right here. And I'm going to create an object that is a breakdown of the first string. So if I called valid, let's just grab one of these examples, like this one right here. So this should return true. And the first thing that I'm going to do, I'll just model this object here. We're going to go through, we loop over it. So I starts at 0, I is less than first.length, I++. So it's going to loop over this first string, which is called first. And I'm going to take the first character the very first time through. I'm using a variable called letter just to make my code a little cleaner instead of writing first I all over the place. So this letter is going to start as A. And I'm going to check if my lookup object already has A in it. And it's empty right now, so it doesn't. So this line is going to either set it equal to 1, or we're going to add 1 if it's already initialized to a value. So in our case, there is no A in our object, if this is our object. So we add, or we initialize it to 1. This is not true. It returns falsy because there's nothing in there. And so we set it to 1. So we set A equal to 1. Then we go through for N, and we set N equal to 1, right? Then we get to A again. And this time we look up A. Well, A is already in there. So this time, this part runs. We add 1. Lookup of A plus equals 1. So we set it to 2. Okay, so we construct the entire object first. And just so you can see what that looks like at the end, I'll console.log lookup right here and run my code. This is what we start off with. So I constructed this lookup, and now we're going to actually use it. So we're now going to loop over the second string, and we're going to compare each character to our lookup object that we created based off of the first string. And what we'll do is, because we have multiple, like A is in here twice, right, or 3 times, so we can't just check is A in here. We need to make sure A is in there exactly the number of times, and they're equivalent. So what we'll do is subtract 1 from A. So if we start at N, we're going to find N, and then we'll subtract 1 from N and set it to 0. If we find A, we're going to go to A and subtract 1. So now we need to find 2 more A's, and we keep going. So just to show you that, we loop over the second string. We make a placeholder variable called letter that is just going to store the individual letter, like N at the beginning. And the first thing we do, if we can't look up that letter, meaning it's not in there, like if we were looking for an S and there's no S in here as a key, then we return false. We're done. Otherwise, we subtract 1. So we go through N, we look for N. All right, well, it's set to 1. Well, now we subtract 1 and it's set to 0. And so now we go through again, and we're looking at A. So we find A, we set it to 2, and then we move on to G. We set G to 0, we subtract 1. Then we go to A again, we subtract 1. Then we go to R, we subtract 1, it goes to 0. Then we go to A, we subtract 1 again, so it goes to 0. And then we go to M, and we subtract 1. And we're done. And so we don't have to do any check at the end. We don't have to see is everything 0 or anything like that. Let's say somehow, what would be an example? If we had some random letter here like an S, like this, so we'd have S is set to 1, and we have another M. So we just did this M and we crossed it off and set it to 0. Then we get to an M again. Well, this time we look up letter and it's going to give us, what is the value for M? 0. So because 0 is falsy, if we run not lookup of letter, not 0, that means this is true, so we will return false. So if we ever encounter 0, that means that there's a problem, because we've exhausted, basically what this represents are the characters that we've gone through in our first thing. So all we have left is an S. There has to be one S over here in order for there to be a match. And if instead we get to a 0, that means that we're working on a character in the second string that didn't exist in the first string. So it's a nice, simple solution, I think. I kind of like it. I think it's kind of cute. It involves, just 2 simple loops. It does not involve nested loops, which you could do easily. We could start with an A here and loop over this string and then look for an A in the second string. Then we could start with an N and look for an N in the second string, and that would involve nested loops. And of course, we would also have to pay attention to making sure that we were crossing things off or removing things as we went, so that we were not, getting a false positive. Hopefully, you can see how it is a helpful pattern in this scenario. Anytime you have multiple pieces of data and you need to compare them, in particular, if you need to see if they consist of the same individual pieces, whether it's anagrams or you're trying to see if if one array is equal to another array squared, each individual piece, or what else have I seen? If you need to tell if numbers consist of the same digits, just in a different order, there's a lot of applications for this. Anyway, moving on to our next pattern. Hey everyone, the next problem-solving pattern we'll talk about, I'm calling multiple pointers. Again, it's not really an official name for it, but let me just read the definition first. The idea is that we create pointers or values that correspond to an index or position, and then move towards the beginning, towards the end, or towards each other in the middle, based on a certain condition. Okay, so what it really comes down to, we have some sort of structure, linear structure, like an array, or a string, or later on, we'll talk about things like a doubly linked list, which you may not be familiar with, or even a singly linked list. If you don't know what those are, don't worry. And the idea is that we're going to be, searching for a pair of values, or searching for something that meets a condition. Usually we're looking for a pair, and I'll show you an example in a moment. And we use 2 references. So we start one reference maybe here, and another one here, and we work towards the middle, towards each other. Or we could start something here and another, like when I say reference, I mean a variable like I and J, which are numbers referring to indices. So we could start I here and J here, and then we move them forward in a certain way. So there's not, a guaranteed direction. This is sort of a loosely defined one compared to what we saw in the last video, or the last sort of pattern, frequency counting. But this does come up pretty often. I'll show you a couple examples. So just to recap, we have a pointer, which is just a variable. We're looking at a specific location in an array or a string usually. And then we have a second one, and we work towards each other, or we work in the same direction. We work from the end towards the beginning. It doesn't matter, but we use 2 pointers. So let's talk about an example where this could make sense. An example. Okay, so write a function called sum0, which accepts a sorted array of integers. So it needs to be sorted, not assorted, but in order, sorted from lowest to highest. The function should find the first pair where the sum is 0. So the first pair where you take one number and you add it to another number and it's equal to 0. So you can see here, -3. First of all, this is a sorted array, -3 up to +3. And in this case, -3 plus 3 gives us 0. So we return that pair in an array. Otherwise, like in this case, there is no pair that sums to 0. So we return undefined. Same thing here. So how would you approach this? First of all, it's important to note, and remember I'm hitting this a lot, but it is sorted. If it was unsorted, then we're kind of out of luck as far as coming up with an efficient solution. But it is sorted, and we're looking for something that sums to 0. So we know that we have small numbers here, and the largest numbers are up here. And because of that, we can use 2 pointers and test for sort of certain conditions to see if we want to move down or want to move our other pointer up. But first, let me show you the naive solution. This is the simpler one that has time complexity of O of n squared, it's quadratic time. And you can see right off the bat, we have two loops. We're using one for loop and a second for loop. So what this one does is it starts a pointer looking at -3, and then we have a second loop that iterates over the entire rest of the array, the entire rest of the string, the structure, looking for something that adds to -3 and equals 0. So looking for 3. So we go all the way through and we happen to find a 3. And so that's a simple example. But imagine that there wasn't a 3 here. Then we would move on to -2 and look through the entire array to find a -2. And if we're talking about a 10,000 item array, that's a lot of iteration when we have these nested loops. But this is the simplest way. You start here and then you compare it to every single other number. And then if there's no match that equals 0, you move forward 1 and compare it to every other number and keep going. So here's the example, the naive version. It does work if I run this. So we've got -4, -3, and so on. We would start here. We look for a match. There is no 4. So then we move to -3. There is no match. We compare all of these different things. We get to -2, and we compare it to every single other item until we hit 2, and we found a match. So even in this case, we had to do a bunch of operations to figure out there was no match for -4. Then we go to -3, and we have to do a bunch of operations. And this is a small array. So this could benefit from a refactor using the multiple pointers pattern. So here's how it would work. We would start a pointer here and start another one up here, because we know that this is the smallest number and this is the largest number. And we start by just seeing what the sum is. What do they add to? Well, -4 plus 5, that's going to give us a positive number, which is 1. And that's too big. We're looking for 0. So 1 is greater than 0. That's not what we want. So what we would do then is move this pointer down to 2, because this is the smallest number we're going to get. So maybe, just maybe, there's a 4 here. But there's not. But our code doesn't know that, so it's going to look 1 below and hope that now we're going to sum to 0. So we add -4 and 2. Well, this time, it's too small because that's -2, and that's less than 0. So that means we're going to add 1 to the left side because there's no match for -4. Remember, it's a sorted array. So we go up. Now we're looking at -3 and 2. Well, we add them together. It's still -1. Well, it's not still -1. It's still negative. It's -1, which is less than 0. So what that means is that we're going to try and add 1 to the left side, which gives us -2. And now we add -2 and 2, and we get 0. And that is the first pair, and we return -2, 2. So way fewer operations compared to using a nested loop and starting here, looking at every single other number, then moving to here, looking at every other number. And this is a simple example where we find it relatively quickly because there's only, 7-ish numbers? I didn't count them. Is it 8? Okay, it is 8. So it's really small compared to 10,000 items, where it would save us a lot of time. So here is that refactored solution where we have 2 pointers, one starting at the left, index of 0, and the other starting at the last index in the array.length -1. And I'll take you over to the code in just a moment, but you can see time complexity is linear. It's O of n, much better than O of n squared. So here's the refactored version, and we've got left set to 0, right set to array.length -1. So left is going to be this index 0, right is this index over here. This is a slightly different array. I put 10 in here, and it looks like our first pair should be -3, 3. Okay, so we start and we check the sum of array of left and array of right. So -4 and 10, that's going to give us 6. And we check first, is it 0? Because then we're done. No, it's not. So if sum is greater than 0, which it is, we're going to subtract 1 from right. So right was this index, which I'm not going to count what position, but we subtract 1. So now we're looking at this place, 3. And we're adding 3 to -4. So we start the loop again because nothing else happens. We have an if, an else if, and an else. So only one of those is going to run. So we subtracted 1 from right, moving it down to here, and start over. So now sum is equal to -4 and 3, which is -1 now. So this time it's not 0, it's not greater than 0, so this else runs, which means we add 1 to our left. So now left moves up to -3. Next time through, we sum -3 and 3, which gives us 0. and we're done. If sum is 0, return array of left, comma, array of right as an array, a new array. And just to prove that it works, there we go, -3, comma 3. And if we give it something that doesn't have a pair, like let's remove that 3 and change this to be a 5. There's no pair here, right? Oh no, we have 1 and -1. Remove the 1. Okay, there should be no pair now, and we get undefined, which is how it's supposed to work. So we stop because our while loop runs while left is less than right. So if they cross over at some point, that means that we've exhausted every possible pair. We tried here and here, that didn't work. That was too large, so we subtracted 1 from right. We tried 5 and -4, still too large, so we went to 0 and -4, too small. So we went to -3 and 0, too small. So we went to -2 and 0, too small. Went to -1 and 0, too small. So then we went 0 and 0, and we have to stop before there. Otherwise, if we try and do 0 minus 0, what are we going to get? 0, which is what we're looking for, but that's a false positive. And if it wasn't 0, it could be any other number. We subtract it by itself, or subtract it from itself, we're going to get 0. So we have to stop there. And that's why we have while left is less than right rather than less than or equal to right. So we have to have that. That's our failsafe, and that means that we're done. And we could explicitly return undefined at the end, but this works fine too. Yep, so that is using 2 pointers, in this case working from the far left side and the far right side towards the middle. That's not the only way of doing it. Next, I'll show you a problem where we actually start from the same side and just look ahead rather than going from the left and the right simultaneously. We just have 2 pointers on the left side. That's next. Hey, welcome back. So here's a second problem we can solve using the multiple pointers or the 2 pointers pattern. It's a bit different, as I already mentioned, because we're not working from the beginning and the end towards the middle, but we still have 2 pointers, and that's really all that matters. 2 pointers moving some direction based off of a condition. So the function you need to implement is called count unique values, and it should accept a sorted array again, and it returns the count of unique values in that array. And it can have negative numbers in there, but it will always be sorted. So in this case, it should return 2 because there's only 2 unique numbers, 1 and 2. In this case, it should return 7 because we've got 1, 2, 3, 4, 5, 6, 7 as far as the unique numbers. Empty, we have 0 unique values. Here we have 4 unique values, -2, -1, 0, and 1. So you can use 2 pointers to help you out here. If you do want to try this on your own, it's not, a direct copy or a clone of the previous solution. It is a little different, but we still have 2 pointers. So here's, if you want to just try it totally blank slate with the 0 pointers, 0 help, 0 hints, go ahead, pause the video and just start it. There's an exercise after this video if you want to try it, and I'll have a solution after that. But if you do want some advice, some hints, pointers, here's how I would do it. This is sort of the intended approach. Start a pointer, let's do this example. Start a pointer here and another one here, and basically compare the two. Well, these aren't equal. So you could create a variable to count how many times they're not equal, how many times there's a different value. But the other thing you could do that's kind of nifty is use the array itself to store the unique values. So build the unique values at the beginning of the array, because there's no rule that says you can't, alter this array that's being passed in. You don't have to use a separate variable. So the solution I'm going to do will actually build up the unique values at the beginning. So we'll end up with a 7 right here, and then we'll end up with a 12 here and a 13. And so our first pointer is only going to move as far as index of 6. If there's 7 items, it will move over. So let me just show you an example. So if we had this array that was passed in, I would have a pointer here, let's call it I, and another one called J. And we compare them. Well, they are the same. So I'm going to move J forward, but leave I where it is. Then I'm going to do it again, compare them. Well, they're still the same. So I'm going to move J, sort of like, J is like my scout, leading the pack, or the charge, or whatever the expression is. And we look at 2 and compare it to 1. Well, now they are different. So then I'm going to move I up here, and then I'm going to put a 2 right here, just like that. So now I is going to be looking at 2, and I'm going to move J forward, and now we're looking at 3. Well, 3 and 2 are different. So I'm going to move I up 1 and put a 3 here. So I'm building up the unique values here. And at the end, I'll have all of them at the beginning, and I can just figure out how many there are based off of what index I is equal to. So I move j up again. Oh, it's another 3, so we don't do anything. We just increase j. Now we got a 4. So I'm going to move I up and put a 4 here. So now I is looking at 4. J goes to another 4. We don't do anything. J goes to a 5. Now we have 5 compared to 4. So I add 1 to j and I put a 5 here. Now we compare 5 to 6. Well, they're different. So we put a 6 right here. And now we're done. J has hit the end of the array. And this really only takes one pass through the array, O of n. And we're looking at how many items are here. Well, the way we would know that is by taking the current index of I. So I is going to be 0, 1, 2, 3, 4, 5. So that's index of I. We need to add 1, of course, because our index starts at 0. So there's actually 6 unique values. And this is one way of doing it. We don't even need a separate variable. We don't need another variable to keep track of, unique values. Now, if we weren't allowed to alter the array, then this might not be the best approach, but it works well for this exact set of circumstances. Okay, so if you want to try it using 2 pointers starting from the left side, you could also start from the right side, of course, and move to the left, but move from one direction to the other with 2 pointers. I'll have a solution after this, after the exercise. All right, welcome back. Here's my solution using 2 pointers for the count unique values problem. So as I mentioned, we use 2 pointers starting from the left, one starting here and the next one, so index of 0 and then index of 1, and then we look forward from there. And then we update the first pointer only at a particular condition, which is when we find 2 unique values, 2 values that do not match. So let's hop over here, and the first thing I'll do is just define my function. Let's call it count unique values, and it will take an array. And let me call it down here with a new list of unique values. So let's do 1, 1, 2, 3, 3. All right, that's good enough, like this. And I'm going to start by making a variable I and setting it equal to 0. So it's going to start right here, right? And then I'm going to make a loop, and this will be a for loop. Let's call it j, and I'm not going to set it equal to 0. I'm going to set it equal to index of 1, which also is value of 1. I hate when that happens, but yeah, index of 0, index of 1. So j equals 1, while j is less than array.length. We don't want it to go any further. And then I++. Nope, j++. So j is just going to go through the entire loop from here to the end. So we have one iteration, and that's it. Now, inside of those iterations, inside of this loop, we're going to compare array index of I and array index of j. So we could just start with that. So array of I and array of j. So what do we want to check? If they are not equal to one another, so array I is not equal to array j, what I'm going to do, first I'll wrap it in valid syntax to make it a conditional statement. If they are not equal, if you didn't watch the entire video where we talked about my approach in the last video, 2 lectures ago, what we do is we compare them. If they are equal, we just move j ahead until we find something that is not equal to what I is looking at. So they're not equal now. We move I up by 1. And then we put this value here. So we don't have to swap them. We just put 2 here as well. So to do that, we just can do I++. That adds 1 to I. So it started at 0. Now we move it up here. And then we set array of I to now equal what is at array of j. And then we move forward again so that j goes up. So now j is 3. This has to be a 2. I forgot to do that. So now j is 3. We compare it. Oh, well, they don't match again. So we move I forward, I++, and we set array of I to be 3. Array of I is equal to array of j. And then the loop moves on. This time they are equal. When that's the case, we don't do anything. J increments automatically because of the loop. So 3 and 3 are equal. So next time through, j goes up to 4. Well, now we have a mismatch again. So we take 4 and we put it here. So first we technically move I up, and then we put 4 here. So now we're comparing 4 to 5. So we do the same thing. We move up, we put a 5 here. Now we're comparing 6 to 5. So we move up and we put a 6 here. And then we move up again. They match, so we don't do anything. Move up again. We put I right here and we put a 7 there. So now we've built up this beginning part of the array that has all the unique values. And it's basically all we want is the length of this portion. And we have that by default. If we look at I and j at the very end, well, j is going to be the very last index of our array. So actually, to demonstrate this, remember this only works with a sorted array, so I can't directly use this array as it is. I need to return it to how it was. So that would be, I don't actually remember it. Let's just say 1, 1, 1, 2, 2, 3, 4, 5, 5, 5, 6, 7, like that. How many unique numbers are there? Well, there's 1, 2, 3, 4, 5, 6, 7. So we should get 7. And we'll call count unique values with that. And then what I'm going to do is in here, let's inside the loop at the very end, console.log I, comma, j. And we have to do it in here if we want j, because j is going to disappear. And if we run it, okay. So we can see, here's I, here's j. And at the very end, j hits the end of the array, and we stop the loop. I is at 6, because that's index of 6. And that's because internally, the array looks something like this, where we have all the unique values right here. This is where I is. We can get rid of this. I is right here, which is index of 6. So we need to add 1 to I, because it's basically the length of this section up until I. And we don't want to start at 0. We want to start at 1 when we're counting. So we want to return I plus 1, just down here. Just like this. And if we now test it out, we get 7. And that should be right. Let's try it with something like this, 1, 3. We should get 2, and we do. Now there is a special case, which if we have an empty array, it's not working. It's giving us 1, and it should give us 0. There's no digits in there. And why is that? Well, I starts at 0, and even if none of this runs, and nothing happens in here, we are returning 0 plus 1. So I'll add a little short circuit at the beginning. Just check. If array.length is equal to 0, just return 0. That means there's 0 unique digits. Now we get 0, but if we go back to 1, let's do like this, we get 5. 1, 2, 3, 4, 5 unique numbers. Okay, so that is one way of solving this using 2 pointers, and it's O of n time. It's linear time because we're only looping once, which is pretty nice. All right, moving on. All right, welcome back. The next pattern we'll talk about is called the sliding window. So this really is useful when we have a set of data like an array or a string again, and we're looking for a subset of that data that is continuous in some way. So, for example, here's a string, and if I asked you to write a function to find the longest sequence of unique characters, so, you would start, let's see, well, we've got HEL, those are 3 unique characters in a row, but then we hit another L right here, so this is the longest one we have so far. ELL, nope, that's not going to work. So then we could look at LOTHER, and that looks like it's going to be our longest string of unique characters, unless I'm losing my mind here, because then we hit this E. So anyway, this is one example of a problem we could solve with the sliding window approach. The other one I'm going to show you has to do with finding a max subarray sum. So we pass in an array like this, and then a number. And we're trying to find the max sum of 2 digits that are next to one another, or in this case, 4 digits that are next to one another. So this would return 10 because the 2 digits next to one another that have the largest sum are 8 and 2, which is 10. Anyway, we'll come right back to this. So what we do is we make a window, which can be a single variable, or it can be a subarray, or even another string if you wanted to. And we move that window depending on a condition. We slide it up, usually from left to right if we start at the beginning. You could go from right to left, you could start in the middle, I guess, but usually we move the window from the left, the beginning of the element or the beginning of the array or string towards the end. And sometimes we might make a new window. So I'll show you what that really means. But it's useful in these problems where we're keeping track of a subset of data in a larger set of data. So back to this problem. Write a function called max subarray sum, which accepts an array of integers and a number called n. So it doesn't have to be sorted, the array. This is just any integers in an array. And then we pass in a second number, as I already mentioned, and your function should calculate the maximum sum of n consecutive elements in that array. So whatever we pass in here, like I already showed you, 2 should return 10 because 8 and 2 is the largest sum of 2 consecutive numbers. Here we have 4. Well, what's the largest sum of 4 numbers? We know it's 17, and I believe that is, I think it's these 4, right? That's 7, 8, 9, yeah, 17. And it's close because there's, this subarray here gives us 16, I believe. Is that right? And we've got this one here, which also gives us 16, but this one is the largest sum of 4 continuous consecutive numbers, which is 17. Also, in an edge case, if it's empty, it should return null. Anyway, that's the problem. And to solve it, there's a couple approaches. Of course, the naive version, the simpler version, is basically to start right here. Let's actually go with this example, 4. Start right here in a loop, and then have a second loop that looks ahead and sums together 4 items. And you create a variable to keep track of that sum. So what is that? That would give us 7, 8, 9, 10. So we'd start with that. And then we move forward one. And we have a new sum starting from here. And we add these 4 together using another loop. And then we compare that to the sum we had before. We take the maximum. And we keep track of whatever the maximum is. And then we would move forward from here and try with the second loop, 1, 2, 3, 4, and sum that together. And we keep doing that. And I have that solution right here. So I'll copy it over. And let's just quickly walk through it. When we call it, the very first thing we do is just make sure, once again, an edge case, if the number is greater than the length of the array. If we're trying to find the largest sum of 3 consecutive integers and there's only 2 in there or 0, we just return null. Otherwise, we make max. And I started it at negative infinity because I wanted to account for if we had an array that was all negative numbers, our biggest sum would still be negative. So starting it at 0 doesn't really help unless we're only working with positive sums. So I did negative infinity. That's not a huge deal. So then what we do, I should mention, we take an array and a num. This is the number of digits we're trying to sum together. And I create a loop. So this loop starts at 0. It goes until the end of the array, well, almost to the end of the array. And I'll show you where it actually goes. What we're doing here is if we're looking at 3 digits in a row, we're going to start here and add these 3, and then add these 3, and keep going. And we don't want to go all the way to the end and try and add 2 more digits together. We don't want to go here. We want to stop here so that we hit the end of the array with our sum. This is the last place we could start our sum, if that makes sense. If we're looking for 3 digits. If we're looking for 5 digits, this is the last place we could start. So that's what this is doing here. And then we add one to I. Okay, so if we're adding 3 digits together, that first loop is just going to start a loop here, and then we'll go to here, 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 and stop right here for our last sum. Then what we do is make a variable called temp. Temp is just going to start at 0. We have max, and so temp will store our sum each time through. So we'll add together these 3, and then add together these 3, and compare it to max. And then add together these 3, and if it's larger than our current max, we'll update max to be temp. So that's what I'm doing here. So our second loop goes through j equals 0. J is less than num j++. So num is the number of digits. So we have I starting here, and then this second nested loop right here that is going to look ahead and add 6 to 2, and then add 9 into our temp variable as well. That's what this is doing, array of I plus j. So we're at I, and then we add I plus j, where j has gone up by 1 index, which is just a way of summing these 3 together. Then we check if temp is greater than max, max equals temp. So we update max if our temp sum is larger. And the very first time through, max is negative infinity. So no matter what we do, we'll be updating max to be these 3 digits. And why don't I just print out our state of, let's do console.log temp, and then also max, like this. And when I call my code on this subarray, or on this array, I mean, you can see that we start off, first couple times, we have 17, the first 3 digits, sum to 17. And then actually again, we get 17. Then next time through, we're looking at 9, 2, and 1. So that gives us 12. So we don't update max. Max is still 17. but temp is 12. Then we do these three, 11, these three gives us 14. Then we get to here, and now we hit 19. And this temp is now larger than the old max. So we update max to be 19. And then that is our max for the rest of the array. And we return 19 at the end. So let's talk about what's not good with this solution. So it doesn't seem like this nested loop is that big of a deal when we're talking about 3 items, when we're only trying to sum 3 things together. And that's true. But if we had a really long array, which I'll type up real fast, let's say we have this massive array, and we're trying to find the largest sum of 20 consecutive digits. What would happen is that we have this first loop, I, that's going for every single item, or almost every single item. Technically, it doesn't go all the way to the end. It stops, 20 digits before the end? But we go all the way through, and each time we're summing from the beginning 20, I'm just going to guesstimate 20 or so digits. We're going to sum 20 together. And then we're just going to move forward 1 and loop 20 times again and add them together. And we keep going. And this can be really inefficient, especially 20 is still a very small number in the grand scheme of things. If we had a huge array, remember with big O notation, we'd take things, extend them way out towards infinity. So let's say we have 1 million items in here, and we're trying to find the largest sum of 10,000 or even 100,000 digits in a row. It's really inefficient to continuously do this and update and now add together another 100,000 digits and then move forward 1, add together another 100,000 digits. It's just not efficient. And a rule of thumb is you can just say it's n squared anytime there's nested loops. So there are better ways of doing this, which is where our sliding window approach comes in. Dum-da-da-dum, here's a sliding window. All right, so here's how this one works. I'll just copy it over. First thing you can see, though, it is O of n. It's linear complexity. We only loop 1 time. Well, technically, there's 2 loops written down, but we only go over the entire array 1 time. So let me show it to you. Here it is. What we do is at the very beginning, we sum together the first, if we're looking for 3 digits in a row, we sum together these 3. And then rather than starting a loop here and summing together these 3, and then starting again and adding 3 together again and keep going like in that fashion like we did in the last solution here, what we do is we keep a variable that just has this total right here. And all that we need to do to figure out the next sum of these 3 digits, we don't have to re-add 6 and 9 and 2. We can just subtract this number and add this number. Or to give you a better example, if we go back to this massive array, let's say I'm summing these digits together. If I want to figure out this sum that comes after it, starting from this 2 instead of this 1, let's do something slightly more manageable. Let's say I'm going from this 1 up until this 4. I don't have to re-add every number together to calculate this sum. All that I have to do is subtract the 1 and add the 5. So that's the sliding window. We're going to create a sum that goes from here up until, let's just say, here. And then to slide it over, we don't recalculate everything. We just subtract this number. So we move the window up like that. And then we add this number in. So that's what I'm doing here. If I get rid of this massive array again, and we hop back, we have this max sum and temp sum. And I have my edge case. If it's an invalid array and we're looking for, a number that's too large, we return null. Then we create our first sum. So let's say I pass in 3. Okay, that works. We're going to just start at the beginning and sum together the first 3 digits and store that in a variable, which is called max sum. And that's it. We don't keep looping. So we just loop 3 times and add them together. Then I set a temp sum equal to max sum. So we just have these 2 variables, and max sum is what I will return at the end. Now what I do is I start another loop, and instead of starting from 0 at the beginning, I start, if this is what we added together already, I'm now going to start my loop from here. If we're adding 3 digits at a time, we already did this sum. So now I'm going to start here. I already have a variable with this sum, which is, what do we get? 17. I'm going to take that variable, which is called temp sum. I'm going to add 2, and I'm going to subtract 2, which is stupid because we get the same thing. But then next time through, let's say we're looking at these 3. This is our current sum, which is 17 again. What we do now is I add 1, and I subtract 6. And so then we're looking at 13. No, 12. We're looking at 12. and we take the maximum between max sum and temp sum. So math.max is an easy way to do that. You could also just do an if statement like we did over here, if temp is greater than max. And this just updates max sum if temp sum is larger than what is in max. So this solution allows us to loop over the array one time. So if we're talking about 1,000,000 digits in the array, we're still only going over the entire thing once. And we don't have to continuously re-loop with a nested loop. All that we do each time through the loop is a single subtraction. Technically, there's a subtraction in here, but we're subtracting one of the array values and adding one array value in. And that's a sliding window. And it's much, way better, much more efficient in the grand scheme of things. It's O of n instead of quadratic, O of n squared. Oh, and I should prove that it does indeed work. If we execute it, we get 19. Let me just declutter things. All right, we get 19. And that indeed is the largest sum. What is it, these three here? Is that right? Yes, that gives us 19. Awesome. Moving on. Hey, welcome back. The next pattern we'll talk about is called divide and conquer. And this is actually a real thing. It's a documented name. I didn't just make it up like some of the other ones. So you can Google it. You can read about it in textbooks. And the way I'm going to approach this video is a little different than how I did for the previous patterns in this section. I'm not really going to type a bunch of code because we do a lot of divide and conquer algorithms in this course. Most of them are a little bit more complex. So when we get to sorting algorithms, we talk about many sorts, I think like 7 different sorting algorithms, maybe 6, I don't remember. And 2 of them, at least, quick sort and merge sort that we discuss, are examples of divide and conquer algorithms. Or we'll get to earlier on before sorting, we get to searching algorithms. We talk about binary search, where that is a divide and conquer algorithm. When we get to binary search trees, we talk about divide and conquering. So it will come up more. It's a little more advanced. I don't want to try and take the entire binary search. There's like 3 videos I have on it. I don't want to try and condense that into one 5-minute video here. So I just want to introduce the idea of dividing and conquering. So what we do is we take a larger set of data, usually an array, a string. It could be a linked list or a tree even when we talk about those, but let's just say an array for now. And rather than starting from the left and moving all the way to the right, let's say we're searching for a value. We start by dividing it into smaller pieces and then doing something to each smaller piece to determine where to go next. So we divide up a larger chunk of data into smaller chunks. And this, depending on the problem, can be a significant helper, but not always. The classic example, the one we'll be starting with once we get to searching algorithms, which is pretty soon, is called binary search, or just search is what I'm calling the function, but technically it's called binary search. So it accepts an array of sorted numbers. It has to be sorted. So 1, 2, 3, 4, 5, 6 is what we have here. Write a function called search that accepts a value and it returns the index where that value is found. So if we pass in 4, it should return 3 because 0, 1, 2, 3, that's where 4 was found. If we pass in 6, it should return index of 5. If we pass in 11, it returns -1 because 11 is not found in here. So the easy approach is to start from the left and just look. Let's say we're looking for 11. We start on the left and we check, is this 11? Nope. Okay, loop to the next thing. Is this 11? No. Is this 11? And we just go all the way through the array. That would be O of n. We go through the entire array one time and we either find it or we don't. Remember that it's sorted. So that solution would look something like this. We have a single loop. Its time complexity is O of n. This is called linear search. We actually have a quick video on this later on. Binary search actually involves something a bit different. It's a divide and conquer algorithm. So if we hop over here and we take a look at a sorted array, I'm going to mix up some of the numbers so it's not just, let's see. All right, let's say this is my array and I want to know if the number 15 is in there. What we could do is start here with linear search. Are you 15? Are you 15? Nope, no, and loop all the way until we find 15 here. Or we can use binary search where we divide the array up. So we just pick a middle point because it's sorted. So let's say this is our middle roughly. And we check, is the value we're looking for greater than 8 or less than 8? And because it's sorted, this will work. And the value we want is greater than 8. We're looking for 15. So we can ignore all of this. Just don't even look at it because we know it's somewhere up here or it's not in the array, but it's definitely not below 8. So then we look at this subarray. We've divided it up. Now we got to conquer it. So now we pick a middle element, and this time, if we pick 15 as our middle, well, that's nice and easy. Imagine we have a much larger array. This is still very small in the grand scheme of things. Let's say we had 1 million digits in there sorted. If we were looking for a value that was towards the end, for example, and we started all the way from here and looped all the way through, that would be a lot of iterations. Although if we knew that the value we were looking for was large, it might be better to start from the right and move to the left. But either way, it still is much slower than binary search, where we take a middle value like this. Let's say we're looking for 950. We'd start here and just roughly say that's the middle. I actually don't think I think the middle's closer to here. Anyways, let's just say this is the middle. Is 950 greater than this? Yes. So ignore everything here. Now, here's our new division that we're looking at. Let's pick something in the middle. Let's say it's like right here. And we care about, is 950 greater or less than or equal to 913? It's greater. So now we only look at this portion. And now we pick the middle again. Let's say 916. Well, it's greater than 916. So we look at this. Now we pick the middle. Well, there's only 2 elements, so we'll pick 917. It's greater. So then we look at this. That's not it. So we know 950 is not in here. And that only took, 4 steps versus potentially starting at the beginning, looping. It might take, it takes n steps, where n is the length of the array, or that's the maximum steps to figure out something is not in here. We'd have to look at every single value if we just start at the beginning. Anyway, so dividing and conquering can really save a lot of time. It can complicate your code a little bit. If you do want to take a look at the solution for binary search, like I said, we have multiple videos where we build this and we talk about how it works, and we talk about how we get to log n, which if you didn't watch the log video in the big O section, you don't remember what log is. It's technically log base 2 of n. We just simplify it. Don't worry about it. We will come back to that. We have a whole video on binary search, or multiple videos. But I just wanted to introduce the idea of dividing and conquering, taking a larger set of data and dividing it into smaller subsets and ignoring other ones. Or in the case of like merge sort, quick sort, we actually will go and merge things back together, sort of sew them back in one at a time from smaller pieces. So those algorithms definitely take some more work. They're broken up into like 3 or 4 videos each. They come later in the course, but I just wanted to introduce the fact that dividing and conquering is a thing. It's a really commonly used pattern. It just happens that most of the time we use it is for more complicated algorithms, not for, small things like finding unique sequences in a string. It's usually for larger, more complex things like sorting a really large list of data. So look forward to that if that intrigues you in any way. We will learn some real divide and conquer algorithms, starting with binary search, and then later on merge sort and quick sort. Okay. Hey, welcome back. So this section is about a topic called recursion. And I think often recursion comes with a lot of baggage. A lot of the students that I've taught in person have heard of the term recursion and approach it with a bit of apprehension. It's somewhat intimidating. And I think that's because it's a little bit tricky to wrap your head around at first. But then once it clicks, it's one of those things that once the pieces fall into place, I think most people don't struggle as much to understand it, and they don't have to. It becomes sort of second nature once you understand how it works. But there is a bit of that first hurdle. And what I want to do, I'm not trying to scare anyone, but what I want to do is actually teach the exact way that I was taught recursion. In my first computer science class in high school, AP Java, there was this teacher. Oh my gosh, what was his name? Mr. Carlson. There we go. I remembered his name. And he read a story to us, a very short story, that helps explain this idea behind recursion. So all that I'll say to preface this is that recursion is it's a different way of thinking about writing solutions. So we can write a solution to a problem the non-recursive way, which is called iterative or iteratively. And then there's also the recursive way. And I know that's insanely vague. So first I'm going to hop into this story. It shouldn't take more than like 30 seconds or a minute. Once upon a time, there was Martin, a little boy named Martin. This was way back before there were computers, back when there was wizards. In our world, there were wizards at least, and alchemists. And there's this little boy named Martin who was training with them. And there was an angry dragon named the Dragon. And he happened to look like the new dragon emoji. So one day, Martin is talking to some wizard, and this wizard gives him a task. The wizard says, I need you to go talk to the dragon, and I'm going to give you a list of numbers, and I need you to come back and tell me if any of the numbers on that list are odd. And they didn't have computers, and they, for some reason, were unable to do this on their own. They needed the help of the dragon. So Martin goes up with his list of numbers. You can see it here. And he says, excuse me, Mr. Dragon, can you tell me if any of these numbers on the list are odd? And the dragon is not in a very good mood. He's a little hungry. It's been a while since he had something to eat. So he's angry. And he says, I'm sorry, boy. I'll only tell you if the first number in that list is odd. So he's not super angry. He doesn't immediately burn him alive and eat him. Instead, he just says, sort of grumpily, I'll only tell you if the first number in that list is odd. And Martin is very upset because he doesn't want to fail at his task. He says, I need to know if any of the numbers are odd, not just the first one. And the dragon is even angrier, and he says, sorry, I'll only tell you if the first number is odd. That's my final offer. That's all I'll do. So then the boy has a little bit of a think. What could he do? And Martin comes up with a solution. He goes to the dragon and he says, okay, fine. What about the first number in this list? And he gives him the whole list. And the dragon says, that's not odd. It's even, as we can see. Then Martin comes back and he says, all right, what about the first number in this other different list? It's not odd. He does it again. What about this number, the first number in this list? Is that odd? And the dragon says, it's not odd. And the dragon's getting pretty bored. And then finally he says, what about this number in this list, the first number? There's only one number left. It's not odd. And then finally, Martin comes back one more time. What about the first number in this list? And it's an empty list. And the dragon is very upset. He says, that's an empty list, you moron. There isn't a number in there. How could anything be even or odd? There's nothing in there. And then Martin triumphantly says, aha! So all the numbers are even in that list. And then the dragon says, I never said that. I only told you if the first number of a list was odd. So then Martin gets out a pen or pencil, or I guess a quill, or maybe just a stick in the dirt. There we go. And he starts drawing, and he says, well, I gave you this first long list. You said the first number was not odd. Then I gave you this shorter list, and you said the first number was not odd. Then I gave you this other list. You said the first number was not odd. Then I gave you this list. You said the first number was not odd. Then I gave you this empty list, and you got really mad at me. But you said that there's nothing in there to be either even or odd. So I can conclude that there's no odds in this list. There's no odds in that list. No odds in that one and that one. And finally, there are no odds in the entire first list that I asked you about. So no odds. And the dragon says, oh, congratulations, boy. You have discovered recursion. He's very condescending. And then Martin is slightly puzzled, and he says, wait, you knew about this the whole time? And it turns out this whole thing was just a test. That's the way I spin it. It's a test, because otherwise it's a pretty big waste of time to send this kid to a dragon. It's a pretty dangerous operation, honestly. Dragons are very unpredictable, just to find out if the list of numbers is odd. But on that day, Martin discovered recursion. So that's the way that I was first introduced to recursion. I'm sure you could update that and make it a little more exciting. But the idea is basically taking one problem and doing it over and over on a smaller piece or on a changing piece until you hit some endpoint, which we call the base case. So we'll get to that. But first, let's talk about our objectives for the section. So we're going to define more specifically what recursion is and how it's useful. We'll understand the two essential components of writing a recursive function. There's two things that have to be there. Then we're going to talk about something called the call stack, which if you haven't heard about, I'll explain what it is. And then we'll also talk about how it relates to recursion, how we can use the Chrome developer tools to debug the call stack and recursive function calls. We'll talk about helper method recursion and pure recursion and compare them. And we'll solve a bunch of challenges and have a ton of exercises. So this is going to be a little bit of a crazy ride for this section. We've got a lot to talk about. Remember what I said, recursion takes a little bit to click. Once you get it, you get it. But if you struggle with it, that's totally normal. I have seen many students take days that sounds scary, but take a lot of time to get it. But then once they get it, they understand it, and it's not a problem. So don't beat yourself up if you have to review some of this or come back later. In an online course, I know it's hard because it looks like this is, 6 or 7 videos of content and it only takes maybe 30 minutes or an hour to watch it all. But that's not the time that I intend for somebody to really take to absorb the content. So just keep that in mind. If you're feeling behind, that's normal with this. It's tricky. Okay. All right. So we talked about objectives. We did that little story with Martin and the dragon. Now let's actually get a formal definition of what recursion is. And secondly, let's talk about why you should care. I did a little bit of, I wasn't trying to scare anyone, but I did a little bit of talking at the beginning about how recursion can be tricky. So let's talk about why it's worth it, why you should care, and why you should push through it if you do have a hard time getting it right away. But first, a definition. What is recursion? It's just a process that calls itself. And in our case, in everything we do in JavaScript or in code, when we say recursion, we're referring to a function that calls itself. So we've seen many a function that calls other functions. That's very, very common. We could have a function called laugh, and inside of it, we would call console.log potentially. That's a function call inside of a function. What's different about recursive functions is they call themselves. So our laugh function inside would call laugh. And you can imagine, first of all, that might make your head hurt already. But then imagine that it's happening over and over and over again, and there has to be some endpoint. Or if we go back to this slide here we have, imagine that we have a function called check for odds. We would call it here, and then in check for odds, it would call itself again on a smaller list. And then that would call check for odds over and over and over again. There has to be an endpoint, of course, or else we just keep going like an infinite loop. But it's slightly different than an infinite loop. But we'll get there. So let's leave it at that. It's a function that calls itself. Now, why should you care? Why do you need to know this? There's a bunch of reasons. First of all, it's everywhere. It's used all the time. We're going to use it a lot in the course for a lot of the solutions we write later on. But even before that, if you've been writing JavaScript, you've probably been using recursive functions without knowing it. Things like json.parse or json.stringify. If you've ever made an AJAX call and gotten JSON back and turned that into JavaScript, then you may have called a recursive function. Now, json.parse, json.stringify are up to the JavaScript engines to implement. So Mozilla has their own, Rhino, I think, their own implementation where they write json.parse how they want to. And it doesn't have to be written recursively, but it often is. So the point that I want to make is not that it's guaranteed that you've called a recursive function, but that json.parse is often written recursively. And actually, I have the source code open for Rhino, and this is the engine that Mozilla uses, and it's written in Java, so don't worry about the syntax. But if we look, it's not as simple as json.parse calling json.parse immediately. Instead, there's a function called readValue, this method here, and readValue calls things like readObject. So let's just focus on those two. readValue, you call that. It calls readObject. Well, if we look at readObject, in the middle of readObject, if we scroll down a bit, it calls readValue again. So then readValue is called, and that could call readObject, and we end up with this cycle where even though it's spread across two different methods, they are calling each other. So readValue is calling readObject, which is calling readValue, which calls readObject, and it's this cycle that goes over and over and over. So that's an example of recursion. But let me show you a simpler implementation. Here's a simpler implementation written in JavaScript. So this is not actually what's used in any of the browsers because browsers aren't written. JavaScript isn't written in JavaScript, but here's an implementation to show what it would look like. So I'm going to take a look. There's this method called walk, which is, here's json.parse. So it's called walk. And inside of walk, it's calling walk. I don't know if you can see that. Oh no, I lost it. There we are. So walk is called inside of walk. It calls itself over and over. I'm getting tired of saying the word walk. It starts to sound very bizarre when I repeat it that much. But what it's doing, if you think of a JSON, a string, it's all nested. When it says walk, it's going to move down sort of to the next line or to the next thing to parse over and over and over until it hits the end. Okay, so a bit of a tangent, but maybe somewhat interesting. Those are two examples, json.parse and stringify. Document.getElement by ID in DOM traversal algorithms. So remember that the DOM is this tree structure where we have all these nested things. They could be 100 layers nested. full of a div inside of a div inside of a div. And if we're trying to search through all of them, one popular approach is to write code that does it recursively. Object traversal, which is just like traversing JSON. Now, aside from these functions like JSON.parse and getElementById, query selector, things that we've used before probably, we're also going to be writing a lot of our own recursive functions later on. So when we write our own data structures, when we create trees or graphs, for example, when we want to traverse them, when we want to search for something across them, often the solutions involve recursion. Now, remember, you don't have to do anything recursively, but sometimes it's easier. Let's put it that way. It's cleaner and simpler to understand rather than doing it without recursion. And I just got ahead of my bullet point here. It's sometimes a cleaner alternative to iteration. So we'll see some examples. We're going to write a couple functions both ways, with and without recursion. And I think we'll make it a little clearer that sometimes it's nicer. So why you should care? One, it's everywhere. You've been using it. That doesn't really matter, I guess, because it doesn't impact how you use things like JSON.parse, but it really is important once we get into these more advanced data structures and we're writing our own parse functions or our own getElementById, traversing a tree, for example. All right, so I'll leave this video off here. Okay, so we're almost to the point where we're going to write our own recursive functions, but first we have to talk about one important thing, which is what happens behind the scenes when functions are called in JavaScript. If a recursive function is calling itself over and over and over again, what happens behind the scenes? And this is important for us to understand in order to write effective recursive code that doesn't break. So in almost all programming languages, there's some data structure behind the scenes that's managing function calls. When they're invoked, often are waiting on other functions to return. There's a special order that happens, right? Functions don't just happen randomly. Like if you have a function called first, and then inside of that function, it calls a second function, you need them to go in the correct order. And so there's a data structure in charge of that in JavaScript called the call stack. So you can think of it as a stack of papers or something. It's actually a data structure called a stack that we'll learn about later. You might have heard of stacks and queues before, but all that we're going to say for now is that when a function is invoked, it's placed on the top of the call stack. So just like if we have a stack of papers on our desk, the newest one that we put on goes on top. And then when JavaScript sees the return keyword, or when a function ends, there's no more code to run, the compiler will remove the top item from the stack. So the idea of a stack, the reason I'm saying a stack of papers on a desk is that you put something on top. When you remove something, you also remove from the top. You don't remove from the bottom of a stack of papers. You take whatever's on top. So that's the idea of the call stack. What I'm going to show you now is what it looks like in the Chrome DevTools when we have a couple of function calls, what the stack actually looks like, how it reflects those functions. Okay, so I have a snippet here that I've made. It's very silly, but it has 4 different functions. There's a function called wake up, and wake up calls take shower, eat breakfast, and then it prints at the very end when everything's done, okay, ready to go to work. So wake up is invoked down here, and then wake up calls take shower, and take shower is simple, it just returns showering. Then we have eat breakfast, and eat breakfast is called, and it's a little more complicated because it sets a variable meal equal to cook food, which is another function. So cook food is going to then be called, and that returns, well, there's a list of items and it picks one at random. So it's going to pick one of these 3 things. That's what this code does, and just return it. So cook food might return eggs. Then eat breakfast was waiting on that. So meal is now eggs. It returns eating eggs. And then wake up was waiting on that. And because of eat breakfast, that was holding things up. Then we move on finally to console.log. Okay, ready to go to work. So I'm going to step through this one at a time, one function call at a time. And the way I'm going to do that, over here I have this call stack window open. And I'm going to add a breakpoint here. So as I hit this little button to run it, or command enter on a Mac, what's going to happen is that over here we'll see things added to the call stack. So I just hit command enter, and I'm going to step through it with this little thing here, this arrow. So first thing that happens is that we get to wake up, and you can see wake up is on the call stack now. It's the first piece of paper put down. But wake up isn't resolved. It hasn't returned something. It's not done. In fact, the very first thing it does is call take shower. So take shower is added onto the call stack. So now we have this stack with 2 function calls on it. So take shower is simple. It just returns showering, and you'll actually see that right here. So we're on take shower now. Return value is showering, and then it's removed from the call stack because it returned a value. Then we move on back to wake up. The next part of wake up, we already did this. Now it's on to eat breakfast. So eat breakfast is added to the top of the stack, and you can see eat breakfast isn't as simple. Eat breakfast is going to call cook food, and cook food is added to the top of the stack. So now we have wake up, which is still waiting for eat breakfast. Eat breakfast is waiting on cook food. So cook food is first, it makes this array of items. You can see that in the local scope, items is created now. Next line is going to pick a random item and return it, which is what happens. We returned protein shake. So now cook food is done because it returned, and we return back to, or I shouldn't say return, we go back to eat breakfast, which was waiting on cook food. So now you can see in eat breakfast, meal in the local scope is equal to protein shake. So we're going to return eating meal, and we return eating protein shake. So it returns, which means that eat breakfast next is removed from the stack. It's done. And finally, we go back to wake up, which has been waiting patiently this whole time, and we are able to console.log, okay, ready to go to work, which you'll see appear down here. Okay, ready to go to work. And now we're done with wake up, and we've finished now. We're at the end. There we go. So there's a lot going on there, but the idea behind it is that as functions are invoked, they're added to the top of the stack, and then they are popped off one at a time from the top as well. So the reason that we're going over this, first, hopefully that was clear, what's happening there. These dev tools are useful. If you've never seen the call stack tool over here, it's very nice to be able to step through and understand the order things are happening in and what's waiting on what. But the reason I'm showing it to you now when we're discussing recursion is that when we're writing recursive functions, we're going to be working with the call stack a lot. So you're probably used to functions being pushed on the call stack and popped off right when they're done. But with recursive functions, it's different. They keep pushing new functions over and over and over onto the call stack. In fact, the same function over and over and over, and it's waiting to be called. So if we take this idea of json.parse, calling json.parse, and it keeps calling itself over and over and over, the call stack is going to look like json.parse, 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 but it has to end somewhere. And that's what we're going to talk about in the next video when we actually write our first bit of recursive code, is where it ends. We've established that a recursive function calls itself, but how do we know when it stops? Because otherwise, isn't the call stack just going to continue to go forever? And we'll talk about that as well. So hopefully this made it a little bit clearer what the call stack is. It's this thing behind the scenes in JavaScript that it's a stack data structure, which all that means is that things are added to the top and removed first from the top. And functions, when they're invoked, are added to this structure. So next up, we're finally going to write some recursive code. All right, welcome back. So in this video, we're finally going to write our first recursive function. So big moment. And the first thing we should do is just talk about the game plan for any recursive function. There's 2 things that must be present. So the idea is that we're invoking the same function over and over, having one function call itself recursively, but there has to be a stopping point. And that's the second piece, which is called the base case. So the base case is where the recursion stops. There has to be an end of the line. It doesn't just continue to call itself over and over and over and over forever. That would be a huge problem. Just like a while loop has to have some place to stop, otherwise it just goes forever and makes your computer angry. So if we go back to this example with Martin and the dragon, every time, let's say that this represents a single function call. Let's call it check for odd numbers. And it's called over and over on a smaller piece of data each time. But that doesn't just go forever. There's a clear stopping point. The code, if we were to write this, and we can do it in a bit, the code would basically have a conditional to check, is the list empty? Is there an empty array for numbers? If that's the case, then stop. So the 2 essential parts of any recursive function, the base case that has to be there, that's the end of the line, that's where the recursion stops. And then different input, I couldn't really think of a good name for this, but basically the recursive call, you're going to call the same function over and over, but each time you want to call it with a different piece of data. You wouldn't want to just use the same list of numbers and check for the first item in that list to see if it's odd over and over and over, because you would never get anywhere. What you would want to do, or in that with the Martin and the Dragon solution, we change the list. We basically chop off one number at the beginning and then pass the list through again and try to do the same thing until we hit an empty list. So there's the different input, and then there's the base case. So let's take a look at a real example now. Our first simple recursive function, it's called countdown. It doesn't do much, it just prints numbers. Starting from whatever number we pass in, let's say 5, it will print 5, 4, 3, 2, 1, and then all done. So I have it in a snippet. There we are. If I execute this, you'll see the output is 5, 4, 3, 2, 1, all done. So we could easily write this without recursion, do it iteratively. I went ahead and typed it up. We could do something like this. Let me comment that one out. Function countdown takes a number. We just loop. Start I at the number, like 5. While I is greater than 0, subtract 1 from I each time. And let's verify that it works. Let me clear this just so we can double check. There we go. So we go 5, 4, 3, 2, 1, all done. Okay, so I just wanted to show that you can easily do this without recursion, and that's not the point. This is something that we all are familiar with, just looping and printing numbers, but to do it recursively is a bit different. So let's walk through how it works. When I call countdown, let's do something simpler. Let's do 3. Countdown with 3. Well, let's just walk through line by line. Is number less than or equal to 0? No, it's 3. So none of this happens. So all we do is print 3, then we subtract 1 from num, and then we call countdown with num, which is now 2. So we print 3, so we can, if we step through, basically print 3, then the next line, num is now 2, so we call countdown with 2. So then let's start over. Is 2 less than or equal to 0? Nope, so we skip this. We console.log num, so that's going to be print 2 again. We subtract 1 from num, turning it into 1, and we call countdown with 1. Then starts over, countdown of 1. If num is less than or equal to 0, that's still false. Console.log num, so then we print 1. I cannot spell print. Print 1, and then countdown of 1, or excuse me, countdown of 0, because we subtract 1 from num, giving us 0, start over, countdown of 0. Now, this is our base case. This is the end point. Otherwise, if we didn't have this, we'd keep going into negative numbers and just forever. So what is our base case? Is num less than or equal to 0? Yes, now it is. Num is 0. So num is less than or equal to 0. So we console.log all done. And then this is important. We return. And we're not returning anything, but we have to have this here, because if we didn't, if we just printed all done, then we'd keep going, right? Console.log 0. Num minus minus would be num is -1, and we call countdown with -1. So we have to have this return in order to stop it. Or I guess if we wanted to, we could wrap this all in an else. So hopefully that's clear what happens. Let me just add our final print all done here. So you can see when we call it with 3, it calls itself countdown with 2, calls itself countdown of 1 with 0, and then we hit the base case and we stop. Okay, so hopefully you survived that first recursive function example. Now we're moving on to our second example. So this is what it looks like. It's called SumRange. And first, try and identify 2 pieces. Can you identify the base case? So a key hint for that is there's only 2 lines here, but a base case almost always involves a conditional to check for something, and then it returns something. That's the end. It's the bottom of the well. You hit the water. You hit the rock. I don't know. That's a terrible way of putting it. There's an end point. Then there's the different input, which I'm still not happy with that term, but there's the recursive call, which we're calling with a smaller piece each time. So in the last video, we were subtracting 1 from num and calling countdown again. Num keeps shrinking towards eventually the base case. Here, we're doing the same thing. So the base case to start is this line. If num is equal to 1, return 1. And that makes sense. I mean, first of all, if we tried to just do some range of 1, if we're going to add all the numbers between 1 and 1, we should just return 1. So that's the base case. And then here is our recursive call. return num plus some range num minus 1. So this gets a little bit crazy, I know, because we have more than one return in here. We're going to step through this one little piece at a time. But think of it this way. If I plug in 3, we're going to start. This is not true, so we skip that. And this is going to return 3 plus some range of 2. And some range of 2 will return 2 plus some range of 1. And some range of 1 returns 1. And then all those things are added back up, waiting on the call stack, and we end up with, 6? So I have it over here. Let's just test it out quickly. If I do some range of, let's do 4, that's going to give us 10, as you can see there. Okay, and 3 should give us 6, and it does. So let's actually walk through what happens. If you feel good about this, just move on and skip this, because I am going to do a detailed walkthrough, just because, it really helps. I think, in my experience, it helps if anyone's struggling to understand what's happening. This is a bit different, because we're not just printing. We're returning and returning and returning and returning over and over and over. So let's walk through this. I call some range of 3. So that's the first thing I do. This is not true, so that doesn't matter right now. Num is 3. But then that's going to return, so if we just write I don't know why I'm doing caps, there we go. Return num, which is 3, plus some range of 2, right? Okay, so some range of 3 is this right here, and it's waiting for some range of 2. Some range of 2, if I tab over here, is going to be called, is num 1? No, it's not, so we skip. So that returns num, which is 2. So I'll try and do this in the middle here. Return 2 plus some range of num minus 1, which is 1. Like that. Okay? So we have some range of 3, the first thing we called. It's waiting. It's basically trying to add 3 to some value, but it doesn't know what yet. Some range of 2 has to be computed, but that's waiting because some range of 2 is going to return 2 plus whatever some range of 1 is. And then finally, some range of 1. When num is equal to 1, this is true. So we return 1. That's our base case. This stops us from free falling forever to a rapid descent. We're returning 1. That's the end. There is no further recursive call. So when we return 1, what happens? Well, this was waiting to see what some range of 1 was. So that gets simplified. That turns into 1, right? So this returns 1. So then this turns into 1. So then some range of 2 is going to return 2 plus 1. This now has a value, which is 3. So then some range of 2 returns 3. Let me just delete it and put it back up here, which some range of 3 was waiting. Some range of 3 basically knew it was going to be 3 plus whatever came back from some range of 2. Well, finally, there's a value that came back. It's 3. So it returns 3 plus 3, which finally returns 6. And that's our answer. So it's kind of complicated to draw out. I picked a small number like 3, but as we go higher and higher, there's many more function calls on the stack that we have to worry about. So we can view this. Let's do the same thing. Let's do 4 this time. And I'll put my breakpoint here. If you grasp this already, skip it. But let's do it now. So we step through. First thing that happens, well, I have to execute it. Command enter. Okay. So first off, some range of 4 is called. That's added to the call stack. This is waiting. Num is 4. Well, it's not waiting yet. It's being executed right now. This is not true. Move to the next line. And it's going to return 4 plus some range of 3. So it's going to wait because it has to have an answer from some range of 3. So you can see in this sum range right here, num is 3. Down here, num is 4. So it's going to do 4 plus whatever this answers or returns. This can't return anything just yet because its return value is 3 plus some range of 2. Num minus 1 is 2. So if you watch over here, as I go to the next step, we get another sum range added to the call stack. In this one, the local variable num is 2. So this first part's not true. Move on. It's going to return 2 plus some range of 1. So finally, our call gets added up here. So now we have another function call added for some range. This time though, num is 1 in this context. So num is 1 which means this is true. So we finally return 1. So remember, this is waiting here. This is waiting on the return value of this. This is waiting on the return value of that. This one is waiting on the return value of this one. This is going to return 1. So when that happens, right here, there we go. Return value 1. And then watch as it gets popped off. There we go. This function now, which was waiting, it was adding 2 plus the return value of some range 1. Well, that now has a value. It's 2 plus 1. So it returns 3. Then this one, when it returns 3, fills in the blank for this second call, which was waiting to see what some range of 3 was. So then we get that answer, returns 6. And then finally, this sum range, which was waiting the whole time patiently to add 4 plus a sum range of 3, which came back as 6. So we get 4 plus 6, which is 10, and it returns 10, and we're done. So I know that there's a lot there, but I hope that explanation helped out a little bit. It's always nice to walk through the call stack, but this one is different than the last video where we just were printing things out. In this case, whatever is returned from the base case matters. It's added on to what the previous function call was waiting for, and then that's added on, and it has this reverse cascade going back up. Okay, hopefully that makes a little sense. We have a couple more examples. All right, welcome back. So we have one more basic recursion example here, and it's probably the most classic example of the most classic intro to recursion function that's used, which is factorial. So if you're not familiar with factorial, it looks something like this as a mathematical expression, exclamation point. You don't read that as 4. That's just 4 factorial, which is equal to 4 times 3 times 2 times 1. And, 10 factorial is 10. I'm not going to type the whole thing out, but 10 times 9 times 8, all the way down until 1. So you could easily do this without recursion, just like all the other things I've shown you so far. How would you do that? Well, hopefully you can visualize it now, but use a for loop. And like here, let's define our function. We'll just call it function factorial. It takes in a number. And then let's make a total variable. Let total equal 1. And then we'll do a for loop. So let's do I equals num. Keep going while I is greater than 0. And then do I minus minus. And then we'll just multiply total. So total times equals I. And then at the end, return total. Should work. So total starts at 1. If num is 3, we're going to loop for I equals 3. So the first time through, we multiply total by 3. So we get 3. Then we subtract 1 from I. It's 2. So we multiply by 2 next time. We get 6. Then I is 1. So we multiply by 1, which technically we don't. Well, let's just make sure it works. I'm going to run this. So let's just do factorial of 3. Okay, we get 6. Factorial of 4. We get 24. Okay, so it's working. There's one small change we can make just to eliminate some redundancy. If total is already 1, there's no reason to multiply by 1 at the end because we're multiplying by 3 times 2 times 1. So we can just do this. I is greater than 1. We multiply by 1. And it still works. Okay, so that's the non-recursive solution, the iterative solution. Next, let's do the same thing, but recursively. Welcome back. Let's do the same thing, write factorial, but do it the recursive way. Okay, so what we need to do, the first thing, aside from just defining our function, the first thing is going to be to understand both the base case and the smaller chunk, the recursive call, the different, whatever we want to call it, basically the two different components. So let me just define it here. It takes in a number like this. And what we're going to do, factorial of 3 is equal to 3 times the factorial of 2. Factorial of 2 is equal to 2 times the factorial of 1. So what we're going to, at the end of the day, we're going to return here num times factorial of num minus 1. So hopefully this part makes sense. But if we just had this, this would be problematic because there's no stopping point. If num starts at 10, then we're going to return 10 times factorial of 9. But then factorial of 9 returns 9 times factorial of 8. But it keeps going. It goes past 0, goes to negatives, and it will go forever. So that's not good. So we need to have the endpoint. Well, what is our endpoint? Well, we kind of can take what we did in the iterative version. We multiply by 1. That's the end of the road. We don't want to keep going to 0 because if we multiply by 0, it eliminates all of our hard work because it wipes everything out, the magical power of 0. So we'll just do something like if num is equal to 1, return 1. Factorial of 1 should be 1, right? If we plug 1 in here, we should get 1 right away. 1 times 1. There's nothing below it to multiply by. And this is it. This is the solution. So it's short. And if we step through it, let's do it with 3 again. It's the same idea behind the last one we did with sum range, right? It looks identical, except we're multiplying instead of adding. So factorial of 3 is going to return 3 times factorial of 2. Factorial of 2 is going to return 2 times factorial of 1. Factorial of 1 returns 1. So then we work back up. So if we just really quickly do this, factorial of 3. Actually, let me do factorial of, let's do 5, a little bit larger, just to show you. And I'm not going to go through it step by step. We're just going to very quickly look at what happens to our stack over there as it continues to grow. Okay, so now num is 1. So we have 1, 2, 3, 4, 5 calls here. Num is 1, which is returned. So then we work backwards. You can see the return value growing from 1. It then is multiplied by 2, then by 3. Now we're going to multiply it by 4. And we get 24. Then we multiply it by 5, and we get 120, and then that's the return value, 120. And you can see the console shows us, it displays the return value of 120. All right, so that is recursive factorial, a very, very common intro to recursion exercise. And it's a pattern, as I already explained, it's basically the same thing here, except we're multiplying now instead of adding. Welcome back. So what I want to do now in this video is talk about some of the pitfalls, the common problems that arise when you're writing recursive solutions. So one thing that happens more often than you might think is that you don't have a base case or your base case is wrong. So what I mean by that is that if we go back to factorial here, without this base case right here, this code just keeps going and adding function calls to the stack over and over. So if we just plugged in 2, factorial of 2, it's going to do return 2 times factorial of 1. Factorial of 1 is going to return 1 times factorial of 0. Factorial of 0 returns 0 times factorial of -1, and it just keeps going forever. There's no end in sight. And if I do run this right now, you'll see what we get. Maximum call stack size exceeded. So this means that, actually, I don't exactly know what will happen if we do try and step through this, but if I try it out, you'll see that our stack just continues to grow over and over and over. So I could keep clicking forever and stepping through this. We're at 100-something calls on the stack right now. But there is a maximum size. It does differ depending if you're on Node, what engine you're using. I think that it's somewhere around 10,000 calls. I'm not positive though, but there's a maximum and we're going to exceed it. So if I just resume the script execution, you'll see we get that error. Maximum call stack size exceeded. Okay, so that's a big problem. Another thing that we could run into is returning the wrong thing or forgetting to return in the first place. So what I mean by that is if instead of returning, so let's say we have our base case, the correct base case, so it should stop. But what if we were just returning num times factorial of num? And this is a simple example. It's easy to identify the problem, but sometimes your code is a lot longer, and sometimes it's harder to walk through each individual step if you don't take the time to pay attention to what you're actually returning. Because even though we have our base case, it doesn't help. We're never going to hit it because we're returning, in the case of factorial 2, we're returning 2 times factorial of 2, which is going to return 2 times factorial of 2 and spin forever. Well, not quite forever, as you'll see. We hit a problem. There we go. Maximum call stack size exceeded. One more potential pitfall is if instead of a return here, if we had a console.log 1, for example. So we still have the base case. Let's change this back to num -1. So everything looks good except that we're console.logging 1 when num is equal to 1. And what do we get? Same thing, maximum call stack size exceeded. Because we printed out 1, here, if we, let's refresh and do the same thing, step through this. If we look at the call stack, okay, so factorial of 2 is called, so we return 2 times factorial of 1. Well, factorial of 1 isn't returning anything, so it doesn't stop execution here. Remember, that's the way that we pop this thing off the stack is by returning, but we're not returning 1. So instead, this is just a nice little extra thing. Oh, by the way, if num is equal to 1, print out 1. But then keep going. Return 1 times factorial of 0. So you'll see that's what happens. Num is now 1. We return 1 times factorial of 0. Now num is 0, and we keep going. And if I keep clicking, you'll see num keeps going down, -7 now we're at. And we'll keep going until we hit the maximum call stack size, or we exceed it. So I'm going to fix that and put it back as return 1. So the importance of returning is, that's what recursion is built on. The idea of this call stack where all these things are dependent on one another, waiting, they're kind of primed in a chain, but we still have to return some value at the end to then send back, and then to add or multiply or do something with to send back to the previous one, to keep going until we get to the original function call of factorial 2. All right, so let's just make sure it still works. Let's do factorial of 5. What do we get? 120. Okay, it's working. Now, one note. In Chrome, the message it's giving me is, maximum call stack size exceeded. This is generally what's known as a stack overflow. Think of a stack, it's overflowing, right? Too many frames on that stack, too many functions trying to be called. So you've probably come across that term before in the name of a popular website, Stack Overflow. That's where it comes from. When you have, usually it's a recursive call. If you see that message, just keep that in mind. This means that your recursion is not stopping. There's never rock bottom. Okay, so that wraps up what I want to say about common problems. You don't have a base case, or you're forgetting to return a value, or returning the wrong thing. All of those can result in a Stack Overflow, which is not good. Welcome back. Next, I'd like to introduce a design pattern that's commonly used with recursion, called helper method recursion. So far, all the recursive functions we've written are single standalone functions like factorial. It is recursive itself. We call factorial from outside the function, and factorial itself calls factorial inside its own code. That's been the case with all the functions we've written so far. With helper method recursion, it's a little bit different. So this code doesn't actually do anything. This is sort of just a pattern that I'm laying out. But with helper method recursion, we have two functions. We have the outer function here, and then inside we have our recursive function. So this recursive function calls itself, as you can see here. Again, this is just the pattern. I'm going to show you a concrete example that does something in just a moment. But that's why it's called helper function or helper method recursion. We have our main outer function that we would call, like as a developer from outside here, we would call outer and pass something in. And then inside the code of outer, there's another function defined, and it is called, and it calls itself recursively. So this is commonly done when we need to compile something like an array or a list of data. We're not simply tabulating, we're not multiplying one value over and over and over like we were with factorial, or summing different, summing range. That was another one we did. If we're doing something like this, collecting all the odd values in an array, it's very easy to do helper method recursion. We create an empty array where we will then store our data in, and then we call our helper function. So the reason we do this, if I just try to define a function called collect odds, which accepts a list of nums, if I tried to make a variable called result, and I set it to be an empty array, this is where we're going to put the odd numbers. Well, if we're doing a recursive function, no matter what I put after this, every time it's called, result will be reset to be an empty array. So how are we going to collect our data? How are we going to have, this piece that persists throughout? And one easy solution is to define result outside of collect odds, like this, and then add to result in here. And rather than having result float around in the middle of nowhere like this, we use helper method recursion, which really just means defining a function around it. So here's my solution, or a solution to this problem. Oops, looks like I'm missing a bracket. I'll update that slide. Oh, there it is. Okay, zoomed in too much. So what we have here is collect odd values, which is what we would actually call down here. We'll pass in, like, I don't know, let's do a simple one. Something like this. And it takes that array in. It makes our result array that's empty. Then here's our recursive logic. And ignoring that for just a moment, we call the helper function, which we defined here, with the array. And then we return result that was defined up here. So this is going to manipulate result. It will be adding to result. And again, the reason we do this is that if we tried to define result inside of here, it would be reset to an empty array every time through. So with helper method recursion, we can get around that. And this is a common pattern when we are trying to compile some sort of result, usually an array or some other sort of data structure along those lines. So the actual logic here, if we do want to walk through this, if we look at helper, it's executed at the bottom with array. So this is array, this is passed in, and we have a base case where if the helper input is empty, if the length is 0, we just return. Otherwise, we check if the first input or the first element, mod 2, is not equal to 0. That means that it's odd. So if it's not divisible by 2 cleanly, it's odd. So we push helper input 0 into result. Then the next thing that we do is call helper, but this time we call it on everything else in the array, excluding that first element. So we make a subarray like this, a smaller array, and we pass that in to helper, and we run it again. And it's not empty, so we don't return. And then we take the first element, which is this, and we check if it's even or odd. Well, it's even this time, so this doesn't run. So then we call helper again, helper input.slice1. So this time, instead of this subarray, we look at this one. So we're always looking at the first element, and we're shrinking that array and shrinking it until it's empty, and we return. Okay? So that's the logic behind it. But this pattern, whether it's odd values or we're doing something else, so later in the course, this is a flash forward. Do not worry about understanding any of this, but this is from the graphs section of the course. We define a method called depth first recursive, which has a result variable. And this actually is, it's an example of helper method recursion. Here is the helper method defined inside of our other function. And we call it down here, and it's updating the result variable. Anyway, we'll come back to this, not the focus. I just wanted to show you that this is a real thing. I'm not just making it up or showing it to you for no reason. This is an actual traversal of a graph data structure, something a little more complex. Okay, so this is one way of doing the solution, but this is not the only way of writing collect odd values recursively. You can do it without a helper function. You can do it without having to define result outside in a different scope and then updating result. It's just that this is simplistic. It's easier to understand. In the next video, I'm going to show you how to do this the pure recursion way, which is not necessarily better. It's a little more confusing, but it is all recursion. There is no helper method. It's a little shorter, but we'll get there. That's coming up next. So helper method recursion is just a pattern where we have an outer function that's not recursive, which calls an inner function, which is recursive. Okay, I'll be quiet. Hey, welcome back. So the first thing I should say is that this video is paired, or it goes along with the previous video. We're going to solve the same problem in two different ways. So in the last video, if you didn't watch it, I recommend you at least skim it. We talked about helper method recursion, one strategy, one approach to solving this problem, collect odd values. So recursively, doing this iteratively is easy. We can use a loop and it's not difficult, but to do it recursively is a little bit more difficult. So collect odd values takes an array of numbers, even and odd, and it should return only the odd numbers extracted from that array without actually changing the original array. So helper method recursion was one strategy, but that's not the only way. We can do it with what's called pure recursion, meaning the function itself is totally self-contained and it's recursive. We don't have some external data structure like we had here, this external result array. We're not doing a nested function, helper method recursion. We're not doing any of that. We can do it with pure recursion. It's just a little more challenging. So here's the code. It is shorter, but it's a little harder to wrap your head around at first. So I'm going to copy this over and show you that it works. Here we go. If I execute the code, collect odd values on 1, 2, 3, 4, 5, it works. We get 1, 3, and 5. Now, if we walk through how it works, it's a little bit different. So we are defining this variable new array each time through. And if you remember in the last video, what I said was if you define this new array each time through, it's going to be reset to be empty. And that's true. This is going to be an empty array every time the function is called recursively down here. What's different is that we don't care. We want it to work that way. And what we actually do is concatenate all the arrays at the very, very end into one array and return that. So let me just walk you through what happens. It accepts an array, 1, 2, 3, 4, 5. That's what we'll start with. Then we define new array to be empty. We check if the array, the input, is empty. It's not. In our case, it's 1, 2, 3, 4, 5. Then we check if the first number in our array is odd. And in our case, it is. So we push that number, 1, onto new array. So at this point, our new array looks like this, just 1. Then we assign new array to equal new array, the current value, dot concat the result of collect odd values on the rest of the array. So array.slice1, if we take this array, for example, 2, 3, 4, 5, dot slice 1, it gives me everything from the first element onward. So ignoring the 0 element, or the index of 0 element, we get 3, 4, 5. So array.slice1 is going to take this array like that, collect odd values of 2, 3, 4, 5. So of course we're waiting, here's the recursive part, we're waiting for this to come back and return a value. And that's going to take a moment. So when we call that, we diagram this out, collect odd values 2, 3, 4, 5. We make a new empty array, new array. Array.length is not 0. It still has values in it, 4 of them. So we skip this. The first number is not odd, it's 2. So we skip it, we don't add it in. Then we get to this line, new array equals new array.concat, collect odd values, array.slice1. So new array this time is actually empty. This is what new array is. New array.concat, the same thing, collect odd values of the array 3, 4, 5. Sorry if you can hear that car honking outside. It's a bit ridiculous. 3, 4, 5, this array, slice 1. So speeding through the rest of this, when we call it next time, we're waiting on this collect odd values 3, 4, 5. Well, what does that return? Well, it's going to concatenate on a non-empty array this time. New array contains 3 because it's the first value is odd. And so then we call .concat on collect odd values on 4, 5. And then this repeats. I'm just going to copy this down. So this time it's an empty array because the first value is even. And then next time through, we're almost there. It contains 5. And we try on an empty array. And then finally, when we call collect odd values with an empty array, if it's empty, we return new array. Well, new array is just empty. So this finally returns this value. So we get an empty array. So then what happens? Well, this was waiting to concatenate this with whatever this returned. And this happened to return an empty array. Okay, so when we concatenate 5 with an empty array, it's just 5. Then we return new array at the end. So we return this. So we can replace this right here with that. So now we can, once again, we concatenate an empty array with this array. And that's going to give us this array. And we return it. So then here, collect odd values returned this. And we concatenate it with this, the array containing 3. So we end up with this array. So then we take this, and that's returned. And we fill it in there. And we concatenate it with an empty array, which just leaves us the same thing. We return that here. Whoops. Which is concatenated with this, which gives us our final return value, 1, 3, 5. So along the way, we use concat to help build up the result. If we just tried to push into new array over and over, it would be reassigned. Instead, new array is just going to allow us to either concatenate nothing, as you saw if I rebuild this. Oh, it won't let me go back. Well, a lot of the time with even numbers, we were returning an empty array or concatenating an empty array with another return value that wasn't empty, that contained an odd value. So we use concat to help us out here. And this is the pure recursion way of accomplishing the same problem. I think personally that helper method recursion is more straightforward. Yes, it does involve a little more code to make that second method, but I don't think that it's a big deal. And when you get to more complex logic and you're working with more difficult logic and data structures rather than just pulling out the odd numbers, you can always do it using pure recursion. You can make that work, but often I prefer to go with helper recursion. But in this case, I kind of like this solution. It's kind of cute doing all this concat over and over and over. Just to show you a couple of tips, when you're using arrays and you're trying to do a pure recursive solution without a helper method, you can use methods like slice, the spread operator, and concat that will make copies of arrays so you don't mutate them. And this will allow you also to accumulate some sort of result. Strings are immutable, so you'll need to use methods like slice or substring to make copies. And with objects, it's helpful to use object.assign or the spread operator. So we will come back to this later in the course. We will be writing quite a few recursive solutions. Hey, welcome back. So in this section, we're talking about search and searching algorithms. Now, when I say search, some of you might think of something like Google right away. Now, the algorithm behind Google and its search is very complex, probably one of the most complicated algorithms out there, and it's probably more like 10 different algorithms that are being tested at any given time and things that are being tweaked, not to mention the fact that this algorithm changes so much depending on who you are, your browsing history, the things that you've done, and the things you've clicked on. So when I search for Howler Monkey, I might see different results than if you search for Howler Monkey. So we're not going to even try and recreate anything like this. What we will get to later in the course, not right now, but later, once we cover graphs and trees and other complicated data structures, we'll discuss how to search and traverse something like a graph, which is closer to what Google is doing. We're not going to talk about the machine learning behind all of this and how it decides, what is best tailored to me, Colt, versus to someone else down the street. We're just going to talk about when Google first started, before it even cared about people and ads and tracking all of that. If there even was a period, who knows? I doubt there was. But if there was, then we're going to kind of approximate that. But for now, what we're focusing on are even simpler searching algorithms that are really commonly used, but we may not often call it search. For example, let's say that we have a string and we're checking to see if there's another string contained in that string. Or let's say that I have a website and I allow people to sign up and they add their username in. So they sign up with a username and password. Well, we need to tell them if their username is taken. So let's say there's not even a database. Let's not worry about how this works. But let's say I have an array of usernames. If somebody types in a username into the form and says, okay, I'm going to be I hate cats. That's going to be my username, and my password will be secretly loves cats 72 or something. If I hit enter, the developer needs to take that username and somehow figure out if it's taken. So if I have a list of usernames, how am I going to figure out if this I hate cats is contained in that list? Now, JavaScript has many built-in ways of doing this. You could, for example, do index of. It's a simple one. And here, let's try that. Usernames.index of I hate cats. This is using a searching algorithm behind the scenes. And so we get 11. And if it weren't in there like that, we should get -1. There are some others that we'll see, some other options. But what we're going to talk about in this section is how these are working behind the scenes and how we can implement our own versions of some of these functions, these built-in methods, and how we can search across arrays and strings. Or one more really quick example, if we had a list of states, an array in the US, I apologize for being America-centric in this video, but if this is what we had, we wanted to make sure a user was inputting a valid state. Well, we could check it against this, but how are we going to do that? What's the best algorithm? We're going to get into that in this section. So what are our objectives? First, just describe what a searching algorithm is. We kind of talked about that a bit. Then we're going to implement linear search on arrays. Then we're going to talk about a slightly better algorithm, binary search, on sorted arrays. So we'll talk about the pros and cons of those approaches. Then we'll implement a naive string searching algorithm, as well as something called the KMP string searching algorithm. So this section is really the first where we're getting into named algorithms. In the recursion section, for example, we talked about how to write a solution to the factorial problem, but it didn't have a name. Like, we haven't really seen code that has a particular name to the solution, but that's going to change in this section. And that will be something that we see throughout the course as a recurring theme. We'll talk about sorting. There's particular names for a lot of common sorting algorithms. So those are our goals. And the first thing we're going to do in the next video is implement linear search. All right. So we introduced the fact that we're talking about searching. For now, we're going to focus on searching an array. So imagine we have this array with states in it, which I didn't type this myself, just to be clear, I copied this. And so it also includes, I think there's 59 items. It includes territories like American Samoa, Puerto Rico's in here, Guam, things like that. But that's beside the point. So imagine that a user types something in and they're trying to, create an address, and they need to enter a state or territory. And for our application, we want to make sure it's in this array. What's the best way of doing that? And the simplest way is just to look at every single element in order and check if it's what we want, right? So if the user enters, let's say, Indiana, we would just start at the beginning and check, okay, is this Indiana? Nope. Is this Indiana? Is this Indiana? Is this Indiana? And we keep going until we get to Indiana. And in that case, we return something, true, or we say the index that we found it at. Or if it's not in there, we keep going until the end. And then we have some logic at the end that says if it's not found, return false or return -1 or something like that. Now that approach is actually not a bad approach. Now in this situation where we have sorted data, alphabetically sorted, there are better ways. But let's go back to, I think I had a list called usernames. This is unsorted. So there is no order to this at all. Now somebody enters, I hate cats as their username. How do we check if it's taken or not? In that case, the best way of doing it is to check every single element one at a time. Are you, I hate cats? No. Next. Are you, I hate cats? Nope. Keep going until we find it or we get to the end. Now that is called linear search. And in fact, JavaScript is doing that. Things like index of, which we talked about, includes find index. All of these methods are doing the same thing behind the scenes. They're checking every element one at a time to check if whatever we pass in, so let's do index of. Let's do usernames.index of Tommy, index of 0. Let's do index of Q, which is towards the end, 15. We do index of something that's not in there, -1. We could also do the same thing with includes. I'm not going to go through all these methods, but let's try, does it include Tom? That's true. Does it include Toms? That's false. So what's happening here is that it is going through and checking each item to see, are you Toms, over and over until it hits the end. And if you looked at the source code, you would actually see the algorithm that we're going to talk about. And it's very straightforward. It's called linear search. So we've already been describing it. We visit one item at a time, starting at the beginning, moving forward, or we could start at the end and move backward. But it doesn't matter. All that matters is that we're moving at a set interval, one item at a time, checking every single thing. So if we were to have this list of numbers, this array, and we want to check for 12, we want to search if it's in there. We just start at the beginning. Is 5 12? Nope. Is 8 12? No. 1 is not 12. 100 is not 12. 12 is 12. And then we return true, or we return the index, 0, 1, 2, 3, 4. It depends on what we're doing. So for index of, for example, it would return 4. For includes, it returns true. So that's linear search. And what I'm going to do now is something that is a bit different than how we've structured the course so far. I'm going to give you pseudocode to try and implement it. And I encourage you to write this code on your own. This is a nice and simple one. Here's the pseudocode. And then afterwards, we'll go through it and I'll write up the solution. So write a function, call it whatever you want, but it accepts an array and a value. So call it linear search, and it takes an array full of, let's just say it's numbers, but it doesn't matter really. Let's say it's numbers and then a value, another number. You just loop through the entire array and check if the current array element is equal to the value that we pass in. And if it is, return the index at which it's found. and if it's never found, return -1. Okay, so loop through the entire array, check for a value, whatever it is. Let's say we're looking for 3. If you find 3, return that index. If you don't, return -1. So this is possible in just a couple lines. Don't overthink it. Give it a shot. In the next video, I'll show you a potential solution. And keep in mind that even though this is simple, that doesn't make it bad. Like we discussed, it's used by built-in functions, things like index of, for example. Okay, see you in the next video. Okay, so in this video, I'm going to implement our basic linear search. So here's the pseudocode again. We're going to write a function. Let's just call it index of, or linear search, and it's going to accept an array and a value. So we can start there. So I've made a snippet already called search linear. I'm having them all start with search, just like I did with recursion, so that they're just grouped together. So I made that over here, new snippet. I'm going to close that away now. And let's define our function called linear search. And it takes an array and a value. Let's do it like that. All right, so that's the first step. So I should be able to call it like this, linear search, pass in my array of, we'll just do numbers, 34, 56, 1, 2. And then the value I'm looking for is 1. And it should return the index, which is 0, 1, 2. It should return 2. So the next step is to just loop through the array and check if the current array element is equal to the value. So let's start by looping through the array. So that's going to be a for loop. Or, we could do a while loop if you wanted to. You could even just do a for each. There's many ways, but we'll do for var I equals 0. We're going to go from the beginning. So while I is less than array.length, add 1 to I. And then we need to check if the current array element is equal to the value. So we access the current array element with arr, array of I, and we're going to check if it's equal to the value. So we need to make this an if statement. And if that's the case, what are we going to do? We're going to return, well, we want to return, as you can see here, the index at which the element is found. So that's pretty easy because we already have I, which is why I chose not to use a for loop, or a for each, although you can still do for each with an index, but we have I right out of the box because of our loop, so we just return I. So in this case, I will be 0. We start, we check, is array of I equal to the value? No. Is 34 1? Nope. Next up, I is 1. Is 56 1? Nope. Next time through, I is 2. So we check array of 2, which is 1. Is that equal to 1 that we're looking for? Yes. So we return I, which is 2. Then we have our final catch-all. If the value is never found, return -1. And the easiest way to do that is just after the loop. That means we've hit the end. So if we haven't returned by now, that means it's not in there. So we can just return -1, just like that. And a small simplification that we can make, we can do this all in a single line. The if statement, the conditional, just move that back up there, like that. Just shorten it a little bit, but it's just a personal preference. So if array of I is triple equal to value, return I. So now let's test this out. So linear search of this, we should, if it works, get 0, 1, 2. I'm going to use command enter to run it. And there we go, we get 2. Let's try it again. Let's add some other numbers. And let's check for 56. Which is actually, wow, I'm so bad at picking random numbers. I picked the same number twice. Let's change this one to be 51. And if I run it, we get index of 6, 0, 1, 2, 3, 4, 5, 6. Finally, let's test it on something that's not in there, like 100. We get -1. Now, if I still have my states array, there we go. Because I made this a snippet, I should be able to do linear search, pass in states, and then check what's the index of Texas, for example. And we get 50. And if I check for, let's do one more, how about Texas with an extra A? It's not in there. Cool. So this is linear search. This is what, behind the scenes, the built-in index of is doing. Any of these basic searches that we already talked about in JavaScript, what else was there? There was one, find index, index of, includes, all of those are using a linear search. And the last thing we should talk about is the big O of this. So take a moment and try and figure it out. The time complexity. As the length of that array grows, how does the time that it takes, the worst case, how much time does it take? And the answer is that it's O of n. So as our array gets longer, we have to do more searches. We have to do more operations. If we're searching for the last item, Wyoming, we might have to do 59, or we would have to do 59 searches. But if our states were instead 5,000 states, and we're searching for the last one, we would have to check 5,000 different items. So as n grows, as the length of the array grows, so does the amount of time. So this is O of n. It's linear, which is also, it's called linear search. Gave it away a little bit. And next, we're going to see another search that works differently, where if the data is sorted, as I hinted at, there's a better way of searching. And it's a little bit more complicated, but it's a fun sort of first algorithm to step things up a bit from linear search, and it's faster. So we'll see that in the next video. Welcome back. I've decided to make a separate video on Big O for linear search. I've actually already covered this content, but I realized some people were skipping through videos and not watching everything. So if I have a video titled Linear Search Big O, I found more people will actually watch that because it's really important stuff. Same thing for binary search after this. All right, so here's a quick video on how linear search performs, at least as far as time complexity is concerned. So best case, we have an array of 1,000,000 integers or 50 integers. The very best case is that we find the thing we're looking for right away. So that's the best possible scenario, right? But that's pretty rare, depending on the size of your data. The worst case is O of n. So if we have 1,000,000 integers in an array and we're searching for the last one, or we're searching for something that's not in there, we're going to have to look 1,000,000 times. If we have 50 things in there and it's the very last element that we're looking for, we're going to have to look 50 times. And average is also O of n. And you might think, well, isn't it actually less than O of n on average? Because sometimes we'll find it, right away. Sometimes we'll find it in the middle of the array, 2/3 of the way, 3/4 of the way. Shouldn't that average out somewhere? And the answer is no, not as far as Big O is concerned. We care about just the general trend. So as n grows, as the length of the array grows, or the length of the string, whatever we're working with, so does the average amount of time it takes. Remember, we throw away all constants. So 2n, half n, 0.25n, those are constants. We ignore those and we just simplify it to O of n. Okay, so that's linear search. It's the best we can do with an unsorted piece of data. But next, we're going to talk about binary search, which is much better. And I'll have a separate video afterwards, once we learn how to implement it, on the big O of binary search and how we derive it. That's coming up. All right, welcome back. So we're moving on to our second searching algorithm. And this one can be a significant improvement on linear search that we saw in the last video. It's called binary search. So it can be much, much faster. We'll get into the specifics with Big O later on, but it can be faster. Rather than eliminating one element at a time, like we did in linear search, where we checked one element, is this it? Nope. Is the next one it? Nope. Is the next one it? Over and over and over. In binary search, we can eliminate half of the remaining elements at any given point. However, there's a really big caveat here. Binary search only works on sorted arrays. So the data has to be sorted from, if it's numbers, lowest to highest, or highest to lowest, or strings, alphabetical, there has to be an order to it. So imagine we have our same states array. You don't have to imagine because it's right here. And this is sorted alphabetically. So you can see Alabama down to Wyoming. And let's say that we're doing the same example where we ask a user to enter a state and for their address or something, and we're going to verify that it exists in this array. Now, first of all, this is a very short array in the grand scheme of things, so linear search isn't really going to be it's not going to take much time, and the milliseconds, probably less than a millisecond. The tiniest fraction of a second that we're saving with binary search isn't really worth it. But since it's already sorted, it's a good example. Let's say that someone enters Oregon as their state, so in quotes, and we want to check if that's in here. Well, since it's sorted alphabetically, the way that binary search works is that we pick a halfway point in this array. So somewhere, and I'm not going to count exactly, I think there's 59. I'm not going to count the exact halfway point, but let's just guess roughly. Let's say that we pick states of, I think 29, it's 29.5, right? So we'll round down. So we pick our first spot, we pick the middle because we know it's sorted, in this case alphabetically. So the middle should be the middle sorted element. And then all we do is we check. So we find Missouri, there you are, and we check, is Oregon greater than Missouri or less than? In our case, alphabetically, is it after M, Missouri, is it after that in the alphabet or is it before? And it's after. So now we only care about this part of the array. We've just eliminated all of this. We don't care about the beginning. And we check halfway through the next little bit. And I'm just going to eyeball it rather than doing the math. But let's say halfway through is around 44. So let's say check states 44. That gives us Pennsylvania. So now this is the middle of this array here. And we go to Pennsylvania and we check, is Oregon before or after Pennsylvania? And it's before. So now we care about this list. From Missouri to Pennsylvania, we know that it's somewhere in here. We eliminated all of this here. So now we're going from Missouri to Pennsylvania and we pick the halfway point again. And I think this is 16 or so. So let's go to the 8th one, 3, 4, 5, 6, 7, 8. So we go to New York and we check, is Oregon greater or less than New York? And it's greater, so it's between New York and Pennsylvania. So we pick somewhere in the middle between New York and Pennsylvania. Let's say that it's Ohio. And we know that it's greater than Ohio, so it's somewhere between Ohio and Pennsylvania. We pick the middle, and now it's Oregon. And I know that seemed like a lot of work, but remember that was only, 5 or 6 guesses compared to if we started at the beginning with a linear search. We check this. Is this Oregon? Nope. Is this Oregon? Nope. Over and over and over. So it saves a lot of time if your data is sorted. So let's get down to the details of the implementation. So the idea is dividing and conquering. So we split up the array into 2 pieces. We pick a pivot point in the middle usually, and we check the left side and the right side and see where, based off of what we're looking for, where it will be in which half. So let's search for 15 in this list. Remember, it has to be sorted. This doesn't work at all if it's not sorted. So if it's sorted here, we're going to start by picking, we're going to call them left and right. So we're going to change the window of where we're searching because remember, we can throw out half of the array roughly every time. So we're going to start with left at 1 and right at the end, 19. And then we're going to pick somewhere in the middle. And I think this is an odd number, so you can round down or round up, just be consistent as far as where you pick. So I think we're going to pick 11 here. I know we're picking 11. And we check, is 15 greater than 11 or less than 11? And it's greater than. So now we eliminate all of that to the left, and we make the new left 12. And the new right is the same, it's 19. Now we check somewhere in the middle. So we're going to check 17 as our middle point. And we check, is 15 greater than or less than 17? Is it on the right side or the left side? And it's on the left side. So we can eliminate 17, 18, 19. And now we have a left at 12, a right at 16, and then the middle is 15, which is our only choice. And we check, is 15 equal to 15? Is it greater than or less than? And it's equal. So we found it. So that only took 3 checks, 3 guesses. We checked the middle first, 11, and we knew it was greater. So we did a second check. We picked 17, that was too big. And then we picked 15, and that was correct. Compared to starting at the beginning, 1, 2, 3, 4, 5, 6, 7, 8, 9 guesses using linear search. So if we have a sorted array, numbers or strings or whatever it is, as long as we can compare easily to check if something is greater than or less than in some respect, if we can do that, then we can implement binary search, which is much faster. All right, so let's get on with the details of the implementation. Like I did in the last video or 2 videos ago for linear search, I'm going to give you some rough pseudocode, some kind of bullet points that you can follow, and you can fill in the blanks. It's not going to be a line-by-line guide to what you need to do, but it should set you on the right track. And if you have the time, the energy, the willpower to do it, to actually write it out yourself, I highly recommend it. It's not terribly long. It's maybe 8 lines, definitely less than 10, and 2 of those are just the function definition anyway, so it's pretty short. And definitely worth your time. So write a function, we'll call it binary search, and it accepts a sorted array. Remember, we have to assume that it's sorted and a value that you're looking for. And let's also assume we're only working with numbers for now. Then you need to create 2 variables. One that's going to point to the index that that we're starting at, so 0 for our left arrow, our left pointer, and then a right pointer at the far other end of the array, the end. So that's going to be whatever the length is minus 1. So we'll have left is 0, and then right is 10 or 1000 or whatever the end of the array is. Then roughly what you're going to do, you're going to loop over and over, and there's 2 things that you're checking for. One is, have you found the element? So while you haven't found the element, keep looping. But along with that, there's a second condition, which is you want to make sure that you're only looping while the left comes before the right pointer. And then you're also going to pick the middle. And you can just take an average of the left and the right, not the values, remember, but the position. So if left starts at 0 and right starts at 10, then you could take the middle to be 5. And then you're basically going to loop, and you're going to check, first of all, is the element equal to the middle? Is the middle what we're looking for? If it is, then just return, we're done. So if you find that value, return the index. If the value is too small, then you're going to move the left pointer up. And if the value is too large, you move the right pointer down. And then finally, at the end, if you never find the value, just return -1. Okay, so there is some flexibility in your implementation. There's a couple things that I didn't mention here that we'll talk about in the next video, like small changes we could make. But this is a rough outline. You pick a left, you pick a right, you pick a middle, and then you loop. And you basically keep looping while you haven't found, while the middle is not the answer. Then you're going to check if your value is less than or greater than the middle. And then depending on that, you reassign the left or the right, and you pick a new middle. So in the next video, I'll have a solution walkthrough. Hey, welcome back. So let's get on to implementing our own version of binary search. So again, here's the pseudocode. First, I just need to make a spot to actually write the code. So I've already done that. I'm doing it as a snippet again. I'm calling mine search binary. It really doesn't matter. If I were you, I'd probably do this in a file somewhere, save it on your computer, but this is easier for me. So I'm going to define our function. All that we said was that it needs to accept a sorted array and a value. So I'll just call mine binary search. Hopefully this is large enough. Let's see, shrink some of this down. Okay. Binary search takes in an array. We'll just call it ARR. And then the value, I'll call it element or LM. So for example, we should be able to call it with, let's do something relatively short, 2, 5, 6, 9, 13, 15. Almost all odd numbers. Let's do 28. Okay. And then let's say that we're looking for 15 in there. All right. So right now that's obviously not going to work. Next, we need to set our left and right and middle pointers, or I'm going to call them, I kind of prefer start and end and middle. And what we want to do is set the start to be here, the very beginning. Every time we don't want to exclude any of the array. So we always want to start at the beginning. So that's easy. Just make a variable, call it start equals index of 0. Then I'm going to make end. And end is going to be the length of the array, but we need to do -1. Otherwise, we're going to be out of bounds. So we want this index, which is it 6? 0, 1, 2, 3, 4, 5, 6. Yes. So 0 and 6. And then we need to take the middle. And this is just to begin. And the middle is just the average of those two. So in this case, 0 and 6, the average is going to be 3. 0, 1, 2, 3. So that's going to give us this position 3. But if we had one more item in here, like 30, then that throws everything off. So if I just had start plus end, and I need to add parens to do the average. Otherwise, it will just be start plus end divided by 2. This case, it's the actual average of them. But if we take a look, we're going from 0 up until 7 now. The average is 3.5. There's no index of 3.5. 0, 1, 2, 3. It's going to be right in between 9 and 13. That's not going to work for us. So that's where I'm going to do math.floor of that whole thing. You could also round up if you wanted to. You just need to be consistent in what you pick. Okay, so at this point, this is what we're looking at with this exact array. We start is going to be set to index of 0, which is right here. Then we have end is set to index of 7 in our case, which is now 30. And then the middle is going to be index of 3.5 rounded down, which gives us 3, 0, 1, 2, 3. So we have 9. And just to verify, we could do a console.log, start, middle, end, like that. And if we execute this, did I get anything? There we go, 0, 3, 7. So that's what we expect. Now we get into the actual logic. Well, what we want to do here, we want to continue to loop and repeat this process where we select a middle. Well, first we need to check if the middle is correct, right? Right off the bat, we could have picked 15. We didn't. We're working with 9. But let's say we were looking for 9. we picked the middle of 9 right away, so we need to check if we got it right. And if we didn't, are we greater or less than? Are we looking, is 9 too big or is 9 too small? In which case we need to start searching over here only, or start searching only over here only. So let's start with just the simple while loop. So I'm just going to loop over and over while the element, while array middle is not equal to what we're looking for. So while the middle is wrong, let's put it that way. So this first time, middle is 9. That's not what we're looking for. We want 15. So we're going to repeat this code. Now the code that we're going to do, first we're going to check. We can assume if we're in here, that means that the middle is either greater than or less than. If the number we're looking for is less than the middle, so if our middle is 9, let's say we're looking for 6. 6 is less than 9. So what we want to do is shift our end down to 6 now. Now you might think we could shift the end to 9, and that would work, but it's redundant because we know that 9 is not the answer already. We checked it. So we're going to set the end to be middle minus 1. So this is our new window. Likewise, the other direction, like in this case with 15, we check 9, that's too small. So we're going to move our window all the way up to here. So our start is now 13, and our middle is going to be 15 or 28. We'll round down, so it will be 15. So we want to do middle plus 1 or middle minus 1 because we've already tested the middle. So let's do that now. I'm going to have a simple if statement. If the element is less than array of middle, like that. If that's the case, like if we're looking for 6, we're going to set the end. We're moving the end down to here, right? So end equals middle minus 1. And then we have else. There's only one other choice, because if it's equal, if we actually got it right, then we're out of the loop. But we haven't gotten it right, so we're either greater than or less than. So else, that means that what we're looking for, in this case 15, is greater than 9. We need to move the start of our window to 13. So start equals middle plus 1, just like that. Then the only other thing, well, this isn't the only thing, but another thing we need to do is now change our middle value. We just need to recalculate it. So our first time through, let me just copy this. This is what we started with, and then we checked it. So array middle is not equal to element, right? 9 is not equal to 15. So is the element less than array middle? Nope. So skip this. Else start equals middle plus 1. So middle plus 1 is 13. So that means that our start is now 13 here. Our end is still 30. It hasn't moved. But we need to recalculate the middle. So we need to average 13 and 30. Well, not 13 and 30. We need to average those indices, which is going to be, what are we at? 0, 1, 2, 3, 4, and 7. So I'm just going to copy this exact same line without the var in that loop. We just get a new middle. So now middle is going to be math.floor of 4 and 7. So that's what, 11 divided by 2. Floored is going to give us 5, index of 5, which is this item here. So this will be our new middle. And just to verify that, let's move this line into the loop so that we see what we get each time through. Okay, so I'm going to run this now. Let me clear my console. Make this a little bit bigger. Okay. And, oh, it looks like it's only running once because at the end, we got the answer correct. So I picked the example of 15 was too easy, but you'll see at the end, it's 0, 3, 7. So that's what we have, 0, 3, and 7 indices. Then it updates to go from 4 to 7, which is what we have here. And the middle is 5. And what do you know? That's what we're looking for, 15. So we broke out of the loop because array middle is now equal to the element. Now if I pick something else, let's say I pick 28 this time, we'll get an extra step. Execute it again. There we go. 0, 3, 7, same thing. But this time 28 is greater than 9. So our window now is from here to here. And the middle is 15, which is what we checked. And that's too small. So then we have another iteration. And in this case, it's too small. So what do? We shift the start up again. Let me get rid of the M. And the start now goes to 28 here. Our end is 30. And our middle when we take the average, we're going to round down. So our middle is also here. So it looks more like this. And that now means that we've guessed the number correctly because our middle is 28. And you can see that our middle is index of 6, our start is index of 6, our end is index of 7. We've found it. So at the end, what we should be doing, for now at least, is just return middle. And if we test this all out, we're returning 6, index of 6, and that's correct when we're looking for 28. If we're looking for 5, we're returning index of 1. That's correct. There's a big problem with our code though. And the problem is if the number isn't found in there, our code doesn't handle it. And I'm not going to do this. I recorded this video once before, and I actually showed what happens. There's an infinite loop going on. Hopefully, we'll see if you can spot why. But let's say I'm looking for 50 in here. We're not going to find 50. Our code doesn't handle it. And the browser just keeps looping over and over and over. And with my recording software, plus the browser doing that, my computer was really not happy, and it got like 1,000 degrees. So I'm not going to replicate it here. But what would happen is that we would get basically thousands and thousands. Eventually, it would be shut off, but tens of thousands of iterations, if not more, because we're never going to find that element. And the only way our loop ever stops is when we find it. If our middle index is equal to the element, we break out. But our middle index is never going to be equal to, or the item at the middle index is never equal to 50 or 1 or 14 or any number that's not in here. This is going to go forever. So what's our other stopping condition? Well, if we look at what happens, as we approach a number that's not in there, we do the same thing, right? 2 is our start, or 0 is our index. This is our end, 7, and this is our middle at index 3. Well, we check 50 is greater than 9. So we move the window up to here, as you see there. So now our start is 13, or index of 4 up to 7. We take the middle, index of 5, and 50 is still greater than 15. So now we move up again, and this is our new window. And our middle is 28. And we check, is 50 greater than 28? It is. So what's our final iteration going to look like here, or what should it look like, is that we're going to move the start to be middle plus 1, which is 30. So then we end up with everything, start, middle, and end, all at 30. We've hit the end of the list. So then what's next? Because our code is still saying, all right, well, the middle is 30. We're looking for 50. So we need to move the start to go up 1. And there isn't anything after that, but it's going to increment our start, or it will increment our start to be 8 at that point, which is out of bounds. So then if we tried to do that array of 8, we're going to get undefined, and then we're going to start comparing things with undefined, and it's just not good, and it's going to keep going forever and ever. So we don't want that. Okay, fine. I am going to show it to you what happens, and my computer's not going to be happy. Here we go. As you can see, it just keeps going and going over and over, and it sets the start now is 8. Okay, I'm back after my computer's not very happy with me, but it worked out. So what happens at the end is that our start, middle, and end converge, and then our start gets above. Our start is set to be middle plus 1. So the next time through, if we're working with the start is 8, the middle is 7, and the end is 7, if we go through again, we're checking is the array middle, which is still 7 because we take the average of these, 8 and 7, and you floor it, and you're still stuck with 7. So our middle is not going to budge, and it stays at 7. And then we go through again. Is element less than array middle? No, it's greater than, because we're looking for 50. So 50 is greater than, so we get start equals middle plus 1. So start is 7 plus 1. So we're not moving anything, and we get stuck because we've hit the end, basically, and we've crossed over, if that makes sense. Our start has eclipsed our end, and it's stuck that way. We're going to continually set this to be 8, the start will be 8, the middle will be 7, and it just keeps going over and over and over. So we want to stop. We want to make sure this loop only runs while our start is less than or equal to the end. So as soon as the start becomes greater or the end becomes less than, we have a problem. So just in here, I'm going to do and then we just check start is less than or equal to end, just like that. Okay, so we're close now, and if I run this time, we still have a problem, which is that we're returning the middle even if we don't find it. So now we don't loop forever, but it's returning index of 7 because that's where we stopped, right? That's our last point right here. So index of 7, but that doesn't work because 50 clearly is not at index of 7. So now we just need to add a little check at the end. We want to check basically if array of middle is equal to what we're looking for. Oops. Like that. If it is, then we return middle. Else, what do we want to return? We'll return -1, I think is what we said, right? Yes, it is. Does that make sense? So we're checking if the array middle, the item at the middle index is what we're looking for. Should do triple equals. We'll return middle, otherwise return -1. So now we get -1. But if we search for 5, it gives us 1. If we search for 9, it gives us 3. If we search for -1, we get -1. -10, still -1. Okay, so a couple small cleanup things we could do if we wanted to. We can, well, first get rid of the console.logs. We don't need that. Next, we can condense some of these conditional statements. So I'm going to duplicate the solution because some people like to have the longer version, but I will also do a shorter version where we get rid of basically a lot of white space like this. So do a single line if statement, and then our else doesn't need brackets either. So there's one reduction of a couple lines, and then we can also put all of this on a single line using the ternary operator. So that looks like this, or one possible, there's two implementations. So you can just do return array middle equals element. If that's true, so we need this question mark, we're going to return middle, colon, else return -1. If you haven't seen that syntax, the way you would read this is return the result of this whole thing, first of all. And the result is going to depend on if array of middle is equal to the element. So if array of middle is equal to element, return middle. Else, return -1. So just test it out again. It looks like it's working. Let's plug in a number that is in there, like 30, and we get index of 7. If we plug in 13, we get index of 4. If we plug in 103, we get -1. Okay, so that's our shorter solution. All that we did, the logic's the same. We just got rid of some of the extra brackets and the longer if statements. So we made it through there. Hopefully it makes sense how this all works. And now we're moving on to a couple other searching algorithms. So keep in mind this works great on a sorted array, otherwise it's useless. So linear is the best that we can do. What we saw a couple videos ago is the best we can do on an unsorted array. Binary though works great if our data is sorted. All right, welcome back. So I'd like to talk about the time complexity for binary search, how it performs, let's just say, on an array. So as the length of the array grows, a sorted array, of course, how does the time complexity grow in relation? And you can see here on the left, worst and average case are O of log n. And I'll come back to that and why that is. Best case, of course, is O of 1, because it's possible that the very first thing we pick is the element we're looking for. If we pick the middle point of an array, and that's what we want, well, that's one operation, it's constant time O of 1. That's pretty rare, but it's possible. Worst and average case are both O of log n, and I have a couple slides to detail how we get log n. If you're not familiar with logarithms and how this applies to big O, I have a quick video. I think it's the last video of the big O section. I definitely recommend you watch it if you're not sure about logarithms, if you were taught them a long time ago and you forgot them, or if you were never taught them. It's a quick video. So suppose we're searching for the number 13 in this array. How many steps does it take? Well, we actually can see 13 is not in here as a human. It should be right here if it were to be in this array. But the first step is to pick a midpoint. And I know this looks like it's not the middle, but these are all double-digit numbers over here, so it's kind of skewed. But this is the midpoint. So we pick 19, and we check, is 13 less than or greater than 19? It's less than, so we know it's somewhere over here if it's going to be in here. So then that's what this array is representing. We're not actually shrinking the array down. We're just looking at this portion of the larger array. So then we pick a midpoint again, which is 9. Well, 13, is that less than or greater than? It's greater than 9. So we're now looking at this subarray, 11, 14, 15. So we pick the midpoint 14. Is 13 less than or greater than? It is less than. So we're looking at this subarray now, 11. So we check, Is 13 equal to 11? The answer is no, of course. And so we know that 13 is not in this array, unless it's somehow an unsorted array, in which case we shouldn't be using binary search. But given the conditions of binary search, we can say without a doubt 13 is not in this array. Nope, not here. So if we look at the number of steps here, we had 16 elements. It took 4 steps to say with certainty that an element is not in there. So we could have found it earlier if it actually was in this array. If we were looking for 9, for example, it takes 2 steps. If we're looking for 14, it would take 3 steps. But if we're looking for something that's not in there, or the very worst case, it took 4 steps. Now, 16 elements, 4 steps. Let's grow our array. Let's double it in size. So instead of 16, I'm adding 16 more elements. So we have 32 elements in our array. It looks like this. And let's say I'm looking for the number 32. How many steps will it take? Well, in the first step, we pick a midpoint. This is not counting as a step. This is just our starting array. I pick the midpoint, which is 16. And we test, is 32 greater than or less than 16? It's greater than. So we can ignore all of this. There we go. This slide took a long time to make. So now we're looking at this part of the array. And we pick a midpoint, which is 24. And we compare 32. Well, 32 is greater, so we can ignore all of this. Next, we're looking at this portion. And we pick a midpoint again. 32 is greater than 28, so we ignore all of this. Skip. Now we're looking at 30. Well, we're looking at this portion, and we pick a midpoint, which is 30, and 32 is greater than 30, so we ignore this portion. Finally, we pick our midpoint again, and we find 32. We're good to go, and that took 5 steps. 1 step, 2, 3, it's highlighting the wrong thing. 1, 2, 3, 4, 5, until we found it. So we doubled the number of elements from the previous slide. We had 16 elements, which was 4 steps to find, or actually we didn't find the element, but it took maximum 4 steps. Here, we doubled it to 32 elements, and it took a maximum of 5 steps to find our element. So that relationship is log base 2 of n. So log base 2, which we simplified to log n, basically means 2 to what power gives us n. So if we go all the way back here, 16 elements. What is log base 2 of 16? It is 4, because 2 to the 4th power gives us 16. 2 times 2 times 2 times 2. Or here, it was log base 2 of 32 elements. If n is 32, that means 5. 2 times 2 times 2 times 2 times 2. So every time we double the size of n, every time we double it, we are simply adding 1 extra step. So log n is really good. If we look at the big O complexity cheat sheet little graph here, you can see log n is all the way down here. It's really good. It's so good, in fact, they don't even put a separate line in here. So there's the O of n line, our linear big O. And then down here, they put constant and log n together, because in the grand scheme of things, when you zoom out far enough so that you're looking at something that also includes factorial, O of log n is so much better that it just looks like O of 1. Anyway, so log n is really good. Binary search is very fast. Of course, the caveat is that it only works on a sorted array, and if you don't have sorted data, then you're out of luck, and you've got to use linear search, which is not anywhere near as good. Going forward, we actually will see a couple other algorithms when we talk about things like binary trees and graphs, where the big O notation for time complexity includes log n again, or also n log n. So if you're not comfortable with logs yet, I really recommend you watch that video, but also give it some time. I think we have a couple sections before we encounter log n again, but soon we will. Hey, welcome back. So we're still talking about searching algorithms, but now we're talking about a different type, which has to do with searching for substrings in a larger string. So there are 2 that we're going to focus on, and the first one is the naive string search. I don't think there's actually a name for this. This is just the most basic, common way of doing this problem, and then we're going to see a better implementation that is definitely a little more complicated in the next 2 videos from now. But we're going to start with the basic solution. So imagine that you want to count the number of times a smaller string appears in a longer string. A straightforward approach involves checking pairs of characters individually. So imagine we have this string here. Harold said, haha, in Hamburg. So if we were searching for just a single character, like I don't know, the letter I, for example, that's very easy. That's basically what we've done. You just do a linear search. You could treat this as an array, right? You just check, is this an I? Nope. Is this an I? Is this an I? Is this an I? Over and over until you find an I or until you hit the end. So that's nothing new. If we're searching for a single character, we can use what we've already done. Instead of accessing items in an array, we access using an index in the string, just like this, right? 0, and then we check 1, and then we check 2. But if we're checking for a pattern, for example, I want to see if HA, haha, is in there. That takes some more work because we're no longer just checking a single character against a single character. We're checking, okay, let's walk through the string, and it looks like we have an H, so that's a match, and then we have an A, oh, that's a match, and then an R, oh, not a match anymore. So then we start over, and we look for an H again. So I actually have a little diagram here. Imagine that this is our long string we're searching through, and we're trying to find OMG inside of this. So the simplest approach is going to involve, basically, if we put them next to one another, we're going to start by walking one character at a time. And we're just going to check, is this W here equal to the O at the beginning? Are these two characters the same? No. Okay, move on. Now we have a match. O is O. So now we move on to the second character. We're looking for an M. We don't find one. So we move on. W and O, we don't find that, so we move on again. Okay, O and O, that's a match. Now we move on to the next character, M and M. That's good. G and G, and we hit the end of our short string. We found a match. So now we add a count, or we increment something to keep track of how many matches we found. We found 1 so far. Now we move on to the M. So basically we do it for every single character here. And we start at the beginning of our smaller string and check it against every individual character in the longer string. So that's not a match, that's not a match, that's not a match. Now we have a match at the O, so then we check the next character, M. We check, there's still a match, G, and we increment. I don't know why this, when I made this slide, I just checked, these are the same size. Somehow there's some weird bug when it's being displayed. But these should count evenly. There's 2 matches. And that's what we want to do. We want to try and implement this naive string search. So there is a better way of doing this, but it involves a lot more code that we'll see in 2 videos from now. And it has a much fancier name. But this approach is one that it just takes a couple lines, a couple loops. Let's walk through the pseudocode. So the idea, again, is for you to try and implement this on your own using the pseudocode if you have the time or willpower or energy. Here's the steps. So loop over the longer string. So I guess I didn't say define a function this time, but define a function that takes 2 strings and just call it maybe string search. It takes the larger string and then the pattern that we're looking for. And then you loop over each character in the longer string, and then we have another loop over the shorter string. And then we just check, basically, if the characters don't match, break out of the inner loop, so stop. And if they do match, if we find a match for O, for example, in OMG, then you move on to the next character. Keep going until you hit the end of the short string. And if you do hit the end of that short string, that means that you found a match. So if you complete the inner loop, find a match, increment the count of matches, and then return the count at the end. And so if count should start at 0, we don't need to have any special error handling. If there are no matches, count stays at 0. So just return the count at the end. So hopefully that makes sense. Loop over the longer string, inside of that loop, a nested loop over the shorter string. And then if you make it to the end of that shorter string and you haven't broken out yet, then add 1 to the counter. Okay, so give it a shot. In the next video, we'll have a solution. All right, welcome back. So in this video, we'll go ahead and implement the naive string search algorithm. So I already have a snippet created. Do this wherever you prefer, Sublime, some text editor, as a snippet yourself. It doesn't matter. So I have one called search naive string, and I'll close that for now. First, let's just define the function. So it needs to accept 2 strings. So I'm going to call it naive search, and it accepts the long string and a short string, or long and pattern. I've also seen that, or pattern like that. I like short though. And then the first thing that we'll do is just do a sample call down here. So naive search, and let's say, for example, that we would be calling it with maybe Lori lolled, LOL'd as a verb, and we're searching for LOL in that string. Okay, so first of all, we're going to need to get some loops going, as the pseudocode mentions. Loop over the longer string, and then nested inside, loop over the shorter string. So let's just start with the most basic loop over the long string. So for var I equals 0, while I is less than long.length, I plus plus. So that should give us every I, if we just look at it. I'll execute this, make our console a bit bigger. Come on. All right, so we get 0 to 10. There's 11 characters in there. Then let's do the same thing, this time for J, or whatever letter you prefer, but J is the standard one, H-I-J-K, yes, yeah. Okay, for var J equals 0, J this time is less than short.length, J plus plus. It gets a little confusing once you start working with I and J, keeping track of which one is which. So if we just printed out I comma J each time through, those are going to be numbers. So why don't we do instead, let's do long of I, so we see which character we'd be referencing, and short of J. Now we're going to get a lot of prints. This is a nested loop, so we're looping 10 times here, but each of those 10 times we're looping 3 times for the LOL. So if I clear this out, I'll make this larger and try it again. All right, so you can see what we get here is basically we start with L on both of them, L and L. And then the inner loop goes to O. So we have L and O, and then L and L again. And then we move to O, and we start over, O and L, O and O, O and L. Okay, so what do we actually want to do rather than just printing them out? Well, the first thing that we can do, let's forget the fact that I and J are numbers. And let's just say that they're the letters exactly. It's a little easier to talk about. So let's say that I starts as L, and J also starts as L. So remember that I is our outer loop. So I is going to stay L as we progress through LOL, if that makes sense. As J increases, it has to increase 3 times and then reset in order for I to increase once. So we start the loop, I is L, J is L. We compare them, looks good. Whenever there isn't a match, we break out of this inner loop and we move on to the next iteration. But let's just focus on, in this case, there is a match, L and L. So what do we do next? Well, the next comparison is still going to be L, but it's going to be compared to O, because we're moving, basically J moves on and it becomes O, because we're looping through this first. But that's not going to work to directly compare O and L, because we know that's not a match. So what we want to compare it to is one more than L. So as we move through J, we want to also look ahead in I, even though I is going to be stuck at 0, if that makes sense. As we look through this, as our short pattern, LOL, continues to loop, we're still comparing to L each time. So instead, we want to look ahead. And the best way to do that, or one way at least that I'm going to do it, is by adding I to J. It's kind of confusing. But now if we go back to numbers, and we say they both start at 0. Okay, so there's a match. Now, J goes up to 1. So we're going to compare LOL of 1, which is O, to this string, Lori lolled, but instead of 0, we're going to add them together. So where we were before, plus where we are now in J, which means that we're going to look ahead to O, because that would be index of 1. And so that's a match. Next time through our short string, we're at index of 2. So we're going to compare this L, and we are going to add 0 plus 2 to give us index of 2 of this string, looking ahead, and it's not a match. So then we break out. That means that we start again at L. But then once we get up to here, which is what? Index of 0, 1, 2, 3, 4, 5, index of 6. So in the scenario where we are here, index of 6 in the large string, index of 0 in the short string, there's a match, right? Those are matches. So then we move on. In the short string, J goes up by 1, and it now becomes 1. But we don't want to compare Lori lolled of index 6. We want Lori lolled of index 7. We add them together. So hopefully you can see the approach. We're looking ahead. And to do that, it's not too bad. All we do is add I and J together and access, using that new index, access the long string. So here's my approach. Instead of console.logging, we'll just basically check if the short string of J is not equal to the long string of I plus j. Now, if that happens, then we'll break out. So let's make this a loop. I mean, a conditional. Like this. So this means break out of this short loop and start on j again at 0. So anytime there isn't a match, we're going to break. So if I add this console.log in there now, where I'm printing short j and long I plus j, I'm going to clear out like this, and let's see what we get. Okay, so our comparisons, we start with L and L. That makes sense. There's a match. So we don't break out, and we move on to O, and we compare O to the next character, which is O. And then there's a match. So we move on again to L, and we compare it to R, in which case there wasn't a match. So if I added in a console.log here to say break and reran this, you can see what happens. So it looks like there's a match, L and L, O and O, and then there isn't a match, so we break. And when we break, what is happening there is that J is being reset. This inner loop is going back to 0, meaning we start at L again. But the outer loop, I, moves on. So now we're starting here at O. So after that break, we do L and O, and that's not a match, so that's a break. So then we move forward again. This time, we're talking about R and L, and that's not a match, so we break. We keep going until finally we get here. And there's a match, so then we move on. And there's another match and another match. But what do we not have right now? We're not actually incrementing any sort of counter when we find a full match. So we found a full match right here, LOL. Those are three pairs that match correctly. So what we need to do is make a variable up here. Let's just call it count equals 0. Now, when should we increment count? Well, the way that we know that we have successfully made it through this string, because if we get to this last character and there's a match, if we've made it to that point, that means that J is going to be whatever the last character in the short string is, if that makes sense. So if we had lolled, L-O-L-E-D, we know that we've finished if J is 0, 1, 2, 3, 4, if J is 4, or in this case, if J is 2, if we've made it to that point. So we can just add a conditional check, just do an if, and then we just check if J is equal to the short string dot length, but -1 because the length is going to be greater than the index. If that's the case, let's add 1. Let's do plus plus like that. And then at the end, let's return count. Let's see, how many braces do I have? So that's conditional loop loop. Okay, here we go. Okay, so let's see what happens now. So why don't I add a console.log in here? Found one. Clear my console, rerun the whole thing. Let's try that again. Okay, so if you see, we have the same exact thing, almost a match, but there's not, so we break, keep going. But then, hooray, we found a match, and so this code is printing. So count is going up by 1. So if you get this, if it works for you, or if you had a slightly different solution, but it's working, that's all that matters. If you have 2 loops and you're getting it to work, your logic can be slightly different. You could work from the end, for example. You don't have to work from the beginning forward. You could work backwards. That doesn't really matter. But if you have it working, great. If you want, you can stick around and we can walk through this one more time just to see exactly how it works. I'm going to shorten this up because, like some of the other solutions, we can put these on single lines, make it a little nicer, like that. Same thing with our second if. Move that up here, just like that. And it still works. Should still work at least. We're getting it results printed. Come back, console. Yes, we're getting 1. Cool. All right, so if you want to stick around for the extra walkthrough, let's try it one more time with something different. Let's try it with LO, which in this case, we should get 2 matches. Is that working? Yes, we get 2. All right, so what's happening here? Well, we loop through every character. For example, L is where we start. And on the second string, we loop through every character. So we start at L. And immediately we check if this character doesn't match I plus J of this character. So I and J are both 0. So this means we're checking the first characters together. 0 plus 0 is 0. So if they don't match, immediately break out, and that means that we move on and that I is now right here. So if they do match though, which they happen to match, what do we do? Well, since we're still in this loop, we move on. J is now pointing to this, but I is still here. So now we add those two together. J is now 1, I is still 0, so that gives us a total of 1. And we compare this to that, and there's a match, at which point we increment count, because J is equal to the length of the short string. That's how we know we're on the last iteration. J, in this case, would be equal to 1, 0, 1. When we get to 1, and we haven't broken out yet, if we get to this point, that means we found a match. All right, so then it repeats again until it finds this match. So hopefully that's clear. And if we try it with something that isn't in there, like pop, we should just get 0. And we do. So we don't have to account for anything because we have this count variable. It's unlike binary search, for example, where we had to handle errors, not errors, but we had to handle those edge cases. If we don't find anything, we count 0. All right, so that is an implementation of naive string searching. Next, we're going to see a better implementation of a different sort of string search algorithm. Definitely a little more complicated and longer, but it'll be fun to talk about, I think. Hey, welcome back. So this is the first of a couple sections on a somewhat notorious topic, which is sorting and sorting algorithms. So when I get to this point in my in-person classes, I think this is a topic that a lot of people have been dreading. Some people look forward to it, but it's something that has taken on a bit of weight in the developer, zeitgeist. It's a heavy topic to people, and it's something that is important. And part of the reason, I think, is that it's sort of like the quintessential computer science topic that every blog post ever about getting your dream job at Google, here are 10 things you must master, or every book about acing the computer science interview, there's always a large section devoted to sorting. And for good reason. It is an important topic. It's a great challenge and something that we do all the time, whether we're writing our own code or using a built-in sort method. It's important, but it also doesn't have to be that scary. So let's start by just talking about what sorting is referring to. When we say a sorting algorithm, it's referring to the process of rearranging items in any collection. So we could take a string and sort the individual characters inside a sentence, for example. But we're going to usually be working with arrays, at least for now. Later, we'll talk about sorting other data structures like linked lists or trees, but for now we're focusing on an array. So let's say we have an array of data. We want to write a function that takes that array in and spits out a reordered array. So that could be sorting numbers from smallest to largest, or the other way around, ascending or descending. It could be sorting names alphabetically. Or if we have movie data, let's say objects, movie objects, each movie has a year, a total revenue, it has a director, a title. We could sort them by release year, or we could sort them by revenue. Or we could take their international and domestic revenue, add those together, and then sort by that. So the point is that it doesn't really matter what we're sorting by, what the comparison is, whether it's alphabetically what comes first or numerically what comes first, that doesn't matter. The algorithms behind it don't really care. We're going to focus on working with arrays for now and just numbers. So imagine that I asked you to write a function called sort, and it just takes in an array, and it should return that array sorted. So if I called it like this, with, let's just say, some random numbers like that, you would need to write code in here in order to make this work so that it should return, let's see, in this case, what are we looking at? 6, 12, 13, 23, and 45 from in ascending order is what we're going to start with. So it's a simple challenge, right? We can look at this. It doesn't seem that bad, but there's a million ways of doing this, and that's part of the problem. Part of what makes sorting algorithms kind of scary is that I can think of 15 probably named algorithms that exist that actually have a name, that are kind of well known, that do the exact same thing. And there are definitely some better ones overall that we will be learning about. Then there are also some that are very niche, that are terrible most of the time, but they do well in certain situations. So just to give you a really quick preview, this is a video I like to show when I'm teaching sorting. We're not going to look at, I'm going to skip around for like 15 seconds, but it visualizes the different approaches to sorting. So basically, Over here, we have some unsorted data representing, let's say, numbers. The taller items, the taller rows or columns are a larger number. Let's say this is 100, the tallest one here, and the smallest one is representing the number 1. So they're all in this order, totally random, and we write code to go and order them. So here's one approach called selection sort, and you can see that it builds up the array one item at a time. It sorts it one thing at a time until we're done. Then here's another approach. It's called insertion sort, and it's a little bit different. We've got quick sort, very different. We're working from the start and the end at the same time. We've got one called merge sort, another approach, heap sort, radix sort. We're not going to learn every single one of these. There's 15 in this video. Shell sort, bubble sort. But the point is that these are all different approaches. They all end up with the exact same They end up with the same results, but how they get there is very different. So this video is kind of fun to take a look at. I will warn you, the sound is a little bit obnoxious. I'm not playing it here, but definitely don't play it on high volume if you're going to check this video out. So why do we need to learn this? That's the next question. So there are all these different algorithms, and we're going to learn a bunch of them. But why? The first is that sorting is something that is really, really common in programming. And even if you are using the built-in JavaScript sort or the built-in sort method in Ruby or in Python, for example, it still is important to understand what algorithm it's using behind the scenes, because that will help us understand what it's good at and what it's bad at. And that brings us to the next point, which is there are many ways of sorting things, and each algorithm that we see will have pros and cons. So while some are objectively faster than others, there are certain situations where one algorithm, let's say that the data is almost sorted and there's just a couple pieces that are out of place. Some algorithms that are usually slow will be really fast at that. So if you know, for example, that you're working with data that is pretty uniform and it's almost all sorted, but there's a couple things that are out of place, and you want to make sure that it's being sorted as fast as possible, you might want to implement your own sort rather than having to rely on the built-in one, which isn't going to be as fast in that situation. And just to illustrate my point, this is a really cool website I like to show called Sorting Algorithms Animations, and it shows 7 of the most common sorting algorithms: insertion, selection, bubble, shell, merge, heap, and quick sort. These are all different approaches. And what it's showing here are different data sets. So a totally random set of data versus nearly sorted. So you can see we're almost there, but there's a couple items out of place. Totally reversed data, and then data that has few unique items, so a lot of very similar items. Now what I'm going to show you is, first of all, what this does is it just visualizes what happens, just like the video I showed you in the past, but this compares them all at once. So if I hit play on random, you can see basically how their speeds compare. Whoops, I missed it. There we go. How their speeds compare and their approaches compare. So this is totally random data, and you'll see things like heap, quick, merge, and shell finish much before insertion, selection, and bubble, and poor selection just finished. But then if we look at nearly sorted, you'll see that insertion actually finished. I'm pretty sure it finished first, didn't it? Yep, it's done before anything else. Poor selection, still very slow. And I won't go through all of these, but you can feel free to play around with this. But all that this is showing is that something like insertion, which was slow when our data is totally random, was actually very quick when our data was nearly sorted. I think it was the first one to finish. So they have pros and cons, and it's worth understanding them. And the other reason I didn't put on here that we already hinted at, this is a classic interview topic. It's something that it's a great, it's just a good problem. There's so many approaches. It's really a good critical thinking challenge. I can't believe I'm using that phrase. I sound like my dad. It's a good challenge to do. And it's something that comes up in interviews. So of course, that's a good reason to know something if you're trying to interview. So without further ado, let's talk about what we're covering in this section. Our objectives are, first, we're going to implement bubble sort. So this is one algorithm. We'll learn how it works and implement it. Same thing for selection sort and then insertion sort. So these are what I'm calling the elementary sorting algorithms. They definitely are less commonly used because they're less efficient. But that doesn't mean that you shouldn't learn them. And we'll talk more about why it's important, but I kind of already hinted at it. We saw that at least one of the algorithms performed very well in a certain, very specific situation. So we'll be able to analyze these as we go through and figure out when they perform well. And then after this, we will move on to more advanced sorting algorithms as well. So let's start First, before we even get to bubble, we're going to talk about the built-in JavaScript sort, the sort method, and just learn how that works. Hey, this video will be super quick. We're just going to talk about the built-in array.sort. So in JavaScript, every array has a built-in way to sort it. Yes, it does. Thank you, slides. But it doesn't always work how you would expect it should. For example, take this array of strings. We sort it, and I think this makes sense. We get the result that you would probably expect. They're sorted alphabetically. So A for algorithms, then C, then D for data structures, and then steal. That makes sense, I think, to go from A down to Z, or up to Z, whatever. We're going from A to Z. Then if we do the same thing with numbers, 6, 4, 15, and 10, and you sort it, what we get doesn't really make sense. So it starts with 10, and then 15, then 4, then 6. So it would be one thing if it was just the opposite order, like if it was descending instead of ascending, greatest to lowest instead of lowest to highest, but it's not even ordered in any discernible way that we can make sense of, no numeric order. What's actually happening is if we read the array sort documentation on MDN, is that, here we go, the default sort order is according to string Unicode code points. So there's this thing called Unicode used to represent strings, and what happens is that every item in that array is converted to a string, and then the Unicode value of that is taken, and then they're sorted. So it's very bizarre, and it's almost never what you want, unless you're working with strings to start, but even then, it's not always what you want. So how does it actually work? How do we use it in the real world? That's only what happens, that's the behavior when you don't pass anything in. You just do .sort with empty parens. But there's this whole other thing we can do, where we can actually specify how it should sort, what property it should sort by, what to compare. So it accepts an optional comparator function, and we can use this to tell JavaScript how we want it to sort. So basically, the structure that we write this function is, it takes two items, which we'll call A and B, and we tell JavaScript the sort order to make based off of what we return. So if we return a negative number, so if we have two elements, again, A and B, JavaScript's going to call this function every time it's comparing two elements. If this function returns a negative number, then JavaScript will decide that A comes before B. If it returns a positive number, then it's the other way around. A comes after B. And if we return 0, JavaScript treats A and B as the same and just sorts them basically together. It doesn't matter. So here's an example. Number compare is what we called our comparator function, and all we're doing is returning num1 minus num2. So JavaScript gets this. Remember, this is what comes first, this is what comes second. If this returns a negative value, then num1 comes first before num2. If it returns a positive value, then num2 comes first and then num1. So when we do this, you can see that it's now sorting things appropriately in ascending numeric order. So we get 4 and then 6 and then 10 and then 15. And I have it over in a snippet here. So if I run it, that's a little big. There we go. So if I run this now, you'll see that we get 4, 6, 10, 15. But if I just change this order, so num2 minus num1, for example, we get 15, 10, 6, and 4. So that's sorting just by numbers, which that's what you would do if you're trying to sort something numerically rather than working, the Unicode characters and worrying about all of that. We could also do something like this to sort by the length of a string. Rather than alphabetically, we want to sort from whatever the shortest string is, so colt, up until the longest string, which would be data structures. So we do the same thing, string1.length minus string2.length. And we call this compare by len, but remember, it doesn't matter what we call this, it's just a random function. But it needs to accept these two arguments, and then we use them in here, and we return a negative number, a positive number, or 0. So what do we get? There we go. And if we swapped it around, change the order, string2.length minus string1.length, now we have the other order. So this is how we can define our own basic sorts using the built-in JavaScript sort method. Now I just showed that to you so that you know that it exists and it's an option. Now what we'll focus on in the rest of this section is writing our own sorting algorithms that actually do the comparisons. That's the hard part. And so that's coming up next. We're going to kick it off with a fan favorite. It's not a fan favorite, but it has a fun name, bubble sort. See you in the next video. Hey, welcome back. So the first of the sorting algorithms that we're going to take a look at is called bubble sort. So bubble sort is not all that efficient. It's not that commonly used. There is one use case we'll discuss where it does excel, but generally we're not learning it because it's going to be, it's not going to rock your world. You're not going to be implementing it all the time. Although it is a very good problem. It's a fun one if you know how to do it, and there's some optimizations we can make. So it's a good thing to talk about, and it also helps us understand why other algorithms improve upon it. So don't skip it, please. Okay, now that I've made it sound terrible, let's talk about why it's called bubble sort. So the idea is that if we have an array and we're sorting from smallest to greatest, so in ascending numeric order, the larger values will bubble to the top one at a time. So what I'm going to introduce now is something that we haven't seen up until now, I think. It's called visual. Well, I actually don't know how. I use this all the time in my classes. Visual algo. It's a combination of visual and algo for algorithm. So I like visual go, but the way it's highlighted, it makes me question my pronunciation. So what it is a really cool interactive tool in the browser that lets you step through sorting algorithms, among other things. I'm currently looking at bubble sort, and you can see that we have some data. If you open this up, by the way, your data set will look different. I input these numbers specifically. I didn't want to have a massive data set that took me like 10 minutes to step through. So we have 1, 2, 3, 4, 5, 6, 7 elements ranging from 10 up to 37. Okay, so this is our array. This is the first item and this is the last item. The way that bubble sort works is that as we loop through each item, we compare it to the next item, the one in front of it. And we check, is this one larger than what we're comparing it to? And if it is, we swap. So swapping is really important to bubble sort. It's how it works. You basically swap if something is larger, and then you compare it to the next one. Is it larger? Swap again. Compare it to the next one. So let's just step through that. So 29 and 10, we swap because 29 is larger. 29 and 14, that's the next comparison. We swap. Now we compare 29 and 30. This time, we don't swap. So now we have 30 and 37. 30 is not larger than 37, so once again, we don't swap. Now we compare 37 and 14, and now we do swap. Now we're on to 37 and 18. Compare the two, and we swap. So that was our first pass all the way through the array. And what happened is that the largest value bubbled to the top. I've also heard this as sinking sort, where the largest values sink to the end, to the bottom. I think that's a little more pessimistic. Bubble, it's so much happier. Who doesn't like bubbles? So now we repeat the process. I won't make you watch every single step of this, but we start again at the beginning. So we compare 10 and 14. We don't swap. We compare 14 and 29. Again, we don't swap. We compare 29 and 30. We don't swap. Now we compare 30 and 14, and we do. Next, we compare 30 and 18. Once again, we swap. So now we have the last two values cemented in place, right? 30 and 37, those are sorted. So we're building this list as the values bubble up to the top or to the end, the largest values. We know that those last two items are now sorted. Those don't need to change. And on we go very quickly. We go through this, we swap, 29 bubbles to the top, and eventually we end up with this sorted array. So on the slides, I have a simple walkthrough of one of those iterations. So if this is our array, we swap. If we compare 5 and 3, we swap. So 5 moves up. Next, we compare 5 and 4. We swap again. Next, 5 and 1. We swap again. And finally, we compare 5 and 2, and we swap because 5 is the largest element in the array, and it ends up at the end. So that's for one single iteration. Then all we need to do is repeat that over and over. And you could start by repeating once for every item in the array, but remember that as we go through, the amount of items we need to sort decreases because we started out with 1, 2, 3, 4, 5 elements that were unsorted. Now we have 4 unsorted elements and 1 solidified sorted element. So that means that we have fewer elements to sort as we go through. So our loops can reflect that. But first, let's talk about swapping. Since that's such a crucial part, we have to swap. How does that work? Well, in JavaScript, there's a couple ways of swapping. I have two listed here. This is honestly my preference. It's not the newer way of doing it, but this is how the tried and true way of swapping values. I think it's kind of more legible, easier to understand. You don't even have to make a separate function to do this, of course. But here what we have is an array and then the two indices that we want to swap. And we set up a temp variable to store one of them. And then, so if that's the first one, index of 1, we set up a temp variable and save that to that value. Then we change what was in array of index 1 to now be what's in array of index 2. And then lastly, we use that temp variable to update array of index 2. So that's how I like to do it. But there's also in ES 2015 this syntax for doing it, which I don't know. I just don't think it's very readable personally. But the syntax basically is take the whatever's in index 1 and swap it with index 2. Take what's in index 2, swap it with index 1. And this works. And it is a single line. So for those of you who are file size queens, who care about how short your files are, you can use this. I'll probably use both. But it helps to define a function called swap because then our bubble sort code becomes even shorter. The actual logic really is just about the comparisons in the loops, and then we can just call swap. But you don't have to define a separate function. If you want to implement it, which I highly recommend you give it a shot, here are some of the steps. Start looping. So define a function, I didn't add that in, called bubble sort. It takes an array, and you can assume it's all numbers. Start looping with a variable called I at the end of the array towards the beginning. And we'll discuss exactly why, but it has to do with the fact that we're shrinking down the amount of space that we're sorting. Then an inner loop inside of that outer loop with a variable called j from the beginning until I minus 1. So I is referring to the first loop. So we have a nested loop that is depending on the first loop, I minus 1. And then we just compare array of j, so that's going to be our individual, if I went back here, let's say we're comparing, if j is 0, we're going to compare it to array of j plus 1, which is the next item. So whatever j is, we're going to compare the item ahead of it. So j and j plus 1. Okay? So if array j is greater than array of j plus 1, that means you need to swap. And you can swap however you'd like using whichever version that I showed you. And then at the end, just return the sorted array after the loops are done. So give it a shot if you'd like. And in the next video, we'll have an implementation. All right, let's do this. Let's get implementing bubble sort. So I had pretty specific instructions here. Start looping. Oh, I just realized this is a bit of a typo. Sorry about that. Start looping from the end of the array towards the beginning with a variable called I. What I'm actually going to do is show you the dumber, I shouldn't say dumb, the less optimized version that doesn't follow these instructions, which just uses two nested loops that go from the beginning to the end of the array, the entire way. So that would look something like this. I'll define my function. I'll call it bubble sort. I made a new snippet, by the way. It accepts an array. And we know at the end it's going to return that array. And let's say I'm going to call it with a super simple array like 37, 45. I have such a tendency to pick odd numbers like this. It's not on purpose. Okay, we'll put 8 in there. Okay, so this is what we start with. And we're going to loop over every item in the array. So for var I equals 0. And I'm going to do, like I said, just starting from the beginning. So 0 up until, or less than array.length, I++. So that's going to give us a single pass, right? If this is only going to loop, 4 times. So we'll start with I at 0 and it ends at I at 3. So that gets us enough to sort one item. So we could compare and do our swaps. And at the end of this loop, if we did swap things, we would have 45 at the end of the array. But we still have to sort everything else. So we need to repeat that process for every item. Technically, remember, we don't have to do it for every single item every time in that array because as we progress, the end becomes sorted. So if we started with this, the next time through, we would end up with 45 at the end. So then next time, we only need to sort these 3. And if we did that, we end up with 37 bubbling here. And now we only need to sort these 2. But for our naive solution, let's just have the code go all the way to the end every single time. So for that, we just need another loop. So call it j equals 0, while j is less than array.length, j++. And now we have j, so j is going to be 0 starting at the beginning, and we want to compare whatever item we're looking at with j to the one in front of it. So j and j plus 1. So that just looks like this. Array of j, comma, array, well, no comma. Ignore that. We want to check if it's greater. So if array of j is greater than the one in front of it, swap. So let's write that logic now. Now, as far as swapping, I'm going to start with the basic swap, the tried and true swap, where we make a value, so a variable, I'll call it temp, and set it to one of them. It doesn't matter. I'll set it to array of j. And then we change the value of array of j to be array of j plus 1. Thankfully, we saved the old version in our temp variable. So now we set array of j plus 1 equal to temp. Okay? And that's actually it. This is a working version of bubble sort, but it's just not optimized because of what we talked about. It keeps running over and over. And there's actually another small problem. Let's start by printing out up here, console.log, what the array looks like as we go. All right, let's see if it works. Here's our first pass. We had 37, 45, 29, and 8. We compared the two, 37 and 45. We don't swap. Now we move on. J is incremented by 1. So we compare 45 and 29. And we do swap. You can see that change reflected the next time through. Then we compare 45 and 8. And once again, we swap. And so that's what happens here. 8 and 45. That looks good. We have 45 at the end. But here's the problem. And actually, I've changed my mind a little bit. I think what will even be clearer is if rather than just printing the array, console.log array, if we also print what we're comparing. So I'm going to do array of j and array of j plus 1. So we can see the comparison as it happens. Let me clear my console here. Run it again. Okay, so now you can see we're comparing 37, 45, 45, 29, 45, and 8. But then 45 and undefined. So what happened is that we went too far. J hit the end of this loop at 45. Well, j is equal to 3, index of 3, and we're comparing it to index of 4, which there isn't. So we're comparing 45 and undefined. Now our sort still works, but we're going too long. We don't need to do this. Not to mention the fact that now we know 45 is sorted, so we start over. We compare these two, 37 and 29. That is a swap, right? So we do swap them. Then we have 37 and 8. We swap again. And we should be done with this iteration. We should start over and start sorting this. But instead, we compare 37 and 45. But we know that that's already sorted. 45 isn't moving. Nothing is going to be higher than 45 because of the way bubble sort works. It is cemented in place the first time through. So we have a needless comparison. And once again, next time through, you'll see we do the same thing, 37 and 45. There's no reason. So what we want to do is basically at the beginning, we want to make 3 comparisons. So there's 4 items in this array. We want to have 3 comparisons, 1, 2, 1, 2, 3. And then we should start over and next time only make 2 comparisons. This comparison right here, 37 and 29, and then 37 and 8. And then next time through, we should make 1 comparison. Does that make sense? We want to shrink the number of comparisons we're making because we're sorting the array as we go. So the solution to that, if we come in and make a couple of edits, the first is that I'm actually going to change the way this loop is set up. I'm now going to follow the pseudocode I set up. We're going to start with the variable I that goes from the end of the array towards the beginning. So that looks like this. Set I to be array.length, and we go while I is greater than 0. I minus minus. The reason we do this is so that we can use I in the definition of the loop for j. So j now runs while less than I dot, or I minus 1. What am I saying? Dot. I minus 1. Okay, so at the very beginning, our array length is 4. Well, it's always 4, but I starts at 4. So then this loop, the inner loop, we're going to compare j is less than 4 minus 1. So 3 comparisons. This gives us 3 comparisons the first time through. Because I is 4, that means j goes 4 minus 1, 3. Next time through, I has gone down, I minus minus. So we end up with I equal to 3. So then we have j less than 3 minus 1. So that means 2. This loop will run while j is less than 2. So as I goes down, so does j. So we end up running the loop fewer times each time through. So if I save this, get rid of that extra x, rerun it. Let me clear the console now. Now let's look at the comparisons that are made. So we do 37 and 45. That makes sense. Then 45 and 29. And then our final comparison on this first time through, 45 and 8. And we end up with the first time through 45 is at the end. Then we start over. We're no longer sorting undefined and 45 because of this -1. So then next time through, we do 2 comparisons, 37 and 29. So we swap, and then 37 and 8. And we do swap again. And at that point, these two are cemented. So next time through, we only have to do one more comparison. And you can see that 8, 29, we swap them and we're done. So what I could do, let's change this to be 8, 12, 88, 100. No, let's do -3. There we go, negative value. And if we run it now, let's clear the console first. There we go. Let me actually, sorry, this is annoying, but let me make this easier to see. So after that loop finishes, let's do console.log, 1 pass complete, like this. Okay, rerun this. Okay, so now you can see really what happened. The first time through, we did 1, 2, 3, 4, 5, 6 comparisons. Then that was 1 full pass. Next time through, we did 1, 2, 3, 4, 5 comparisons, and then 4 comparisons, and then 3, then 2, and then 1. So this is one version of the solution. Get rid of the console.logs. I also have the ES 2015 version where I decided to, first I used the old version, the new way of swapping things, and I decided to make it into a function. You definitely don't have to do that. I mean, this is only 3 lines, honestly. But if you wanted to, here is the nicer, some people would consider this solution nicer. I used let as well. And otherwise, what else? Big arrow function. Everything is pretty straightforward though. Let's run it and make sure it still works, of course. There we go. -3 up to 88. Okay, so these are 2 working solutions to bubble sort. Hey, welcome back. So we're actually still talking about bubble sort because there's one important optimization we haven't discussed. So there's a very specific scenario where if our data is almost sorted, or if it's already sorted, it doesn't need to be bubble sorted, our bubble sort algorithm as it stands doesn't really treat it any differently. It still tries to sort every single item. So in this scenario where we're almost sorted, if I fast forward through this, okay, maybe this was a bit too long. Okay, we're almost there. Now we're sorted, right? So we get to the end, and as humans, we can see that we're done, but our code is actually going to keep going, and it's going to go to the end. No swaps are made, but then it goes again, and it tries to sort all of these up until here. Then it goes again, tries to sort all of these to here, even though nothing is happening. It's just iterating over. So if we have a super long array, that's going to be a problem because it just takes up a lot of unnecessary time. So we can short circuit our code. All that we have to do is check. Last time through, did we make any swaps? If the answer is no, if we didn't swap anything, that means that we're done. Because if you didn't swap on the last time, you're not going to swap on the next time. So back in our code, what I'll do, I guess I'll make 2 versions. We're getting a lot of solutions going. If we, I guess I'll comment these out for now. I never know what the best way of doing this is because students like to have this different steps as I go, but I also don't like making these super long files because it can scare some people. But what we can do, if we call this right now with a nearly sorted array, like 8, 1, 2, 3, 4, 5, 6, 7, for example. So we're almost there, right? After the first pass, it's going to be sorted. 8 will be to the end. If we take a look right now, how many comparisons we're making roughly, let's run it now. We're making a ton because it was sorted at this point and we kept going without making any swaps a ton of times after that. So what I'll do is I'm going to make a variable. I'll call it no swaps. And no swaps is, if it's true, that means there were no swaps and we're going to break out of the loop. So I could start with that down here, even though it's not defined. I could write if no swaps break. So that would get us out. Of course, we don't have no swaps defined. So up here, I'll do var no swaps like this. And then inside the loop, each time through, I'm going to set it to be true. We'll assume there's no swaps every time through, but then if we make a swap, which is right here, remember, we can set it to be no swaps equals false. Does that make sense? So as we go through, every time at the beginning, so let's say we start with this, no swaps starts at true, and then we make a swap right off the bat. 8 and 1, we swap. So now there's no chance of breaking out this time through. But then we finish the iteration, and 8 is now at the end. You could see, like here, for example. Next time through, no swaps is true, and we never make a swap. This is never true, so we never set it to false, which means we get through all the way to the end one time afterwards. So we sort it all, then we iterate through no swap, no swap, no swap. Then we get done with it, and this is true now, if no swaps, and we break out. So now if we take a look at how many times this prints out with this line, you can see that we basically had to get it to the end, which was right here. This was our first time through. And then we went through one more time and we finished. And then that was it. We didn't keep going. And compare that to the previous versions where we went through, we got 8 to the end, and then we kept sorting over and over and over and over and over, many more passes. In this case, we shortened it significantly. And as the array grows, if it is nearly sorted, that makes a very big difference. Okay, so I just added a little comment. This is our next version that we optimized with the no swaps variable. Just a small change, but it really can save a lot of time. What is the time complexity of bubble sort? Well, in general, it's n squared because we have a nested loop and we're roughly making a comparison for each item in that array. We are making n number of comparisons. In order to get 8 to the end, we had to compare 8 to every single other item in the array. However, if the data is nearly sorted or already sorted, then with this new version with no swaps, it's more like linear time. That's the best case possible, O of n. There's 8 items we go through. I mean, technically in our example, it was 2n because we went through the first time and then we went through again to make sure nothing was swapped, and then we broke out of the loop. So, but that rounds down, or I shouldn't say round, that simplifies down to O of n. So that's the best case, but that doesn't mean that we should be using bubble sort unless you do know that your data is very nearly sorted. It's a good candidate, possibly. We'll also see another good candidate in a little bit. This is more just to show an optimization. This is a classic optimization to make. And yeah, I think we'll end this video here. So we have this version, which doesn't use the fancy swap syntax. Then we have this version that does, using let as well. It's the ES 2015 syntax. And then down here, we have a version where I added the no swaps variable in to short circuit if we don't make any swaps. That is bubble sort. It's a lot, I know. Now we have another sorting algorithm coming up next. Hey, welcome back. In this video, I'm going to introduce selection sort, our next sorting algorithm. So I wrote down that it's similar to bubble sort, but instead of first placing the large values into sorted position at the end of the array, we place small values into sorted position one at a time. So we're building the array, we're still moving from the beginning to the end, but the actual sorted data is accumulating at the beginning. So let me give you an example of how it works. We go through, here's a single pass. So we have this array. We start at the beginning, and what we're gonna do is go all the way through looking for the minimum value, and then we're gonna put that at the front. So for example, we start with 5 and 3. Which one is the smallest? Well, 3. So 3 is going to be our minimum for now, which is what the green means. But then we now compare it to 4. Which one is the minimum? It's still 3. So now we compare it to 1. Which one is the minimum? Well, now it's 1. So you can see 1 is green now. So that's our new min. Now we compare 1 and 2. Which one is the minimum? 1 is. So what we do, now that we've hit the end, is we swap. We take whatever the minimum element was with whatever we started with. And so now we've put the smallest item in the array at the beginning, compared to bubble sort, where we go through and we swap potentially to push the largest element, the greatest value, to the very end. Selection sort builds it the other way. We find the minimum, swap at the end, and put it at the beginning. So let's walk through on Visual Go, however you say this. Visual algorithms, and I have a small data set here. If we step through, we start at the very beginning. This is our first position, and we set a minimum value, to be 19. So that's the smallest value we've seen so far. Next, we compare it to the value next to it, 44. Is there a new minimum? Nope, 19 is still our minimum. Now we move on and compare it to 38. Is there a new minimum? No, 19 is still the smallest. Now we get to 5, and we compare them. 5 is now the new minimum. So that's our new min. We move on, we compare it to 47. Nope, 5 is still smaller. Same thing with 15. We've now hit the end. We know that the smallest element in there is 5. So what we do, we started here. So we now swap the smallest element. As you can see, we have the two things selected, the beginning where we started and the smallest element, and we swap them. And now we start over, but this time we start from 44. So I think that's just showing us that this part is now sorted. We don't have to care about it. So we move on. 44, we compare, okay, the minimum now is 38. Now the minimum is going to be 19. Now it's still 19. Now it's 15. So the new min is 15. So we swap it with 44. There we go. Okay, so now the first two things are sorted. Now we move on. 38 and 19. 19 is the min. 19 and 47. 19 is still smallest. 19 is still smallest. We swap 19 and 38. All right, so hopefully you get the idea from here. We keep going, find a min in that place. In that example, the min was what we started with, 38. Now we just have to swap the last two, and we're done. So that's selection sort. We are going through and selecting the smallest element, the minimum, and then putting it at the beginning. Oh, and actually this hasn't finished officially. There we go. Now it's done. We have a sorted array. So as far as the code for selection sort, it's actually not that bad. We reuse the swap code. So if you made a function for swapping in the last video in bubble sort, or you want to use the one that I made, then we don't have to worry about the swap logic. So let's walk through some of the pseudocode. Okay, so the first thing you want to do is make a variable to store the minimum value. And at the beginning, you can set that equal to just the first item. You have to start somewhere. So the first thing in the array is our smallest value. It's the only thing we've seen. Then what we do is we go through and we compare it to the next item. If that next item is smaller, now we update the value of the minimum variable to be that next item. And if it's not smaller, we keep going. And if we at any point find a new smaller value, we save that to the minimum. Now, what are we actually saving? Well, we're not actually saving the value itself. What we're going to save is the index of where that value is found. So then we can swap. So we don't care if the value is 20. We want to know where it is, index of 3. So then we can swap index of 0 and index of 3 after our first pass. So that's what we have here. If a smaller number is found, designate that smaller number to be the new minimum and continue until the end of the array. If the minimum is not the value, the index, which is why I put that there, you initially began with, then swap the two. Otherwise, if they are the same, it means that we happen to have an array where the first element was the smallest element. We just got lucky. Or maybe it's already sorted, which that's not going to be good for selection sort. And then we just repeat this process. Of course, next time, we know that the first item is already sorted, so we don't need to loop over every single item. What we want to do actually is start from the next item afterwards and find the new minimum. Otherwise, if we kept looking at the whole array every time, we would always find the same minimum, right? If we just started from here again, this is our min, and we compare, our min is still going to be 1. And if we started again, it's always going to be 1. So what we need to do is then look at this area and find the min, and then look at this, and so on. So we want to shrink the scope, our window of what we're comparing as we loop through. Okay, so give this a shot if you'd like to. It's a relatively short one to implement as well. Really, it's just a loop plus another loop and a single conditional, and then at the end a swap. So give it a shot, but also don't feel bad. I don't want to make it sound so easy. It still conceptually can be tricky to get these to work. So in the next video, I will implement it, and we'll see how it goes. Okay, so let's try writing our own selection sort. So I have another snippet called sorting selection, and I'm going to start by just defining a function. I'll call it selection sort, and it takes an array. And at the end, we're going to return that array. So let's say we want to call it on the array, I'm going to do even numbers this time, 10, and I'll add a single odd number at the end there, and 17. Okay. So this is what we're going to test it out with. So what we want to do to start is we can just start by looping over every item. That's a pretty standard place to start. So for var I equals 0, I less than array.length, I plus plus. Okay, and if we look at our pseudocode, store the first element as the smallest value we've seen so far. So let's make a variable, and we'll just call it lowest or min, and we're going to set it equal to I. So that's the position of the smallest element. At least at the beginning, we don't know any better. So this is the smallest thing we've seen. It's the only thing. And what we want to do is compare that to the next item after it, and then the next item after that, and after that, and after that. And if at any point we find a value that's smaller, then we're going to change lowest. So let's do another loop to make that work. Let's go with j, and we're going to set j rather than 0, because remember, we don't want to we don't need to loop over every part. So let me put this in a better way. If we're starting here with our first outer loop, I is referencing here, we don't want to compare it to I again. What we want to compare it to is I plus 1. We want to compare it to this. Or if we're at this point in the array, so if I is now 2, and these two are already sorted, we don't want to start comparing I of 2 to j of 0. We want to compare to 19, which means that we need to go one higher than whatever I is. So we can just do j equals I plus 1, like that. And then we'll do while j is less than array.length, j plus plus. Perfect. And if we just did a simple console.log just to show what we're looking at, let's just do I and j so you can see the comparisons that happen. And we execute this. So no sorting happens, but we start by comparing 0 to 1, 0 to 2, 0 to 3, 0 to 4. Then the next time through, we're going to compare 1 to 2, 1 to 3, and 1 to 4. And then 2 to 3, 2 to 4, and then finally 3 to 4. So this is working. I mean, we're not doing any sorting, but these are the comparisons we want. We don't want to, for example, after our first pass, compare 0 to 1 to 2 to 3 to 4, and then start over and compare 0 again. We don't want to ever look at this element because whatever is here at the end will be sorted. It will be the smallest value. That's how selection sort works. So now we just need a simple conditional in here to check what the value of the array is at the lowest, and then compare that to the value of the array at j. So we're going to have array of lowest, and then array of j, like that. And we want to know if we could do this either way. We could say if array of j is less than array of lowest, or if our current lowest is greater than the array of j. Yeah, I think I prefer logically, I think it makes sense this way, because we're looking, okay, anyways, we're looking for the lowest item, so I like to do it this way. If the array of j is less than our current lowest. Remember, the lowest is just a number like 0. So our first time through, if we walk through this, I is 0, which means lowest is 0, and then j is going to start at 1. So we compare. If array of j is less than array of lowest, is array of 1 less than array of 0? Yes, it is. So if that's the case, we're going to set lowest now to be equal to j. So we've now updated the value of lowest. So if we walked through, we start at the beginning with I set to 0, j is 1, and lowest is now going to be 1 because we just updated it. So it's referring to this item. But next time through, we have I is still 0. What is j now? Well, j is going up by 1, so j is 2. So if we compare array of 2 to array of lowest, which is 1, that's comparing these two. Now 10 is smaller. So we're going to set lowest equal to j, which means lowest is now 2, right? Index of 2. Now we could repeat this, and if we did, we would go I is 0 still, j is now going to be 3, but the lowest is still 2, because 19 is not greater, or 10 is not less than 19. One more time, I is 0, j is going to be 4, we're looking at the last item, and we check. Is array of j, which is 17, is that less than array of lowest? Array of lowest is going to give us 10. Nope, that's not true. So we don't update it. Lowest is still 2. So what we've done now is we've figured out the index at the end of this loop here. We know that the lowest index, the item that has the lowest value, its index is equal to 2 in this case. Now what we need to do is swap. So if you look at the pseudocode, what we do is take the value we initially started with, where we first began, which was at the first item right now, we swap that with the position of the lowest item. So that means we're going to swap 0 and 2. This and this. And to do the swap, we can do it many, many ways. We could do it with our temp. So we could make temp equal to, let's do array of I. And then we set array of I is now equal to array of lowest. And then we do array of lowest, if I can spell, equal to temp. And add our semicolons. So hopefully the swapping itself, the logic makes sense. You can of course use the fancier syntax as well. I'll show the same solution written in ES 2015 at the end. Okay, so this should give us a swap, and let's see what happens. Let's just take a look at what we get printed out. Let's go through at the end of each time. Let's do console.log array, just like that. And actually, rather than just doing this, what if we print? So I'm going to do a console.log array, and then this is going to be kind of annoying. Console.log swapping 2, and then console.log the array afterwards. Okay, and then to make it easier to see what's happening each time, this is a lot of work just to show you what's happening. And you probably already know what's happening, but I'm just going to put these dividers in there so we can see. Okay, so now if we run this, and I'm going to make my console larger. Where do we start? Whew, here we go. All right, so what happens? We start with this state, and we make a swap. Here's our first swap. We move 10 to the beginning. So then we start with that state, and we're looking at these, and we move, what do we move? 17 to the beginning, as you can see there. Now we're looking at these 3 at the end, and 19 is the smallest. So we move 19 to the beginning, as you can see. Now we have these 2. And what do? We swap 22 to the beginning. All right, now we have one element left. And what are we doing? Well, we're still swapping. 34 is the min, and you can see our code is still running. We're swapping 34 and 34. And then this is the return value at the end. So the code works, which is good. At the end, we get the sorted array, and it is selection sort. But there's a change we can make, which actually I think will be better illustrated if, for example, if I did this, 0 and then 2 at the beginning of this list. And I guess we can keep this. Actually, I'm going to get rid of this because it takes up so much space. I'm just going to console.log the items that we're swapping. So console.log I and lowest. And you'll see what happens. So I'm going to clear my console, rerun it, make this bigger. So the first time through, if we look at what that list looks like, the min is 0, but we go all the way through the list because we don't know that, and we find out that 0 is the min, but we still swap index of 0 with index of 0. And that results in nothing. We're doing this is unnecessary because we found that I was actually the same as the lowest. And the same thing happens again. The next item, index of 1 is our I, and we set the min to be, or the lowest to be 1 as well. We go all the way through and there's nothing smaller. So at the end, I and lowest are the same, and we still do a swap. And actually, you can see that happens at the end as well. We have one thing left, 17. Well, we still swap 17 with 17. So a slight change that we can make to fix that is just do a check. I actually think I put this in the pseudocode, yeah. If the minimum is not the value you initially began with, then swap them. Right now, we're just swapping no matter what. So we just add a conditional. If, and we'll just do if I is not equal to lowest. If that's the case, we're going to do our swap. So if I rerun this, whoops, clear down here, rerun here, there we go. Now you can see we're only making 4 swaps. We didn't make a swap here, we didn't make a swap here. But then we made 1, then we made 2, then we made 3, and then we made 4, and then that was it. We're done. Okay, so I have the same code, get rid of the console.log, but written with ES 2015 syntax. So if you prefer that, I brought swap out into its own little function up here. And now if you look at our logic down here, it's pretty short. We can do it on a single line, which I could have done the same thing. I could have moved all of this into its own function called swap as well. But here are two versions, and pick whatever you like. I'm using the newer way of swapping data. So same thing though. Loop over each item, set lowest to be I. Then we start j at I plus 1, and then we just check. I actually did the reverse logic, or the reverse comparison. I checked if lowest was greater than array of j. Up here I did if array of j is less than, it means the same thing. And then we just reset lowest, and then at the end, if I is not equal to lowest, swap them. So selection sort is not terribly efficient. We're talking about, for time complexity, O of n squared. We'll revisit time complexity at the end of this section to compare them all, the algorithms that we've learned so far. But yeah, roughly, we have to compare every element to every other element in the array. So as the length of the array grows, the number of comparison grows roughly at the rate of n times n squared. Yes, technically, the first time through, we make 6 comparisons, then 5, then 4, and then 3, and so on. But that doesn't really matter. In the grand scheme of things, we're still going with O of n squared. It's drastically worse than if we only had to make a single comparison for each item. Now, where selection sort potentially is better than something like bubble sort, really there's only one scenario, which is if for some reason, or you're in a situation where you want to minimize the number of swaps that you're making. So remember that bubble sort, if you can recall how that works, we're basically swapping over and over and over to get the largest item to the end. We keep swapping and swapping until it goes to the end. And then next time through, we swap if we need to and keep swapping. In selection sort, we iterate, we compare a lot, but we only make one swap at the end of each loop. So if for some reason we're worried about writing to memory, we're worried about actually doing the swap, which is not very common to be honest, but if you were, then selection sort is better. Otherwise, it's not very good. But it is easy, which is a good thing, and it helps prepare us for some of the other algorithms we'll see. So that's selection sort. Next, we have one more of the elementary algorithms, the basic ones, which is called insertion. That's coming up next. Hey, welcome back. So we're moving on to the third of our elementary sorting algorithms, the last one for this section, before we move on to some of the scarier ones, some of the fancier ones. Let's call it fancy instead of scary. So insertion sort, actually, it's pretty similar to bubble sort and to selection sort. We grouped them all together. However, there are a couple of key distinctions, some things that insertion sort is actually good at. So this isn't one that's just good to know about. It's not just a good challenge. There are situations where insertion sort does well, and I'll explain that as we go. But first, let's talk about how it works. So it builds up the sort by gradually creating a larger half of the array, which is always sorted. So instead of finding like the largest element at a time or finding the smallest element at a time, it takes each element and places it where it should go in the sorted half. So let's take a look. That doesn't really mean much, but if this is our initial state, we start with this. Our sorted half of the array is shown in green. So right now, half is not the right term, by the way, the sorted portion of the array. And our value we're looking at is 3. So where would we put 3 in order to sort this part? Well, we'd put it before 5, right? We insert it into the right place. Now we hit 4. Where does 4 go? We insert it between the 2. So now this is our sorted portion. Then we hit 1. Where should we put that? At the beginning. And we hit 2. Where do we insert that? Right there, index of 1. So you can see what happens is that we gradually build up the sorted portion of the array by inserting one item at a time in the correct place. So here's a quick walkthrough of it. If we start with this small array, we have 3, and we take 44, and we figure out where it should go in our sorted portion. Well, actually, it just goes right back where it was because it's greater than 3. That's where it belongs. But now we get to 38. Where should we put 38? In this left portion. We put it between the 2. Like that. Then 5. Where should that go? Well, it doesn't go there, does it? Nope. So we have to check the next one. Does it go there? Yes. In between the 2. 47. Compare it to 44. Oh, you just go right where you are. 15. Compare it to 47. Nope. Compare it to 44. No. Compare it to 38. No. Compare it to 5. yes. And now we have the sorted array. So hopefully you can see why it's called insertion sort. We are taking an element one at a time and inserting it in the correct spot. So as far as the pseudocode, what you do, you start by picking the second element in the array because our sorted portion will be considered the first element at the very beginning. So we don't need to sort the first element. So we take the second one and we compare it to the one before it. And if necessary, we swap them. Then we continue to the next element and check if it's in the correct spot. So we iterate through the sorted portion, the left, at this point, if we've sorted two of them, the left two, and we figure out where to put the third one. And we repeat until the array is sorted, and then return that array. All right, so let's implement insertion sort. So I have my snippet ready, and I'm going to define our function called insertion sort. Takes an array. This should be pretty familiar by now. Return that array. And let's call it down here with, what should we call it with? Let's go with 2, 4, oh wait, I'm doing a sorted array. That's not going to work. 2, 1, 9, and 76, and 4. Okay, hardest part of my day out of the way now, picking those numbers. And actually, that's not true. All of this is hard to explain. Okay, so we've got this here. And the first thing we want to do is if we just visualize what we're doing as we go through, rather than starting with the first element, because that can be kind of an edge case. Let's say we've gone through a couple passes and our array is sorted up until this point. So what do we need to do with 4, for example? Well, what we do, we take 4 and we basically work backwards. We compare it to 76 and we check which one is larger. If 4 is larger, then it stays right where it is and we're done. But if 4 is less than 76, then what do we do? Well, what we can do is move 76 up to where 4 is. And then we look down to the next one, 9. Where does 4 fit? Well, 9 is still larger, so we move 9 up until where 76 used to be. And then we check 2. Well, 4 is larger, so we put 4 right here, if that makes sense. So we end up with this. So the reason I'm starting from here is because the first easy part is we want to iterate over every item, right? That's obvious. All these sorting algorithms so far have involved that. We start with a loop. We start roughly at the beginning, although in this case, we can actually start looping at the first item, first index, rather than 0. And then we look backwards and we figure out where to start or what to do. So let's write our loop for var I equals 1 rather than 0. It's not a problem if we do 0. It's just an extra iteration. And we'll do while I is less than the length, array.length, add 1 to I. Okay, so now what we need to do is first let's make a variable to keep track of the value that we're looking at. So let's say that we're looking at 4. We're going to make a variable called, I don't know, what do we want to call it? Let's go with var current val equals array of I, like that. And now we just want to work backwards. So this is why it's easier, like I said, to think that we're towards the end or the middle of the array rather than at the very beginning, because there is no backwards really to work towards. So let's make another loop to go backwards. So for var j equals, and what should we start it at? Well, we want to start it at 1 less than whatever I is. So if we go back to this example, if this is what we're looking at, if I is right here, so that's 0, 1, 2, 3, 4. If I is 4, we want to start comparing I, or this number, to this number, which is going to be index of I minus 1. So j equals I minus 1 to start. And we're going to make a comparison, which we haven't done yet, and keep going until eventually we find the right spot. So worst case, how many times, for example, if this was 0, how many times do we need to go down? We need j to be 3, 0, 1, 2, 3. We need it to be 2, we need it to be 1, we need it to be 0. And then that's where we would put 0 at index 0. So for that to work, we want to keep going while j is greater than 0, or greater than -1 is one way of doing it, greater than or equal to 0. I always, which way do I prefer? I don't know. I was going to say I have a preference, but I don't really. Let's do j greater than, let's do greater than or equal to 0. So it's okay if we hit 0 because an index goes to 0, or you could do greater than -1, whichever one. All right. So then we're going to subtract 1 from j every time. So this is just our rough loop skeleton, if you will. So we pick, if I is 4, Then we have this loop j that goes from 3 down to 2 to 1 down to 0, and then it stops. So that's just the basic loop, but we don't really want it to just keep looping for no reason. We need to start figuring out where this value goes. Or if we're looking at this example, where does 0 fit in? So what we do, we already have 0, in our case, stored under the variable current val. So whatever I is, we're storing array of I in current val. So we have that over on the side. I'll just keep it over here, the value 0. And my console's not very happy about that. So what happens now is that j is going to start at 76 and move backwards. Well, j itself isn't. J starts at 3 and moves down to 0. What we want to do now is compare current value to array of j. So we could write that out basically like this, array of j, if I can type, array of j, and then we want to compare that to current val. What we want to check is array of j larger than the current value. So if that's the case, if 76 is larger than 0, we want to move 0 down, which what that really means is we're going to move 76 up. So if I show you, let me show you the actual operations. Okay, so first time through, 0's here, we compare current value to 76. 76 is larger. So we actually move 76, we copy it over to here. Remember, we have 0 already saved in a variable, so we don't have to do like a swap with a temporary variable. We already have that temporary variable called current val. So then we move back again to 9, and we compare 9 and 0. 9 is greater than 0 still, so we're going to take 9 and put it there. Now we move down to 2. 2 is greater than 0 still, so we're going to move it to j plus 1. Then we get to 1, which is still greater than 0, so we move it up to here. And then at the very end, if our loop is done, we're going to take whatever this value is and stick it right there. So there's a better way of writing this, and I'll show you what it looks like. It's a little bit confusing to see a for loop like this, but this is one way of doing it. So our loop goes while j is greater than or equal to 0 and array of j is greater than current val. So you may not have seen many for loops written like this, but this is one potential way of doing it instead of a second. You could do a while loop as well, or any sort of conditional check to break out of the loop. But what this reads as, so j starts as I minus 1. We're going to keep going while j is greater than or equal to 0 and array of j is greater than the current value. So if at any point, for example, if instead of 0, this last item was 20, we're going to go through once. Array of j is going to give us 76. That is greater, so we keep looping, and we want to move 76 to here. But then we compare 20 to 9, and all of a sudden, this isn't true anymore. So we're done looping. So now we just put 20 right here. So I know it's kind of confusing when we write it this way, but let me just fill in the rest. So if anytime we're going through this loop, what we're going to be doing is taking a value like this and moving it forward and moving it forward, and then we stop at some point. So to actually move that value forward, it's just array of j plus 1 equals array of j. So why don't I just do a console.log to show what's happening. Console.log array, and actually let's do it in here. So we're not sorting just yet because we're not actually replacing the correct value in. But if I run this, okay, you can see what's happening. So we started with 1 and we look back at 2. Well, 1 needs to go here, so we move 2 forward. So we get 2, 2, 9, 76, 4. We just never added in 1. So to remedy this, after this loop finishes, that means that we found the correct spot for where we need to insert current val. So then here, all we do is insert current val, and it's not array of j. It's array of j plus 1. Because if we walk through this again, let's say that we're starting here, then j is going to start right here. So we check which one's larger. Okay, 76 is larger. So remember, we have 20 saved in a variable. We're going to take 76 and move it here. But j was right here. So next time through, j moves down to here, and we compare 20 and 9. Well, 20 is greater than 9, so we're not going to move 9 forward. But we don't want to swap, we don't want to put 20 right here. We want to put 20 here in this space. So j is this, we want j plus 1. So array of j plus 1 equals, what's it equal? What do we call it? Current val. And now actually we're done. So if we step through now, what happens? Let me clear, execute. Okay, I'm printing when we move an item forward, which is kind of confusing. So we moved 2 forward, but then on this line right here, we inserted 1 at the beginning. Let's instead do console.log right here. Okay, so where's the start? Here we go. So you can see we go through the first time and we put 1 where it goes. It goes in front of the 2. Then we're looking at 9. Well, it goes where it is. Then we look at 76. That goes where it is. But then we get to 4. And we need to move 4 all the way to right here. And then we're sorted. So this one's a bit different. I know it's maybe a little harder to understand this code, but step through it. If you do get stuck, I highly encourage you to just write down what I and J are at every point, and just one at a time walk through. It might take a little bit. Use a shorter array. Definitely, when you're choosing numbers for the array, it helps to choose things that make sense, that like work with your algorithm. If you just pick a bunch of numbers like 2, 2, and 2, or you pick something that's already sorted, it doesn't help that much. So pay attention to that, but walk through it. If you need some help, try and understand what's going on. So insertion sort, as far as its time complexity, it's pretty similar overall to the other two we've seen. It's worst case, O of n squared. It's quadratic because as the length of the array grows, we also have to basically make n squared number of comparisons. But if our data is almost all sorted, so if instead we were looking at something like, I don't know, what would work here? Let's say 1, 2, 3, 4, -1, for example. Well, if we look at 2, we immediately find that it's greater. We don't have to do anything. We stop the loop. Then we move to 3. We find that it's greater than 2. We don't need to keep going. We look at 4. We're good. We look at -1. All right, now we have to go through and put it at the beginning. But compare that to totally random unsorted data where we have to continually place something and iterate. Then we're looking at a much worse time. Or actually, what's the worst possible scenario? Something like this, where you start, we get to 3, we have to swap it to here. Then we get to 2, we have to swap it to the beginning. Then we get to 1, and we have to swap it to the beginning again. That's the worst case for insertion sort. But if your data is nearly sorted, you're good. Now, another interesting thing that insertion sort is good at, if your data, there's something called an online algorithm, which is an algorithm that can work as data is coming in, as it receives new data. It doesn't have to have the entire array at once. So for example, let's say that we have some code where people are submitting numbers to us online, live. We're getting them and we want to sort them in. Don't ask why, but let's say we wanted to. With insertion sort, because the way that it works, that we're keeping one side of the array sorted and we're inserting items one at a time, it doesn't matter what the number is that comes in, we can place it where it needs to go. So that's one strength. If you're looking for a sorting algorithm that works in that way, which I probably isn't going to come up, but it is worth knowing that because of how insertion sort works, because we keep one side of it sorted and we insert things in the appropriate place, because of that, it works well in a situation where data is coming in live or streaming and you need to insert it at a moment's notice. Okay, so those are the 3 elementary sorting algorithms. In the next video, we'll just wrap up talking about their time complexity and space complexity, and then also do a quick recap of what we learned. All right, welcome back. So what I want to do now is really quickly take the 3 algorithms that we've learned so far, the 3 sorts, and compare them. So it will be a quick wrap up, but basically we've been working on each algorithm individually. We've been talking about the pros and cons, but we haven't really seen how they all compare. And you can see that they're grouped together in this section. I called them elementary sorting algorithms. They're often called quadratic sorting algorithms because their big O, their time complexity of all of them is O of n squared. Remember, we care about worst case. That's the point of big O. But we also broke it down into average, so you can see O of n squared for all of them. But then if we look at time complexity, there's a bit where they differ. So here's bubble sort. And this is with almost sorted data. So that's the best case. If our data is totally sorted, bubble sort works really well because it goes through and it has to do very few swaps. We iterate over and we do one more check and it's all sorted and we're done. And that's it. So bubble sort performs very well in that situation. Same thing with insertion sort. If we work with nearly sorted data, we place things in the correct spot, but then you look as we go, we don't really have to do anything. We're just checking each item to the one before it, and we don't have to do any swaps. So we basically iterate through the loop once, doing one comparison for each item. If the data is totally sorted, that is. In this case, it was almost sorted. So insertion sort works well in that situation. Selection sort, however, doesn't fare so well. If you look what happens, here's nearly sorted data. We're still going to go through each time to find the lowest item. So we iterate all the way through, and it happens to be the first item. Then we do it again, and we look for the smallest, the minimum item. It doesn't matter that it's already almost sorted. So selection sort does not perform well in this situation. But selection sort is very simple to understand, which is pretty much its only positive. So returning back to this sorting algorithms animations website, if we look at nearly sorted, so there are a bunch of algorithms we haven't talked about, but we'll learn about some of these, like merge sort coming up. But if we click nearly sorted, focus on how insertion, selection, and bubble perform. You'll see insertion and bubble finish very quickly. Selection takes forever, but still, insertion and bubble, which are generally slower than these algorithms, the more advanced ones, they still perform better on nearly sorted data. Okay, so that's the time complexities. Basically, they're all O of n squared, except with nearly sorted data, bubble and insertion perform well. Now, space complexity, they actually are all the same as well. And that's because we're not really using much space with these algorithms. Everything's happening in place. We're not actually creating new arrays. It doesn't matter how long the array is. We're not creating a variable for each element or two variables for each element or something like that. But what you'll see later on, some of the other algorithms that are faster, what they do is that they actually create a bunch of smaller arrays. For example, merge sort, which we'll learn next at the beginning of the next section, its space complexity is not O of 1. It's not constant. But for these, they're all basically the exact same. One thing about insertion sort that is special, that I mentioned already, is that it works very well if you need your data to be continuously sorted. So new elements are being added. So it's not a one-time thing where you have all the data ready. If we're using insertion sort, and I add in the number, 39, for example, insertion sort just needs to do basically a single pass to figure out where to put that. Versus if we were doing selection sort, it would resort the entire thing. It's not able to figure out exactly where it goes right away. So insertion sort works well in those situations. If you have data coming in and you need to resort things over and over and over and maintain a running sort, keep things up to date. Okay, so lastly, I just want to recap what we covered. Sorting is very important. It's a fundamental thing in programming. It's also very common in interviews. We'll talk more about what actually you need to know. If you are interviewing and you're concerned about sorting, you do not need to just sit here and memorize implementations of all of these algorithms. We'll talk more about what you do need to know. So bubble sort, selection sort, and insertion sort are all roughly equivalent in the grand scheme of things, especially when we compare them to the next batch of algorithms we're going to learn in the next section. There are some slight differences between these three, but they become insignificant when we see how much faster some of these other algorithms are. So they all have average time complexities that are quadratic. We can do better though, and that's what's coming up next. We need more complex algorithms. They are a little trickier to explain. They're less, I don't want to say less human. They're less intuitive right off the bat. So it's a little more work. But these algorithms are definitely worth knowing. And also, what we'll see in the next video, or in the next section, these algorithms actually can perform better on very small data sets. So we'll see why that is. So these aren't a complete waste of time to learn. If you're worried about that and you're thinking that, oh, he's just showing the dumb ones first so we can get to the hard ones afterwards, that's only partially true, because these actually do excel when the data sets are small. All right, so in the next section, we're going to start learning about some of these scarier algorithms. We're going to take our time though, so hopefully it's not too bad. And we're going to start off with merge sort. Hello, welcome back. This is part 2 of sorting algorithms. This is intermediate sorting algorithms. So we have 3 more to look at. And basically, we're learning these separate because they are much faster, but they're also a little bit more challenging. They're less intuitive to write on your own. They're meatier, juicier algorithms that take more time to understand. but they're also, the payoff is that they're faster. And I'm going to prove it to you. I'm going to show you at least one example of just how much faster they can be in this video. But first, I want to add an important note, which is don't be scared. When I've taught this before, I think a lot of students feel bad because they struggled through the beginning elementary sorting algorithms. They weren't able to write everything on their own. That's totally normal. And when you get to these three, these algorithms are harder. They're stepping it up. Don't feel pressure to write the code yourself, period, but especially not the first time through. So I'm going to give you pseudocode for the adventurous souls who do want to try and implement it on their own. But really, this section is more about walking through the code and understanding how it works, being able to explain the algorithms, not being able to rewrite it word for word, character for character on your first try. So keep that in mind. We're going to go through it, focus on how it works, focus on being able to explain back to me, for example, what each line of my code does, rather than you feeling the pressure to come up with everything from scratch. Because these are challenging, and these are algorithms created by academics that have been around for a while, that have been tried and tested. So please don't worry. Don't be too intimidated. I'm turning nobody away, all right? If the last section was hard for you, that's okay. Don't feel bad that this one's called intermediate. Okay, so our objectives. First, understand the limitations of what we've learned so far. Bubble, selection, and insertion. What's wrong with, well, we shouldn't say what's wrong. What are their shortcomings? We're going to implement 3 sorts, implement merge sort, quick sort, and radix sort. But first, I promised I would show you a demonstration of how much faster the algorithms we're going to learn now are. So the sorting algorithms we've learned so far don't scale well. They actually work pretty well on small, like a 20 item array. They work pretty fast, but they do not scale well if we're working with 100,000 elements, for example. So if we actually tried bubble sort, I'm going to scale it down and just do 10,000 elements. It takes quite a while. I'm going to show you right now. So what I have here, so here's my bubble sort implementation. And down here, I have a little bit of code that makes an array of, oh no, this is 100,000. I can't count. Never mind. It is 100,000 elements. And I'm going to start by showing you bubble sort. Now what this code does, if I just copy this over and change this number to be 10, it just picks 10 random numbers and sticks them in an array. So if I do 100,000, we're going to have an array that's 100,000 random numbers. There shouldn't really be any order, period. I mean, it's technically possible they could be already sorted, but that would be insanely unlikely with 100,000 items. Okay, so I'm going to do this now. I'm going to hit enter. It's going to make the array. That just takes like a split second, but then bubble sorting, it's going to take a little bit. So command enter, I start it. And what am I going to talk about to pass the time here? Well, let's see. What am I going to say here? I got some time to pass. Well, it's a nice day outside and I'm in here recording. There we go. Looks like it just finished. So I don't know exactly how long that was. I think I also put a cut in the middle of this because I took a sip of water and then I realized that was going to sound really bad on the camera if I'm gulping. So anyway, that was about 20 seconds of my time. Now, if I do the same thing with merge, which I already have in this file, merge sort, we haven't learned it yet, but just watch. I'm going to clear and run the same code. So 100,000 items, but now pass it into merge sort. Wow, look at that. I mean, that's crazy how much faster that was. That was less than a second compared to 20 something seconds. Now, if I added another 0 here, which I'm not going to, remember that bubble sort is quadratic. So that has serious implications. When we add another 0, when we're squaring the time, basically, that's huge. That's a huge difference. So I'm not going to do that. But with merge sort, I mean, we'd still notice a difference, but it's nowhere near the time difference. And we'll talk about what the actual big O is of something like merge sort. But I just wanted to show you there how much faster it is. Maybe that gives you some motivation for learning it. So this faster family of algorithms that we're going to learn, they can improve time complexity from around ON to ON log n. So if you can think back, I'll show you a chart again, but O of n log n is not bad. It's pretty good. It's much better than quadratic time, O of n squared. It's not as good as log n, and it's not as good as O of n, but it's still pretty dang good. So in this section, we're going to learn 3 algorithms that improve time complexity, and we'll also learn why it's n log n, for example. Where does the n log n come from? We haven't really talked about it. We introduced the idea of a log. We said that O of log n is good. It's pretty fast, but we haven't really seen where it comes from. So we'll see that. There's a trade-off, though, as I mentioned, between efficiency and simplicity, unfortunately. So these more efficient algorithms are definitely harder. They're longer, or even if they're not longer in the amount of code, they're just weirder. They're not how we think as humans most of the time. It's not how you would sort something. So they take a little longer to understand. But it's worth it, right? That's a very big difference that I just showed you. And that was only 100,000 items. Now imagine 1 million or 10 million pieces of data. Massive differences in time. So let's dive in. In the next video, merge sort. Hey, welcome back. So the first of the fancier sorting algorithms that we're going to take a look at is called merge sort. It's a very well-known one. It was created back in 1948. A computer scientist / mathematician and all-around smart guy named Jonathan Van Neumann wrote the first ever recorded program of merge sort. It was 23 pages of code for this computer here called EDVAC. It's a very large computer. It was like 6,000 or so vacuum tubes. Writing code back then, obviously very different than it was today, but the algorithm, the idea, was first conceived in 1948. So the idea behind it, it's really a combination of two things, merging and sorting. And actually, you could say it's really a combination of three things, splitting up, sorting, and merging. All three things take place. So it exploits the fact that arrays of 0 or one element are already sorted. So if you were asked to sort an array that just consists of the number 1 and that's it, you know it's sorted. Or it's just the number 9, it's sorted. Or it's empty, it's sorted. So merge sort takes advantage of that fact. It works by decomposing an array into smaller arrays. So that's something known as a divide and conquer algorithm, a divide and conquer approach. We split up the larger array we're trying to sort into smaller sub-arrays. All the way down, we keep doing it until we get to 0 or 1 element arrays. So we would take an 8 element array and split it, and then split it, and then split it until we end up with 8 single element arrays, and then we merge them back together. So here's a little visualization. Imagine we have this array here, 8, 3, 5, 4, 7, 6, 1, 2. That is 8 elements. What do? We start, or the code starts, by splitting it in half. So we're dividing it. And we're still not at 1 or 0 element arrays, right? These are 4 elements, so we split again. And now we have 4 2 element arrays. We're still not there, so we split again. Now what we have are 8 single element arrays. So now we merge them together. So let's focus here. We take these 2 arrays and we merge them back. And as we merge them, they are already sorted. We know that they're sorted. So merging 2 sorted arrays is easy relative to merging 2 unsorted arrays. So what we do, we basically just compare the number. Which one is smaller? Well, the smaller one goes first. Which one of these is smaller? Smaller one goes first. Which one of these is smaller? Put that first. 1 goes before 2. Then we repeat the process. Now we're merging this array with this array. But notice this is already sorted. This is already sorted. So now we just make a couple comparisons. Take the first item, compare it to the first item. Which one is smaller? Put that one first. Then we take this item, compare it to that item. Which one's smaller? Okay, put 4. And then we do it again, put 5, and then 8. And then the same thing over here. So we end up with 1, 2, 6, 7, and 3, 4, 5, 8. 2 sorted arrays that are smaller. Now our final merge, we put them all together. And we end up with this 1, 2, 3, 4, 5, 6, 7, 8. So hopefully you can see, yes, this algorithm is a little more complicated, but it involves first splitting up until we end up with sorted arrays, which are 0 or 1 element. That's the base case. That's the smallest thing we get to. We know they're sorted if they're only 1 item long or they're empty. Then what do? We merge them. Merging sorted arrays is easy. Well, compared to merging unsorted arrays, still not that easy. And we sort them back until we finish and we get a totally sorted array. Here's another visualization. Here we have 8 elements in an array. And the very first thing that happens is we split them all up into 8 individual arrays. So now they all have, each color represents the fact that they're an individual array. And then you'll see as we merge them together, they change color. So it starts with the first 2. These are 2 arrays. How do we sort them into one? 3 and 44. It takes them out and puts them back in in that order. They're sorted. So now we have, this is one array here. So we have 7 arrays, right? Oh wait, 1, 2, 3, 4, 5. Yes, 7, I can't count. So next, we take these 2 individual arrays and we sort them into 1 and put them back. Now, we take these 2 arrays, the orange and the red, of those 2 items each, and we sort them into 1 array, like this, and then we put that back. Then we have to start on the right side. So this was the left division. Now we take 47 and 15, we sort them from 2 arrays of 1 item into 1 array of 2 items. Same thing with 36 and 26. Now what do? We merge these 2 arrays together, the yellow and the green. There we go. Put that back in, and now we merge our 2 arrays of 4 items at the very end. There we go. So that's merge sort. And as you can imagine, there's a little bit of logic involved. In the next video, we're going to implement the first step, which is merging. So we have to understand how to merge 2 sorted arrays, and then the rest is actually pretty easy. So in the next video, we're going to cover that. We're going to build a merging function. Hey again, welcome back. So this is the first part of writing merge sort, which is writing a function to merge 2 sorted arrays. So again, we assume the arrays are sorted, and all you have to do is return the combination of those 2 sorted arrays. So for example, I already have it written here. Well, I'm not showing you the code, but I have the function call here. 2 sorted arrays, 1, 10, 50, that's sorted. 2, 14, 99, 100, that's sorted. When I run this, I merge them together. We get 1, 2, 10, 14, 50, 99, 100. So 1 array that is returned. So that's basically your job. If you want to try and do this on your own, I'll have a solution in the next video. This part's, well, personally, I always hate saying if something's hard or easy, but I think the logic for this one makes sense. So we'll walk through it though. I have pseudocode. So I jumped the gun on my slides. Yes, it's useful to first implement a function responsible for merging 2 sorted arrays. Given 2 sorted arrays, the helper function should create a new one, which is also sorted. And yeah, it's important. It needs to consist of all the elements in the 2 input arrays. So what do we do if they're not the same size? We'll cover that. And as far as how it should work, this is something we haven't seen, but it should run in O of n plus m time and O of n plus m space. So n and m, we have 2 inputs now to our function, 1 array and then the second array. So n is the size of the first one, m is the size of the second one. Of course, those are 2 that sound very similar, and you probably can't tell when I'm saying n and m, but that's the standard way of saying it, of writing it down. So that just means that if n grows super large but m doesn't grow very large, it should just be O of n plus m. Often, and usually in merge sort, they are the exact same size or 1 element different in real life. But if we're working with something and for some reason we're merging an array of 1,000 items with an array of 1,000,000 items, it should be O of n plus m. So as that 1 grows, anyway, all I'm saying is that you should visit each item in the array 1 time. Right? If it was just O of n, that means that it's linear time. You visit each item once, you iterate over it. But if it's O of n plus m, that means that we're iterating over each item in each array once. So here's the pseudocode. Create an empty array. So define a function, takes 2 inputs. Create an empty array that you'll return at the end. And then you start with the smallest values in each input array. You start at the beginning. So have 2 counters, one called I, one called j. I recommend using while loops for this. Personally, that's what I like to do. And you need to have one that starts out, they both need to start at 0. J and I are 2 numbers, start at 0. While there are still values we haven't looked at, meaning while I and j both haven't hit the end of their respective arrays, we're going to take the value of the first array, of the first item, and then compare that to the value of the first item in the second array. Now, if the first item is smaller, we put that in our result array, and then we move on to the next item in the first array. If it's the other way around, if the first array is larger, the item in the first array, then the value in our second array, we take the value from the second array and put that in the results and move on to the next value in the second array. And then once we finish one array, we just push all the remaining values from the other array in. So for example, if we took these 2, we just write them down here. These are our 2 arrays, and then this is my result that I'm going to return. We start with 2 counters, I and j, and they start at 0 and 0. So we compare 1 and 2. Which one is smaller? 1 is. So we put 1 here. And then we move on in this first array, we're now looking at 10. So if I were to put a little marker here, like that, it's not a very great way of writing that, and our marker over here, this is going to bite me, this is going to be annoying to keep track of, is 2. So next time through, we're comparing 10 and 2. Which one is smaller? 2. So we put 2 in here, which means that now we need to shift this over, and now we're looking at 10 and 14. So now which one is smaller? 10 is. So we put 10 in, and then we move this up, not this one. Now we're looking at 14 and 50. Which one is smaller? 14. All right, so then we move this to 99. What am I doing? Get out of there. Okay, 50 and 99, which wins? 50 wins. So then we've now exhausted that array. And what that tells us, if we've hit the end of this, all we do is take all remaining values in this other one, because if this is sorted, and they have to be sorted in the same way, I should have mentioned that. We can't have one in ascending and one in descending. They're sorted in the same way. Whatever is at the end of this array, if we have stuff that's left in the other array, we know for sure it's all greater than whatever that 50 in this case. So now we just add in 99 and then 100. And now we have successfully merged the two arrays. So that's the approach that I'd like for you to try and take. Otherwise, if you don't want to do it, in the next video, I'll just show you a solution. So this is a first important step for merge sort. All right, welcome back. Now let's write the code to make this work, to merge two sorted arrays. So if you jumped to this video because you saw implementation in the title, I recommend you just go back and take a look at the rough pseudocode, how it's supposed to work, just so you understand what we're doing here. So here I'll start by defining, I have a snippet as always. I'll call it merge, my function, and it takes in two arrays. Let's just do ARR1 and ARR2. And then in here, the very first thing we should make is just make a variable called results. Empty array, and then at the very end, we return results, like that. And then we need to do all of our logic. So the first thing we'll do is make our two little pointers. We're going to start with a variable at 0 and another one at 0, one for each array, and then they'll move through individually. So we'll do let I equal 0, let j equal 0, or whatever. You could call it ARR1 index or something, but I'm just going to go with I. Okay, so now the bulk of our logic, we need to have a while loop that runs while I is less than the length of the array and j is less than the length. Basically meaning while there is still data for us to look at in both. If we hit the end of one of them, remember in the last video what I showed, when we started here, then we hit the end of 50 and there was still data here, we're going to do something else. So this first loop only applies when we're looping through both at the same time. So while I is less than array1.length and j is less than array2.length. Perfect. Now we just do a simple comparison of array2 of j and array1 of I. So it's up to us which one we want to do first. I'm going to say if array2 of j is greater than array1 of I. It's so confusing to try and talk about. If this is our results, we're basically checking if this one is greater than this one, what do? We take this and we put it in results. So if that's the case, we're going to say results.push array. Oh, and I said that backwards. I'm sorry. If this one is greater than this, then we take the smaller one and we put it in there. I don't know why. We're not trying to do descending order. We want the smallest items first. All right. So we're going to push array1 of I if it is smaller, if array1 is the smallest thing. And if that's the case, if we actually push array1 in, we then need to move I. It's no longer going to be 0. We need to move I up by 1. And that's super easy. I++. Okay, so now we have an else, which is a lot of times, well, I guess we haven't covered the edge case if they're the same value. So instead of doing an else if array2 is less than array1, because if we just did greater than and less than, we'd be missing the case of equality. But we can just pick one. We could do greater than or equal to with an else, or do greater than and then have an else, which will catch the case when they're equal and when array1 is greater. Okay, so if that's the case, otherwise we do results.push array2 of j, and then we increment j by 1 because now we're moving up So that would be do we have that scenario? Let's see, in the first time through, we put 1 in here, and then we're looking at 10 and 2. Yes, so now 2 is smaller. So in that case, we add 2 in, which is from array of j, but then we increment j by 1, and we go here. Array of 2, I mean. All right, so if we look at what happens at the end of this loop, let's print this out. Well, we're going to return results, so we don't actually need to print it. It's not complete, but it's getting there. So we end up with 1, 2, 10, 14, and 50. Because what happened is we did this, then this. We did 10, 14, did 50, and then we hit the end because we did 50, and then we added 1 to I, and we hit the end of the array. So this loop broke out. We finished. So what needs to happen afterwards once we exhaust one of them, because remember our condition, while I is less than array1.length and j is less than array2.length, once we hit the end, we then just take everything that's left in j and add it in. Or if this was shorter, like here, if we hit the end, we then take whatever's left in the first array and add it in. So that's easy as well. I'm just going to do 2 while loops, and I'll just have a while loop while I is less than array1.length. What are we going to do? Results.push array1 of I, and then just add 1 to I. So basically the same logic in here, it's just that we're not doing a conditional check anymore. And I'm going to just duplicate this, but then replace I with j, and array1 with array2. Does that make sense? So whatever happens at the end, we merge them as far as we can until we hit the end of one of the arrays. So let's say we hit the end of array 1. That means that array 2 still has stuff in it. So j hasn't hit the end. So j will be less than array2.length. In our case, if we hit the end, 0, 1, 2, 3, we get 1, 2, 10, 14, 50. That means that j is currently at index of, 0, 1, 2. So we have to add this in, and we have to add this in. And then j will have hit the end. J will be equal to array.length at that point, and then we finish. And we return results. Let's see if it works. It looks good. If we tried something sneakier, like an empty array, and then the array 1, 3, it still works because this loop never runs, right? All that happens is that we have array of 2, so j is less than array of 2, so we just push in all the results, or all the items in array of 2 into results, and then return that. If we tried, let's see, doing something like 100, and then over here, I don't know, I don't really even have anything worth showing at this point. That won't work, it needs to be sorted. All I want to show is that it works, and it does. Okay, so this is the first part of merge sort. This is the longest part, actually. If you came up with something better, definitely share it in the comments, post on the discussion board. But this is a pretty simple way of doing it, and I think it's pretty legible, pretty easy to understand and walk through. So we're going to use this code in the next video where we add on and actually implement merge sort. Right now, this only works with 2 sorted arrays. Okay, see you then. Hey, welcome back. So now we get to the sorting part of merge sort. And this is actually, the code itself is pretty short. It's only, my solution is 5-ish lines. The problem is that conceptually, it's a bit hard to understand. And that's because most merge sort implementations use recursion. So if you skip the recursion section, I highly recommend you go take a look at that because this is going to seem a little insane if you've never seen recursion before. And even if you have, it's not immediately intuitive to write code that's recursive. So here's how it works. We have our merge function that works. We just assume it works at this point. If you didn't write it, just go to the last video, copy the code if you want to try and implement this yourself. But again, don't feel bad if you can't. This is really about the concepts, how it works, not about you being able to write it from scratch immediately. Okay, so merge sort. We have our merge function takes 2 sorted arrays. Now remember, the goal is to basically keep breaking up the array into halves. So how do we break an array, just a single array, into a half, 2 halves? Think about that. My recommendation is to use slice. So array.slice, and you go from 0 until the middle of the array, and then you go from the middle array until 0, and that gives you 2 halves. And then what are you going to do with each one of those halves? Well, you're going to call merge sort again, and you're going to break each half into its own halves, and keep going recursively. And what's our base case? When the arrays, their length is less than or equal to 1, meaning that it's 1 or 0. Okay, so that breaks them all up into these small elements, these small arrays, using slice recursively until, again, our base case is we hit the end. Array.length is less than or equal to 1. Then once we have those small arrays, we merge them back using our merge function that we've already written until we're back at the full length of the array. Now, it seems simple when you write it this way, but the code, it gets confusing when you're writing it recursively. I'll just put it that way. But that's pretty much it. So once the array has been merged back together, we return the merged array at the very end. Okay, so if you want to take a stab at this, definitely do it. But in the next video, I'll walk through it. Remember, recursion is kind of crazy. It can be a bit of a leap to get there. So don't feel bad if you can't get this one. Okay, see you in the next video. Okay, so let's get writing our own merge sort. So I have a new snippet again. I have our merge function that works from 2 videos ago. We can get rid of this line for now. Now I'll define our merge sort function, which takes a single array. And if we go back to our pseudocode, all that we want to do is keep splitting it up into smaller arrays and calling merge sort on those arrays until the length of the array is 1 or 0. So we can start with the base case if we want. If array.length is less than or equal to 1, we're going to return the array. Not array1, array. So right now, that doesn't mean much. Basically, we're not doing any recursive calls. Remember, every recursive function has a base case and then the recursive case, a recursive function call. So we're going to call merge sort on something again. But it needs to be on the 2 halves of the array. So how do we split this array in half? So for example, if I call merge sort down here on this array, 10, 24, 76, 73, 72, and 1. So how do we split this in half? So if we just took this, I recommended using slice. So if I save this to a variable, var arr equals that, how do we splice it or slice it in half? Well, we go from 0 for the left side. We go from 0 until what? How do we find the midpoint? Well, we could take the array.length divided by 2 and then floor that. All right, so remember binary search, we did the same thing. So that's what I would do. I would do math.floor of array.length divided by 2. And that gives us 3. So then I would do array.slice from 0 to 3. And that gives us the first 3 items. And then we need to do array.slice from 3 to what? We need to do we can actually just do array.slice 3, and it will go from 3 until the end. That's how it works. We don't have to pass in the second number if we don't want to. So that will split the array. That's our first step. And then we'll call merge sort on each of those. So let's just write that code to start. So we can define the midpoint here. So let midpoint, or let's just call it mid, equal math.floor, just the same thing we saw, array.length divided by 2. So that gives us the halfway point. Then we're going to say the left side equals array.slice from 0 until the midpoint. And then we'll say the right side equals what? The right side is going to be array.slice just from midpoint until the end. So now we've split that array into 2 pieces. I'm missing an R here. There we go. Now comes the tricky part. Instead of just doing left equals array.slice, I'm actually going to call merge sort array.slice. And same thing here, merge sort array.slice until the end. Okay, so what's happening here? If we called this the first time through with this array, array.length is not less than or equal to 1, so we skip that. We find the midpoint, then we find left and right. So if we focus on left, we're calling merge sort again on this array that you can see right here. So that goes through, and it's called again. Array.length is not less than or equal to 1, so we skip that line, and then we split it in half again, and now we call merge sort on the left and right. And then one time through, one of them has length of 1, so we return that array, but the other one has length of 2 because there's 3 items, so we call merge sort again. And then at that point, we have 3 single item arrays. And now we have to worry about merging them back. And this is the other bit of magic. We merge the left and the right. So this is the code, and I'm going to walk through line by line how it works. We're going to step through the call stack with a smaller version, but let's just make sure that it's working. So if I execute it, looks good. 1, 9, 10, 24, 72, 73, 76. Okay, now let's call it on, let's do 4 items. And I'm going to put a breakpoint right here. Now if we look at what happens just with these 4 items, I'm going to step through it. So I'm going to run the code. And let me close the console so we have more space. Look at our call stack over here. Okay, here we go on our journey. So we start and merge sort is called on this array. It's 4 items long. So this first thing does not happen. Then we find the midpoint, which is 2. Now here's the first thing. Watch what happens to our call stack. We are recursively adding, so there's another merge sort that's been added to the call stack. And if you look now at this merge sort, it's been called on that left half, right? So that left half is just 10 and 24. Is the array.length less than or equal to 1? Nope. So we skip it. And what happens again? We find the new midpoint, which is just the middle of this array. We're calling merge sort on what? If we look at our stack again, there we go. We're calling merge sort on a single element, 10. All right, now, this time array.length is less than or equal to 1, right? So we're going to return the array of 10, and you'll see it pop off the stack here in just a second. Return value, array, and it popped. Next, we're back to this one. So now we're back to, we left off right here, right? This is a hard thing about recursion. I wish I had a whiteboard diagram this all out, but we were waiting. This function call waited for left to go all the way until it returned something, and now right needs to go all the way until it returns something. So right on that second half is 10, 24. We split it, and the right side goes in, and we get the array of 24. Array.length is less than or equal to 1. So we return array, and you'll see it pops off the call stack in just a second. Now we merge the left and right, 10 and 24. And when we merge them together, it calls merge. All this code happens. And at the end of the day, we end up merging and then finally returning. And watch the call stack. Now we pop off again. Now this time we finished left, right? That was waiting. In this code, we were waiting to merge the left side. Now we need to do the right side. We never even ran this line. So now the right side is now going to go. And if we take a look, it's calling merge sort again with, what is it passing in? Just a moment. There we go, 76 and 73. So array.length was not less than or equal to 1, so we didn't return it, so we move on. Now we call merge sort on the left side, which gives us 76. The array.length is less than or equal to 1, so we're going to return array, and you'll see it pop off that call stack. Keep going. There we go. And now we're back here at merge sort for the right side. It's crazy. I know this is the hard part to understand, but we're back here. And this time we're calling it with 73, array.length less than or equal to 1. That's true. We return that array, which is 73, pops off the call stack. Now what we have is left and right. So left is 76, right is the array 73. We merge them together. So we call back up here, go through this, merge them, and then eventually we return results, which is the merged array. And now we return that from this merge sort call to our original call of merge sort, which was waiting. So we have left and right that have now been merged. Well, they haven't been merged together, excuse me. They have been sorted, they've been split up and sorted individually and then merged. And now we have two arrays that are 2 items long, and we merge those together with our final merge, left and right. So now this code takes a bit longer because we've got 2 pieces of data for each one. But you can see results down here. We return results to merge sort. So now we have 10, 24, 76, 73. And that is what we return out. And finally, I think if I show the console, we end up with that return value. Whew. So as you can see, it's a lot to keep track of in your own, just 4 elements, trying to keep track of it all in your head can be a lot. So I diagrammed it out, And let's just take a look at the actual order things happen in. So when we call merge sort on 10, 24, 76, 73, first thing that happens, array is this array. We check, is the length less than or equal to 1? No. So we find the middle point, and then we call merge sort on the left side from 0 until the midpoint. So this is called merge sort of 10, 24. So then in that code, if our list is 10, 24, it's still not less than or equal to 1, the length. So then we call merge sort again on the left. And now, this time, the length of this array is less than or equal to 1. And in that event, we return array. So we return 10. So now this merge sort of 10, 24, the list of 2 items long, it now has a value for left. So next, it finds the value for right. It was waiting for this to come back, remember? Now it came back, so it moves on to the next line, right. So now we call merge sort of the right side, which is 24. Merge sort of 24, the length of that array is less than or equal to 1, so it returns 24. So now we have our left and we have our right. So now we can move on to this line, merge left, right. So when we call merge left, right with 10 and 24, remember our merge function takes the 2 sorted arrays, it merges them, and that returns a value, which is the array 10, 24. Yes, it was already sorted, but ignore that part. Our code doesn't know that. So it returns a value now. So that was returned from this merge sort call, which was the left side of our first merge sort. So now our very first merge sort was waiting, and it has a left side returned. Now it's going to do the whole right side. So we call merge sort on 76, 73. In that code, the length is not less than or equal to 1, so it computes the midpoint, and then it does the left side merge sort of 76, which that is a 1 item array, so it returns the value 76. Then this right side, which was waiting, we completed this side. Now we're going to merge sort the rest, and that gives us 73 as a return value because it's a single item array. Then once again, we move on to this line. This was waiting, merge left and right. Well, now we have our left and our right, so we merge them, and that returns 73, 76, 2 item array. Then this merge sort up here now has the left and the right that it was waiting on. So it got this, then eventually this. Now it can actually merge left and right. And to do the left and right merge, we end up with this, 10, 24, 73, and 76. I know it's a lot, but remember, I've said this a couple times, just focus on being able to explain what's happening or walk through. If you have a whiteboard or a piece of paper, I think it can be really helpful to write down exactly what's in the call stack at any given point. And I recommend you don't try it on a super long array. If you go into like 6, 7 items, it takes a lot more time and a lot more space to diagram. Please don't feel too intimidated by this. In the next video, we'll talk about the big O of merge sort. All right, welcome back. I just want to quickly talk about big O, time and space complexity for merge sort. So we haven't mentioned it really, although I showed you in the very first intro to merge sort video how much faster it is, at least anecdotally, compared to something like bubble sort. But the best case, the average case, and the worst case for merge sort are all the same, O of n log n. So unlike something like bubble sort did okay. It was, I wouldn't even say okay. It does pretty poorly. It's quadratic n squared time, unless the data in the best case is already sorted, in which case it improved to linear time, O of n. Merge sort has no such, how do I want to say this? There's no edge case like that in merge sort. It doesn't care what the data looks like. It doesn't have an impact. It's going to split it up over and over and over and merge things over and over and over, no matter what the input is. If it's already sorted or if it's reversed or totally random, it doesn't really matter. So that's the first point. Now, the second thing is, why is it n log n? Where does that come from? And definitely I would not expect you just to know that or even necessarily to be able to compute that right away. But here's a basic overview. So if we start with an array of 8 elements, so this is showing at the end of the process merging them together, but let's say we're starting here and moving upwards. So we have to split it into 2 pieces. So that's one decomposition. then we split it again, and that's another decomposition, and then again until we get items that are arrays that are 1 item long. So what's the relationship here? If we have 8 items in the array, n is 8, how many times do we have to split in order to get single element arrays? In this case, it's 3. But if instead we had an array of 32 items, I'm not going to type it all out, but imagine that I'm just writing the length here. So we have an array of 32 items. We could do a split, which gives us one array of 16 and another of 16. And then we could split that again, which is what would happen. We'd get an 8, 8, 8, 8. So 4 8-item arrays. And then we split that again. And what do we get? We get 8 4-item arrays. And then we keep going. And I am not going to count these precisely. It doesn't exactly matter anyway if I get the number right. The point is, though, eventually we're going to end up with 32 1-item arrays. Now, how many splits did we have to do to get there? I'm not counting. Please don't hold me accountable here. How many splits? Well, here's the first split, the second, the third, the fourth, the fifth. So as n grew to 32, we had 5 splits. When n was 8, we had 3 splits. What's that relationship? Well, going back to the big O section, that's log n. Now remember, we're talking about base 2, so log base 2 of n. What that really means is 2 of what power gives us n. So in our case, if we have 8 elements, we take 2 and raise it 3 times, 1, 2, 3, to get 8. Or if we have 32 elements, that means 2 times 2 times 2 times 2 times 2. 2 to the 5th power is going to give us 32. So that's where the log n comes from. As n grows, the length of this array, the number of times we have to split it up grows at the rate of log n. Now, what about the n log n? Where does that come into play? Well, each time that we decompose it, we have O of n comparisons when we're doing the merge. So for example, let's take a look at this row right here. This is on the way back to the merge towards it's the last step of merging. There's always 8 items we're comparing each time through, right? We're not adding or removing items at any point. We're just splitting them up and moving them around. But there's always 8 things total. So here, we would start and compare 1 and 3. That's a single comparison. And then one of those is chosen, which is 1. So then we move on and we compare 2 and 3. And then we compare 3 and 6, and then 4 and 6. And at the end of the day, we have O of n comparisons on each of these. So as n grows, the merge algorithm itself, not the merge sort, just the merge, has time complexity of O of n. So if we have 1,000 items in the array, there's roughly 1,000 comparisons that need to be made. If we have 8 items in the array, there's roughly 8 comparisons that need to be made to merge. So in total, we end up with n log n. So O of log n is the number of decompositions. As n grows, there are the number of times we split n, the number of times we split the array grows at the rate of log n. But then each time we do split, each decomposition, we have O of n comparison to actually perform the merging. So in total, we end up with O of n log n. So if we look at a chart, here's O of n log n. You can see it's way better than something like O of n squared quadratic time. It's not as good as O of log n, of course, or linear time O of n, but this is actually the best that we can get for a sorting algorithm, unless the algorithm itself takes advantage of some weird quirk in the data. So there's an algorithm we'll look at called radix sort that uses a particular quirk of numbers, and it won't work to sort anything else. But if we want a data agnostic sorting algorithm, the best we can do is O of n log n. So merge sort is doing great. It's always O of n log n, best, worst, and average time. And then finally, space complexity. So this is a bit different compared to things like bubble sort, which have a constant space complexity. When we talk about merge sort, as we have a larger array, we have to store more arrays in our memory, and not in our memory. We have to use more space. So that is a trade-off. Now, usually we care about time complexity, but if space is a consideration, then absolutely something like merge sort takes up a lot more space compared to bubble sort or any of the other earlier sorts. Okay, so that is the big O of merge sort. Next up, we have a whole other fun sorting algorithm. See you then. Hey, welcome back. We're moving on to our next intermediate sorting algorithm, which is called quicksort. So it has a bit of a catchier name. It sounds better than merge sort. I mean, who doesn't want a sort that is called quick sort? But I have to admit, personally, this is the bane of my existence as far as sorting algorithms. Not because it's bad. I mean, it's very useful, as we'll see later on. It's efficient. It works well. It is indeed quick. But for some reason, my brain just does not like the way that quicksort works. Anytime I have to teach these sorting algorithms, I usually, like the night before a lecture, will go review, make sure I remember how everything works. I can rewrite the code. And occasionally, I'll have to reference previous code or something. But with quicksort, every single time I have to double check my work. My brain just rejects storing it. It does not like it. So not to poison your opinion of it ahead of time, because I have had many a student who really loves quicksort. Just for me, the way my brain works, it's just not very intuitive. So we're going to pay special attention to trying to understand it and make sure we step through it. Okay, so quicksort, it works on the same assumption that merge sort does. It's one that is going to be easiest to solve through recursion, where we keep basically splitting up the data, the array, until we hit arrays that are 0 or 1 item long, which means that they are individually sorted. We have an item of one, you have an array with 1 item, it is sorted. So that's what we take advantage of, but we do something different. We work by selecting a single element, which we're going to call the pivot point. So in any array, you pick any element. It doesn't actually really matter. We'll talk about some of the implications, but let's say we pick the element in the middle. What we're going to do is move all the numbers that are lower than that number to the left of that number, and all the numbers that are greater than that number to the right. Now, we're not going to sort them all. We're just going to move them to one side. And then from there, we know that that one number is in the correct spot. Only that one number. All the other numbers are on the right side of things, or the left side, but we don't know the exact position. So then we repeat the process for the left side and for the right side. So if that explanation made 0 sense, I don't blame you. Let's take a look at a little diagram. So if this is our array, we have 8 elements, 1 to 8, the numbers, and they're in a random order. What we do is we just pick some element, and for this example, we're going to pick the first one, which is 5, and then move all the numbers that are less than 5 to the left of it, and all the numbers that are greater than 5 to the right. So if we count the numbers that are less than 5, we have 1, 2, 3, 4 numbers. So that means that we should have 1, 2, 3, 4 here. We're going to move them all here, and then at this index right here, we'll move 5. And then on the right side, we'll have 7, 6, and 8. And if you look at the next step, that's what we've done. So 5 is in the correct spot. We know that in our sorted array, 5 is going to have index of 4. 0, 1, 2, 3, 4. These aren't sorted, this isn't sorted, but this is sorted right now. So now we recursively repeat the process on the left side and the right side. So on the left side, let's just start again. It doesn't really matter what we pick. It will work no matter what. But let's pick the first item again and put that in the correct spot. So that means it's going to be at index of 0, 1, 2, because 1 and 2 need to come before it. And that's what we end up with. So now this is in the correct spot. We know in our final array, 3 is going to have index of 2, 5 is going to have index of 4. Then next, we have an element of 2, or an array of 2 elements. This is nice and easy. So we pick the first element, which is 1, and we figure out where it needs to go. And that all that we have is one other element, which is greater than it. So the right side now becomes 2, and we can sort that, and it's a single element. So we've now hit the end on our left side. And if you kind of look, imagine putting these all on the same line, we end up with the sorted array, at least the left side of the 5. Then we have to get to the right side. So remember, all the way at the beginning, we split right there. We just took care of this. Nope, highlighting the wrong thing. Okay, my computer doesn't want me to highlight that. We took care of the left side here. Now, let's get to the right side. So we pick the pivot point, which is 7 in our example. And we have to figure out, okay, where should 7 go? What's the index where it should end up? We move the other elements. So we move 6 to the left of it, 8 to the right of it. And those are both single element arrays now. And actually, if you look at what we have, 1, 2, 3, 4, 5, 6, 7, 8, we have the sorted array. There, I got ahead of my slides again. I'm always doing that. So this shows us how it works roughly. It makes sense, I think, in a nice little diagram, but when we actually start working and trying to write the recursion and visualize it when we have code, it can be a little bit tricky. Okay, so I have Visual Algo pulled up with Quicksort now. So here's another visualization. We start with this unsorted array and we pick 11 as our first pivot point. So we want to move all the elements that are less than 11 to the left of it and all the ones that are greater to the right. So we start and just compare it. Okay, 40 is greater than. Okay, here's a 10. So that's less than. So what we're going to do, you might think that we would swap them or something. What we're actually going to do is keep track of how many elements are less than 11. So far it's one element. And then we're just going to swap 10 and 40. But we're mentally keeping track of, in our code, not mentally, there was one element that is less than 11. Now we keep going. Nope, that's greater than. Okay, here's another element, less than 11. So we do the same thing again, but now we know we have a variable, and we say there are two things less than 11. So once we hit the end, because there's nothing greater than 11, or nothing less than 11 anymore, now we know, okay, there were two things that we added in. There are two items that we now need 11 to leapfrog over. And that's what happens. So now 11 is in the correct spot. So does that make sense? We count 1, 2, and then we move to that position. And now everything on the left side is less than 11. Everything on the right side is greater than 11. Now it happens that these two values are sorted already, but our code doesn't know that. It's not guaranteed. Okay, so now our code is going to take the left side and repeat the same thing. So this is showing us 11 is cemented in place. And now it does the same thing with 6 and 10. But this is super short because there's really no other values to compare. And so it cements 6 and then it cements 10. But now let's focus on the right side. So next up we have 50. And I'm just going to count how many numbers are greater than 50 or how many numbers are less than 50 as we go through. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers. So now we're just going to swap 50 to the end there. Now 50 is in the correct spot, so it should turn orange. Okay, so now we have to sort the left and the right side, but there is no right side, so we have to sort this left side. So we pick 27 again. Not again. We picked 27 for the first time. Now we compare it to 43. That's greater than it. Greater. Okay, here's a less than. So we swap, and we keep track of, okay, there's one element that was less than. Keep going. Here's another swap. Now we have two elements that were less than. Keep going. Now we have three elements that are less than. And finally, four elements. Now where do we put 27? Well, we know that we had four numbers less than 27. So we swap it there. All right. So I'm not going to walk through every other step. I'm just going to fast forward. But you can see 27 is now in correct position. Now we do the left side. Keep going. Now we do the right side. 43 is in the correct spot. Now we have 42 in the correct spot. Okay. And we're almost there. There we go. Fully sorted. So it's kind of, this is why, for me personally, maybe that made more sense to you, but trying to write this in code can be very intimidating. And I'm going to give you the pseudocode in the next video, but it's not at all the expectation that you just go and write it. This is a hard one. So the actual code is not that long either, but just conceptually, it's a lot. So I'm going to give you the pseudocode. If you want to attempt it, go ahead, but also don't beat yourself up, please. Welcome back. In this video, we'll write the first part of quicksort. Just like with merge sort, we implemented the merge helper first. We're going to do the same thing here. You might hear this called partition or pivot. It does the same thing. So we're going to write a function that, given an array, it designates an element as the pivot point, and it should rearrange the elements in the array. So this is basically what I already said. Got ahead of myself. And ahead of the slides, surprise, surprise, all values less than the pivot are moved to the left, and all values greater than the pivot are moved to the right. But the order on either side doesn't matter. It just needs to be less than the pivot and greater than the pivot on the right side. But inside the left and right, it doesn't matter what order they're in. So the other really important thing is that this helper should do it in place. So it should not make a new array. And it should return the index of the pivot. So it returns the index. It does everything in place, so don't make a new array to do it. So the first thing to discuss, picking a pivot is actually an important decision. The runtime of quicksort can change depending on where you pick the pivot from. Ideally, it should be chosen so that it's the median value in the data set, if that makes sense. If we could perfectly get it, we would pick the middle value of our sorted data so that the left and right sides would be equal. But that's not very easy to do if we don't know what the data itself is and how it's ordered. That's the whole point. We're trying to order it. So there are other strategies. You pick the first element or the last one or the middle or a random element. For simplicity's sake, in this video, we're just going to always choose the pivot to be the first element. That does actually have some consequences with as far as big O that we'll talk about later, but we're going to just pick the first element to make it simple. So here's how it could work. If this is our array and we call our pivot function of that array, it should return index of 4. So notice it doesn't return the array, but if we look at the array, it's been changed. Any of these configurations are valid. So what it does is it picks the first element and chooses that as a pivot, so 5. And now it needs to rearrange the array so that 5 is in the correct spot where every number to the left is less than 5. So if we look at all these examples that could be the value of array, it doesn't matter the order. If we have 2, then 1, then 4, then 3, or 1, then 4, then 3, then 2, and so on, as long as we have 1, 2, 3, and 4 on this side. And then on the other side, we have 6, 7, 8 in some order. Now, this isn't all the possible options. I just didn't want to go and list every single possible combination out, but it's important to note, it doesn't matter for our code what we actually have on the left side, it matters what we have. It doesn't matter exactly the order that it's in on that side. So these are all acceptable. All that matters is that 5 is in the correct spot, and we return the index, which is 4. 0, 1, 2, 3, 4. So this is basically saying, in the final sorted array, if you kept doing this on the left and the right over and over and over, 5 is in its final position. This is where it's going to be once you sort the data. Okay, so here's the pseudocode. Here's one version of it at least. So write a function, call it pivot or partition, and it accepts 3 arguments: an array, a start index, and an end index. And I would have the start default to 0 and the end default to array length -1. Then we're just going to pick the pivot from the start of the array. Remember, and we could change this to be from the middle or the end or a random place, but for simplicity's sake, we're picking from the very beginning, and then store the current pivot index in a variable. So this is going to keep track of where we're going to swap that pivot to at the very end. So I'm going to walk through on the next, in just a second, on visual algo and show you what I mean. But we're going to loop through the array from the start until the end. And if the pivot is greater than the element that we're looking at, we're going to increment that pivot index variable from up here and then swap the current element with the element at the pivot index. So, it's a nightmare trying to just read this pseudocode, but it will make sense once I show you an example. And then at the very end, we swap the pivot that we started with the pivot index. And then we return the pivot index. So rather than just talking about text, let's look at it. So at the very beginning, we're going to pick the first element to be our pivot. We start at 28. Then what we do is loop through every other element, and we compare 28 to 41 in this first case. 41 is greater, so we actually don't do anything. But then we get to 4. 28 is greater than 4, so we know that we need to have 4 on the left side of 28. And we're just going to keep a mental note. We're going to have a variable called pivot index, and that's going to keep track of how many things are less than 28, so that we can then swap 28 at the very end to the correct spot. So we move 4 over, and then we have this pivot index that currently is going to be equal to index of 1. So if there was nothing, ignore everything on the other side of the array. If there was nothing else, we know that 28 needs to be in this position at the end, so that 4 can be less than. But if we keep going, 11 is also less than 28. So we're going to swap that with 41, and now increment the pivot index by 1. So now we know, okay, there are 2 things less than 28. Go again. Oops, didn't click it. Here we go. 16, that's less. So we swap. And now we know there are 3 things less than. Again, we swap. There are 4 variables. There are 4 pieces of data in this array, 4 elements less than our pivot. Nope. Okay, here's our 5th one. We swap. We go again and again and again. And here's our 6th element that is less than 28. So we swap. Now we've hit the end, and we have this pivot index variable, this mental note I mentioned, and it's now equal to 6 because every time we found an element less than 28, we added 1 to it. So we have 1, 2, 3, 4, 5, 6. This tells us we need to swap the element at index of 6 with our pivot, which was at the beginning. And if we do that, there we go. Now we're done. All we have to do is return this index. So everything on the left is less than, everything on the right is greater than. The pseudocode on its own isn't all that helpful, but if you look at this side by side with something like this, where you step through it, I think it can help. So go ahead and implement this if you'd like to. Again, it's not all that easy, but give it a shot. If you want to stick around, I'll do one more example walkthrough, but I know that it can get boring. If you understand it all and you're ready to go, or you're just bored, go ahead and skip this. But I'll put it here for extra practice. New data. At the very beginning, we pick our pivot point at just the first thing, 26. Now we compare it to every other element. Now 23 is less than 26, so we're going to keep track of that. We need to have, we have that counter, pivot index, and we know at the very end, at least, we're going to have to swap 26 to index of 1. We get to 27, that's greater than, so we don't do anything. That's greater than again. Now we get to 17, which is less than. So what we do is we swap with 27 in this case, and then we're going to increment our pivot index by 1. So now we know there are two things less than 26, so we need to swap at the end, so 26 is here, where 17 currently is. We go through again, that's greater than, greater than, greater than, greater than. Finally, we get to 1, which is less than, and we swap with 44. And now we increment pivot index by 1 again, so now it's at 3. So at the end of our code, we're going to swap the pivot at index of 0 with the pivot index, which is 3, 0, 1, 2, 3. So we swap these two things, and voila, now we have the left side correctly partitioned and the right side. So 26 is at the correct spot. And our code should return index of 3, which is saying that the correct spot for 26 in this array is index of 3. All right, welcome back. So let's start by defining our, nope, not in caps, our function called pivot, and it accepts an array. We have a start, and you can go back and look at the pseudocode. It should default to 0, and an end defaults to array.length plus 1. And then here's my sample call. So pivot of this. Take a moment and figure out what you think this should return. Pause it if you'd like. What it should return is the index 3, because it's going to take this first item, which is 4, as our pivot, and figure out the correct index that it should be in. So if we look at the sorted array, like this is the final array of these numbers. This will not be returned from this, but from our eventual quicksort, it will be. If you look at where 4 is, that's index of 0, 1, 2, 3. So our code should return the index of 3. Now the array, it could look like this at the end, but more than likely it will look like this possibly, and then on this side we might have 8, 6, 7, 5. All that matters is that 4 is in the correct spot. So anything on the left just needs to be lower, anything on the right is greater, but the order doesn't matter. So the first thing we'll do is define a variable called pivot. And remember that our example, we're starting with the pivot always as the first element. So if start defaults to 0, we'll set this to be array of start. So we start with 4, for example, as our pivot. Or if our array looks like this, it would be 10. So we start with that. And then we're going to make a variable called swap index. Now swap index is going to keep track of where we're going to swap this 4 to at the very end. And also it's what we're going to return. This is going to be the index. In our case, it should be 3, hopefully, at the very end that we return. So I'm going to start it at the beginning, index of 0. So it starts at 0. Now, we need to loop over every item in this array, but there's no reason to loop over this first one and compare it to itself. So let's loop over everything after start. So that means for I equals, instead of 0, let's do start plus 1, while I is less than array.length, I plus plus. So rather than doing 4 and comparing it to 4 and then 8, just do 4 and start off our loop right here. Now all we want to do is compare our pivot, so that's going to be 4. So if pivot is greater than, and we want to compare it to array of I, the next element that we're looking at. So our first time through, is 4 greater than 8? No. So we're actually not going to do anything. Next time through though, we're comparing 4, and now I has gone up to the index of 2. So we compare 4 and the value of 2. 4 is greater than 2. So what we'll do is increment swap index by 1. So this tells us, okay, there is one thing at least so far that is less than our pivot. But then we're also going to swap 2 with 8. Because our swap index is 1, all we have to do is swap array of I with array of swap index. Does that make sense? So swap index was 0. Now we found the first item that is less than 4. So we increment the counter that's keeping track of how many things are less than 4. Where are we moving 4 to at the very end? So now it's equal to 1. Anyway, now we need to swap. So now what I'm going to do is just copy in any swap function. This is our basic one. It just takes an array and then 2 indices, and it swaps the values in that array. And I'm going to put it in a function because we're going to actually use it more than once in our code. So we're actually almost there. What we're going to do now is swap the array inside of it, the swap index, followed by I. So our first time through, the first swap we make is 2, which is I of 2, actually, the same number. And then we're going to swap it with swap index, which is 1. Okay, so then we repeat the code. Next time through, we compare 4 and 1. Well, 1 is still less than 4. So this time, we increment swap index again. So swap index is now 2. And then we're going to swap the item at index of 2 with the item at index of I, which means we're going to swap 1 with the item that's here, which is actually 8. So if we were to visualize this whole thing, we start off like this. And the next time through, we don't do anything with 4 and 8, but then we do swap 2 and 8, like that. And then the next time through, we're comparing 4 and 1. Well, 1 is less than 4. So we swap 1 and 8, like this. And now our swap index is right here. So at the end of the code, if there was nothing less than 4, which there actually is, but if there wasn't, at the very end, we're going to swap 4 and 1. And if we did that, we end up with all the numbers less than 4 on this side, ignoring the fact that we still have to account for 3. So we keep going, and next we compare 4 and 5, nothing happens. Then we compare 4 and 7, nothing happens. 4 and 6, nothing happens. 4 and 3, this time 3 is less than 4. So what do? We take 3 and we swap it with our swap index, which was right here. So now we swap 8 and 3. So we added 1 to our swap index, which now makes it index of 3. Which, yes, it also is the value of 3. That's confusing, but this is our swap index. So the very last thing we have to do after our loop is take that last swap index and swap it with the start, like this. And now 4 is at the correct position. So basically all that we've been doing, we keep going through here and we move things over to the left. We swap them anytime it's less than 4, but we've left 4 at the first position. So at the very end, we can just swap 4 to the correct spot. What do we need to do now? Well, if we actually just printed out array, I think this would make it clear for us. You can see here, we start off, I'm only printing it out when we do the swaps, but you can see the final state is this. And then we need to do our final swap, move 4 and 3, swap them. And then we need to return that index of swap index. So let's come down here after the loop and add in our final swap, which is in the pseudocode, swap the starting element with the pivot index. So we just do swap, which again is coming from here. And what are we going to swap? We're going to swap the array, the start, and then swap index. So we're not swapping the pivot because pivot is the value. The start is the index of that pivot. So this is kind of a headache to try and walk through. I totally recognize that. But let's just make sure it works first. We need to return at the very end swap index. Remember, that's the whole point. It needs to return the swap index. We run it, it returns 3. And if we start off with a different number like 9 here, it returns 8 because 9, the correct location is at the very end of the array of index of 8. So I'll go back to 4. So we get 3, and if we console.log the array at the very end, you should see 4 is in the correct spot. All the lower numbers are before it, all the greater numbers are after it. So that's our pivot helper. So kind of a lot of work. So now that we have that done, we need to move on to the actual sorting part. We're doing this one time. We need to repeat this on the left side and then on the right side, and then repeat that until we hit the one item arrays. So we'll get there. Oh, and before I forget, here is the ES 2015 version where we just use our fancier version of swap, and I use let instead of var, and that's pretty much it. It's the same exact logic. It still works. We still get 3. So I'll leave them both in there. You can use the one you prefer. All right, next, quicksort. All right, welcome back. So in this video, I'm going to quickly run through the pseudocode for quicksort, but it's pretty short, so I'm actually going to just implement it too, rather than doing a separate video to show the pseudocode and then implement it, just to keep things a little briefer. So we have our pivot helper finished. We pass in a full array, or any array, and it's going to take the first item and figure out where it should go, and then put all the smaller items to the left, all the bigger items to the right, and then return the index. So that's important that it returns the index, because what we're going to do in our quicksort function is that it's going to call that pivot helper at the beginning with a full array, and we'll find out, the index of 4, for example, is the first pivot point. And then what we're going to do is recursively call the same thing, call quicksort again on the left side and on the right side of that pivot point. So imagine we call quicksort with this array. Well, the very first thing that happens is that we find the pivot, which is 4, and that is moved to this index right here. And then what we're going to do, there we go, is we're going to then call quicksort on this side from 3, the beginning, up until, but not including the pivot, because we already figured out this is in place. We don't want to move this. So we're going to sort the array here and here with quicksort. So the rough logic, when the helper returns the updated pivot index, we recursively call the pivot helper on the left side and then on the right side as well. Now it's important to notice, or to point out, we're not making new arrays. This is all happening in place. We're not making new arrays. It's happening in the same array. So our base case, it's not quite just to check if the array is item of length, or if the array has one item in it. It's to check if the sub array has one item in it. And what that means is we're always going to be working with this array, for example, but we're only going to be looking at this portion, or this portion, or eventually this portion. And so what we're going to check is not to see if the length of the array is 0, or is 1, because this length will always be the same. We're not adding or removing elements. We're going to check if the start point that we're looking at, and let's call it left and right, if the left and the right are equal to one another, or if the right is less than the left. So that happens when a subarray has less than 2 elements. So I'm just going to implement it. This is a tough one, honestly, to just take that pseudocode and try and write it yourself. I applaud anybody who wants to do it and who tries it out. But again, no expectation on my part that when I teach this in person, it's very rare that anybody can implement it right away. And even once I show the code, it can be hard to come up with it again. And I've already mentioned my struggles with it and how it's just unintuitive for me. So I'm going to define my function quicksort. I've already done that actually. And it's going to take an array. And the first thing that we'll do is call, so let's make a variable called pivot index. And it's just going to be equal to calling pivot with that array. But the thing is, our pivot, first of all, if we go back, it accepts an array, a start, and an end. And this is important because the very first time through, we want to call it on the whole array. But then this recursive function eventually is going to call it again on this subarray or this one, where we have a different start and end point. It's not just the default 0 up until the end of the array. So what I'm going to do is in here, I'm going to make an argument called left and set it equal to 0, and another one called right, which is array.length minus 1. And then we're going to pass in left and right when we call pivot. So the first time we call this right here, the default value for left is 0, and for right is going to be 0, 1, 2, 3, 4, 5, 6. So we're calling pivot on this array with 0, 6, right? So then that goes, I deleted a bracket, takes the first item inside of that pivot function, and it figures out that this needs to actually be at index 3. So it changes the array to look like this, and it returns the index of 3 to us. So pivot index is equal to 3 at this point. Then we want to repeat the same thing, but we want to do it on the left side, which basically means from the left, the start point, which right now is 0. So from the left up until the pivot index minus 1. So we already have this cemented in place. We want to now sort from here to here. And then the same thing on the right side, but we want to go from pivot index plus 1 up until the end, the right. So let's do the left first. So the left side is just quick sort of the array. This time we're going to pass in a left and a right. Unlike down here when we called it the first time, they defaulted to 0 and then array.length -1. This time the left that we're looking at is still going to be the same left that we looked at before, 0. But next, the right where we're going to stop is going to be what we've already discussed, the pivot index -1. So that way we don't include that pivot index in there. So this is cemented. We just want to look at that. And the same thing on the right side. Well, not quite exactly the same idea, but it's going to be quick sort of the array, but we're going to start at pivot index +1. So that means if this is our index, we want to go from here until the end. So pivot index +1 until right. So those are the recursive calls. However, if I just run this as it is right now, there's a big problem. It's going to run forever. So actually, if I do this, we get our Stack Overflow maximum call stack size exceeded because there was never a base case. Nothing was ever returned. Nothing ever stopped this recursive call. It just keeps going and going and going and going and going. So where do we want to stop? We want to stop in this situation where we've hit a subarray that is 1 element long. And how do we know that? Remember that at any point, if we looked at array, it's always the entire array. We're sorting it in place. So even at this step right here, for example, array is still the entire array. But what has changed are left and right, because left and right are constantly changing as we're calling quicksort recursively, because left and right are based off of the pivot index. And so we're getting a new pivot index each time. Left and right are changing. And so as these subarrays become smaller, left and right get closer together. So for example, here, left was 0 and right was 6. Then here, for example, left was 0 and right was 2. Here, left is 0, right is 1. Now here, left and right are the same. So our conditional, we want to keep doing this code, keep running if left is less than right. And so as soon as they are equal, as soon as left is now equal to right, that means that we're looking at 1 element. Does that make sense? Remember that left and right are just pointers inside of this full array. So it started like this, and then on one of them, the recursive call moved to this, and then to this, and then they became the same thing, and that's when we stop, because that means that we've hit the end, at least of one of the branches. So I need my bracket there. There we go. Okay, so we're still not quite done. We have one missing piece, which is really important. We're not returning anything. We need to return array at the very end. Because remember how these recursive calls work. This quicksort here is waiting on the results of quicksorting this and quicksorting that. And then those in turn are waiting on the result of quicksorting this and that. So we have to return the array here so that we can get it back here and keep going up. And then the same thing on the right side. So let's save, and I'm going to clear my console. Let's see if it works. Nope, not clear 0. There we go. Let's see if it works now. And it looks good. We're getting 1, 2, 3, 4, 5, 6, 9. Not sure why I chose that. And let's just verify. Let's mix it up again a little bit, put a negative number in here. All right, and it looks like it's working. All right, so lastly, let's just step through the call stack, visualizing what actually happens with the Chrome debugger. So I have a simpler array with 6 elements in it, and all that we're going to do is execute it. So I put my breakpoint, command enter, and I'm going to step through it. So first up, at the beginning, this is our array. Left is 0, 5, or right is 5. It's the last index. That makes sense. So now we're going to, because left is less than right, we're going to call pivot from 0 to 5 on that array. So we go up to pivot, and at the end, I fast forwarded, we get to swap index is 2, which is returned, and the array now looks like this, where 4 is at index of 2, and 2 and 1 are to the left of it, and 6, 9, and 5 are to the right of it. So we return that. Then we get to this line. So we have pivot index is now 2. We just calculated that. And the array looks different. And now we're going to do quicksort of this array, but from the left until pivot index -1. So if you watch the call stack, there's a new call of quicksort on top of it, but left is 0 and right is 1. So now we're looking at these two items. And so we do the same thing. We find the pivot. The pivot index is 1, so we return 1. And then we move on. And there's a new quicksort that's been added. This time we're going from 0 to 0 of this array, which now left is not less than right. So what does that mean? It means that we return the array. So now this is the array that gets returned back to the previous quicksort, which was waiting for this side, the right side. So now the array looks like this: 1, 2, and 4. The left side is sorted. So this quicksort is now waiting to do the right side. So pivot index is 1. So this quicksort is the second part. It's the right side. So when we did these two elements, we did the left, and now we do the right. But the thing is that there is no right, because right is less than left. So all that is returned is the array again. As you'll see, it's unchanged: 1, 2, 4, 6, 9, 5. We go back to an earlier quicksort that was waiting. And this time, here we go. And now we're sorting the right half. So pivot index is 2, which is right here. And we're going to call sort the array from that pivot index +1, meaning index of 3, up until this, the end. So here we go, we call it. And you can see that now, this time around, left is 3 and right is 5. So now we find a new pivot. We find that the pivot index is 4. This is what the array looks like now. So we found that 6 was our pivot. We put 5 to the left, 9 is on the right. We return the value of 4. So back here, we now have a new pivot index of 4. And we're going to take that index, and now we're going to call quicksort on the left side, which is really, if you look, it's from 3, which is the left, until our index was 4 minus 1, so 3 to 3, as you can see here. And what does that mean? Well, left is less than right. Notice the new quicksort on the stack. Left is less than right, so we are going to return that array as it is. And then we get to our next one, quicksort on the right side, which also is going to be sorted, because you'll see that left is 5, right is 5. That means that we need to just return the array, which is what we do. And that takes us back to the next quicksort, which is waiting to return array, which now has been updated. So we've returned array, and then we're on our final, this is the original call, where now we have both sides have finished, left and right, and we're finally going to return array. And here's the return value, and there we go. 1, 2, 4, 5, 6, 9. Congratulations on not quitting this video early if you made it through. It's a lot, but that's the basics of quicksort. Welcome back. Our last video on quicksort. Good riddance, if you ask me. We're going to talk about the time complexity and space complexity of quicksort. So first off, notice that best and average are both O of n log n, which is the same as merge. And if we look at y, let's look at best case, for example. So here's our array, and we have to make a decomposition, and then another decomposition, another one, just like we did with merge sort, where the pattern here, as n grows, we have to make log n, log base 2n decompositions. So as we have more elements, for example, if we had 32 elements, we have to make 5 decompositions, slice it in half 5 times. If we are, and this is the best case, remember, we're going to see the worst case in just a moment. If we have, I don't know, what's next, 64, we would have to make 6 decompositions. So that grows at the rate of log n. But then each level, each decomposition that we make, we have to make O of n comparisons per decomposition. So that's happening when we're pivoting. Remember, when we're finding the pivot, we're comparing to every other element one time. So that is how we get n log n. It's very similar. It's the same reason, really, why we got n log n with merge sort. But now let's talk about worst case. So with our algorithm, our pivot function, it takes the first item as the pivot always. Now that's problematic if our data is already sorted. So here's the worst case for our current quicksort. If we have this array and we're trying to sort it, and of course our code doesn't know that it's sorted, So we take this in, and the very first thing we do is find the first item and use that as the pivot. Well, we compare it to every item in that array, but nothing is less than it. So the next array, that decomposition really only gave us a single item. We have this entire subarray left. So every time we go through, each decomposition is only one item that we're pivoting on. And so everything moves to the right side with our current algorithm. And we have to keep going and going and going over and over and over because we're only taking the first item and it's already sorted. And then for each one of those, so that is n decompositions. The worst case with our current setup is O of n decompositions. And on each level, each decomposition, we have to make O of n comparisons, which results in O of n squared, quadratic time, for the worst case. So basically the problem arises when the pivot that is chosen is the minimum element every single time, or the pivot is always the maximum element. So to fix that, in this example at least, if we're dealing with a sorted array, we could get around it by, instead of pivoting around the first item no matter what, pivot around a random item. Just pick anything in here, it doesn't matter, just pick a random item. Or try and pick the middle element every time. And that way, even if we have a sorted array, we can avoid the problem. But of course, there's still a chance that if we pick the middle element every time, it's possible that the array is unsorted and it's supposed to be in random order, or we think it is, but somehow we're always picking the minimum every time. We can never avoid that worst case entirely because the way the algorithm works, if you're pivoting around the minimum or the maximum repeatedly, that's going to be quadratic time. But we can just do our best to avoid the chances of constantly picking the minimum or the maximum, which is why you would do a random number or the median instead of the first element every single time. But by doing that, what we did, picking the first element every time, it allows me to illustrate this problem, the worst case scenario. So take a deep breath. That was quick sort. That's a lot, I know. Again, do not feel any pressure to be able to write that on your own. It's really more about understanding how it works, being able to walk through. If you had a whiteboard, could you write down the values of the array each time through? Could you diagram out the recursion? That's the sort of thing that I hope you took away from this. Okay, moving on. Welcome back. All of the sorts that we've seen so far are grouped together in a group called comparison sorting algorithms. All that means is that whether we're talking about bubble sort or something more advanced like quick sort, at the end of the day, beneath the surface, the base comparison that we're doing is between two items at any given point. So we have one item on the left, let's say, and another on the right, and we're deciding which one comes first or which one comes second, depending on how we're sorting. So comparison sort just means we're comparing two things. That's the most we ever compare at a given time. We're doing less than versus greater than, and then we're deciding where that one item goes. So when we talk about average time complexity for something like bubble sort, it's O of n squared, same for insertion and selection sort. Then we saw a slight more than a slight improvement. We saw a pretty big improvement with quick sort and merge sort, which had average time complexity of O of n log n. So the question is, are there faster sorting algorithms? Can we improve upon O of n log n? Can we do better? And the answer is sort of. The answer is yes, we can, but not by making comparisons. So mathematically, there is a lower bound, an asymptote, for our average time complexity in a comparison sort. So no matter what the actual comparison algorithm is, what the sorting algorithm is, quick sort, heap sort, shell sort, any of the ones we've seen, cocktail shaker sort, haven't heard of that one, all of these, well, not all of them, some of them are slower, like we saw with bubble sort, but the best average case time complexity that we can ever hope for in any comparison sort is n log n. If you want to learn more about the reason for it, you can read this Wikipedia article. It goes into a little bit of a proof down here that explains how we arrive there. It all has to do with the limited information that we can gain from a single comparison. There is a mathematical bound to that. Anyway, that's not really the focus here because we have a solution. We have a way around this, but only in certain cases. So there are other types of sorting algorithms that are not comparison algorithms. And these algorithms take advantage of special properties of the data. For example, there's a group of sorts called integer sorting algorithms, and they only work with integers, with numbers. And we don't actually make direct comparisons. So one of those is radix sort. So when I say that we don't make direct comparisons, I mean we're never actually comparing, is this number less than this number? Is this number greater than this number? So we end up sorting the data in a different way. So radix sort is kind of fun, and it's very different than anything we've done so far because we're not making comparisons. So let's talk about how it works. So I mentioned it's a special sorting algorithm that doesn't make comparisons, and it works on numbers. So usually when this is actually used, it's used with binary numbers. Any number can be expressed in binary. Also, you could take any strings or images if you wanted to and convert them to binary. So it's possible to sort other data, but the actual data we work with at the time that we're sorting it needs to be numbers. And we're going to work with base 10 numbers like 950 or 17. So it never makes comparisons between two elements. It never asks what's smaller, what's larger. Instead, it exploits the fact that information about the size of a number is encoded in the number of digits. What I mean by that is that if a number has more digits, let's say a 4-digit number, it's larger than any 2-digit number. It doesn't matter what the two numbers are. We're not comparing the two numbers, but we know that something with more digits is larger than something with fewer digits. So here's actually how it works. We actually take a list of numbers. Let's say this is what we're trying to sort. We have some numbers that are 1 digit. These are all base 10, 2 digits, 3 digits, 4 digits. And we create 10 different buckets. And these buckets represent all of the possible numbers, the 1-digit numbers in base 10. So 0 through 9. So for every spot in a number, it could be a 0, a 1, a 2, all the way up to a 9. And what we do is we go through the entire list of our numbers, and we start by looking at this digit. So the first digit in the number from the right side. So 6, 4, 6, 3, 8. Okay? And we group them into buckets based off of that number. So you'll see all numbers that have a 2 in the rightmost position go in the 2 bucket. All numbers with a 6 in the rightmost position, whether they're 2 digits, 100 digits, it's just that we're looking at the rightmost digit. We group them together here. So we're not sorting them within this bucket. You can see that these are not in order. We take all 7s, all 8s, all 9s, and then we form them back into a list, keeping the order that they're in right here. So this will be at the beginning, and then this number, and then this number. You can see here. So the numbers that had 2 as their last digit come before the numbers that had 3 as their last digit. And then at the end, we have the numbers with 9 as their last digit. Now we repeat the process, except we look at the next digit to the left. So we're going to look at this digit, and this one, and this one. Okay? So now we group them based off of that second digit from the right. So if we look at this column, this bucket, we're talking about 0, which this has a 0, 408 has a 0 in that position, 902 does. But then these numbers, which are 1-digit numbers, don't have any digit in that position, so we just put them in the 0 bucket. There's a 0 there, right? We could write any number as 07 is the same as 7. 04 is just the same as 4. So then we end up with, if we go over here, we've got all the numbers that have 5 in that position, all the numbers that have 8 in that position, and we're getting closer each pass through here. We're never comparing the numbers to one another. And now we reform them into this list, and you can see it's getting closer to being sorted, but we're still not there. So we repeat it again, where we're talking about the 3rd digit. So the 1st, the 2nd, the 3rd digit. Do it again. Okay, so you can see the smaller numbers are already grouping up here. Then we have, for example, here, 5. This number has 5 in its 3rd spot, and so on. And then we reform it into a list again, and then we have to go one more time. So the number of times we have to actually do this process depends on the largest number, how many digits it has. So we have a couple of 4-digit numbers, so we have to split them up 4 times. If we had a 10-digit number in here, we would have to do it 10 times. Okay, so here's our last time. So now they've been split up. We're talking about the 4th digit. None of these have a 4th digit. This one does, and so on. And then we form them again into our list, and we're done. So when I say we form them into the list, I mean we just take the order that's already in these buckets. So we start here, all the way up to 902, and then we take this bucket. This one is empty, so this one, and we keep going. And now the numbers are sorted. So we never made any comparisons between the numbers in our list. Instead, we took advantage of a special property of numbers. So lastly, here's a nice animation of radix sort. I'll hit play. What we do is we take a look at that rightmost digit and we group them in those 10 buckets. So if we're talking about base 7 numbers instead, we would have 7 buckets. But we're talking about base 10, so we have 10 buckets. Okay, and now we reform them. You can see the order we're talking about. We just pull them out of the buckets in the same order that they're already stored in. And now we take a look at the second digit from the right, and we form them into buckets. Okay, and again, in this case, our largest number is a 4-digit number, so we're going to have to do this process 4 times. So that was 2 times down. Now we have 2 more. So now we take a look at the third number from the right. And numbers that don't have a number in that position, we put them in the 0 bucket. And we're almost there. We just have to take a look at the 4th digit from the right and group things into the correct bucket based off of that digit. So we're almost there. So a couple things to keep in mind. In order to make this work, we have to be able to figure out a digit in a number at a given position. So in the next video, I'm going to talk about some helper functions we need to write. For example, I need to be able to ask, hey, what is the second digit of this number? What's the 4th digit or the 1st digit? And most languages don't give you an easy way of doing that. We have to write our own method to do it. So that's what we're going to start with before we get to the buckets. Anyway, that's radix sort. It is a special case of a sorting algorithm that is not a comparison sort. It's an integer sort that works because of a special, I won't say loophole, but a special property. And it allows us to sort numbers very fast compared to having to do comparisons. Anyway, we'll implement it in the next couple of videos. All right, now that we have a basic understanding of radix sort conceptually, we need to implement a couple of helper methods so that we can actually write the main algorithm. And the first one that we have to do is called getDigit, or something like this, that takes a number and a position and returns the digit at that position. So we might have 1, 2, 3, 4, 5. If we called getDigit 1, 2, 3, 4, 5 with 1 as the position, that should give us this number. So this is the 0 position, the 1, the 2, the 3, the 4. So it's not, a string or an array. We start 0 over here and we move to the right. This is going the other direction. And getDigit is really important for sorting things into these buckets, right? If we have, we're starting the very first pass on this list, we need to take a look at this digit, the 0th digit in our example, and put things in the correct spot. Then the next time through, we need to look at this digit. So we need a method that will give us that digit. And unfortunately, there's no easy way of doing that out of the box. We need to write a method. So if you want to do this on your own, rather than breaking this up into 3 different videos for the 3 methods I'm going to show, I think I'm just going to combine them into one. I know that I'm going to combine them into one. I'm already recording it. The focus is not about this logic. The focus is on the sorting logic of radix sort. But anyway, if you do want to try these, pause the video and do it now. 2 strategies. You can do, you can convert to a string and then use, the correct index to access the number you want and then convert it back to a number. The only problem is that, as I already mentioned, the strings are indexed from the left side. So if somebody asks for position 0 of this, if you convert to a string and you get 0, well, that's going to be the complete wrong side. So you could do some math so that you can convert, working backwards using negative indices or something like that, then come back to a string. Or you can do some math. So this should only work with base 10 numbers, by the way. You don't have to make it work for binary. We don't need, a user. If we were doing other bases, a user could pass in what base, but assume base 10 numbers. So there's some math you can do. Each one of these positions represents a power of 10. This is the 10 to the 0th position, 10 to the 1st, 10 to the 2nd, which the way I learned it in school was not 10 to the 2nd, 10 to the 3rd. It was the ones place, the tens place, the hundreds place. So what you can do is divide by that power of 10 and then do some other math, which I'll show you in just a second to get the answer. Okay, so if you want to implement it on your own, pause it. Otherwise, here's a spoiler. Here's a solution. I just took this from Stack Overflow and it's called getDigit. It satisfies our requirements. Let me show you how it works. Let's say we're taking a look at a number like 73, sure, that number. And if we pass in, so if we did get digit of that, and I'm looking for whatever number is at this position, 0, 1, 2, so I'd pass in 2. The math is that this number here is 300, right? It's a 3, but in the context of this, it's a 300. So we're going to divide by 100. As you can see here, math.power 10 to the I. So 10 to the second, which is I, gives us 100. So we're going to divide this whole number by 100. So I'll write this out here. We can ignore the math.absolute value just for a second. That's just so that this works with negative numbers. If I passed in a negative number, this should still be 3. We don't want to get negative 3. This is just 3 is the digit we want. So that's what the math.absolute value is. So we'll ignore that. If we take this number and we divide by 100, which is what this is right here, and then we floor it down here, so we get 73.23. If we do a floor, we just get 73. Okay, so then we have 73 mod 10. So we divide 10 into there. How many times does it go in? It doesn't really matter, but it goes in 7 times. So we get 70. What's the remainder? Well, the remainder is 3. So if we do mod 10, we get 3, and that's what we're looking for. So we divide by the place, the hundreds place, then we floor to get rid of that decimal, then we mod 10, and that's the math. So just to prove that it works, run the code, and then let's pass in 0. We get the correct digit, also a 3. 1, we get the 2. 3, we get the 7. And if we pass in something that's not in there, we get 0. Perfect. So this works. We're all good. The next helper we need has to do with figuring out how many digits are in a number. And the reason we need that, if we go back here, is in this example, we need to know how many times we need to sort things into buckets. How many times do we have to, reorder everything? And the answer is 4, because the largest number we have has 4 digits. So that's our bound. If we have one 10-digit number in here, then we need to do it 10 times. So we need to write code to figure out how many times we need to run it for a given list of numbers. And all that we need to do is figure out which number has the largest or has the most number of digits. So there's 2 methods we'll write. The first one will give us digit count for a single number. And then the second one will use digit count to figure out the largest number of digits for the entire list. So we'll have, max digits, which calls digit count. So digit count, just you pass in a base 10 number, and it should return to you how many digits are in there. So this would give us 3 digits. This is a 2-digit number. This is a 1-digit number. You could do this as a string, convert it to a string, find the length, or you could do some math, which is what I'm going to do. So pause it if you want to try and implement this on your own. Very loud motorcycle outside. Otherwise, here's the solution. All right, I copied this solution over. It's called digit count, and there's a couple things we'll talk about here. So first things first, log 10. This is a log base 10, which what that does, if you didn't watch the log video early on in the course, it's basically asking 10 to what power gives us this number. So if I called digit count on, let's do 423. 10 to what power gives us 423? Well, it's not going to be a nice clean number. So that's why we do the floor. But let's do math.log 10 of 423 gives us this. And when we floor that, we get 2 because we're just getting rid of that. So our answer here was 2. And we're close, except that we need to count the number of digits, which we need to add 1 in, so we get 3. So just one more example, if we have a larger number like this, okay? We're doing math.absolute value again because we want it to work with negative numbers. If somebody passes in negative this number, it still has the same number of digits. We're not going to worry about negative numbers for our sort, but these are from Stack Overflow, and it's always good to be conscientious of that. So if we take this number and we do math.log 10 of that, and then we floor that, we get 4, and we add 1, which is 5. That's how many digits are here. 1, 2, 3, 4, 5. Okay, so if the math is crazy to you, don't worry. It works, and this is something I feel like it's totally normal to just take this from Stack Overflow and add this to your code if you really need it. So digit count, the only special case is if num is 0. So if somebody passes in, well, not there, but if we did this, this is a 1-digit number. But the problem is that if you try and do, math.log10 of 0, we get negative infinity. That's not what we want. So we have to add this special case in. Okay, that's digit count. And then our last method we need is called most digits. And this will take a list of numbers and just tell us which number has the most digits in it using digit count. I mean, it should use digit count because we just wrote it. I guess you could just do it again. So what I would do is take digit count and run it on each number in this list, and then keep a running tally of what the maximum is, and just return that number. So you don't even have to return which number itself had the most digits, just the count. So for example, in this list, it would return 5 because this is the largest number. It has 5 digits. In this list, it returns 2. All the numbers have 2 digits. So this one's the easiest, I think, because we already have this code if you just want to copy it. The focus, again, is not on actually writing these yourself, but I just want to walk through them. So most digits, here's my solution. It looks like this. I'll copy it over. And it just takes a list of numbers. And we start a max variable, max digits. It starts at 0. And then I loop through nums. And I'm using math.max, which if you're not familiar with, you just pass in 2 numbers. If I do 0 and 12, it's always going to give me the larger number. And so this allows me to, instead of doing like an if statement, if x is larger than my current max, then reassign the current max, I'm just setting max digits to equal the maximum between the current value of max digits and digit count of nums I. So for each number. So if I do most digits of, let's see, 23, okay, of this, at the beginning, max digits will be 0, and then it loops through, and it becomes 2, because the largest number we've seen so far has 2 digits. But then next time through, it's 3. Next time through, it's still 3. Then it's whatever this is, and it stays at that. So let's run this, and I get 8, because this number presumably has 8 digits. It does. I just counted. Yep, 8 digits. Okay, so these are the helpers we need. And now we can actually implement, in the next video, we can implement our radix sort using these. And the logic isn't that bad once we have these done. We don't have to worry about recursion or any sort of crazy logic. We basically just loop over and split things into buckets and then join them together and do that X number of times, where X is the number with the most digits. Okay, see you then. Hey, welcome back. Time to actually write radix sort. So if you watch the video on the helper methods, that's actually the harder stuff. Now we just call those helper methods a couple times in the loop, and we make the buckets, and that's kind of it. So here's the pseudocode if you want to add this yourself. Define a function that accepts a list of numbers. Just call it radix sort, something like that. And then the first thing we have to do is figure out how many digits the largest number has. Well, we just wrote that method, most digits. If we go back here, we need to figure out, all right, which number has the largest number of digits, or what is the largest number of digits in any of these numbers. And in this case, it's 4. There's a couple of 4-digit numbers, or there's more than a couple. So we're going to need to loop 4 times, because we're going to need to sort them into buckets for this digit, this digit, this one, and this one. So 4 different times. If we had a 6-digit number, we need to do it 6 times. So once you figure that out using the method we just defined back here, then you need to start a loop from 0 up until that largest number of digits. So if we're doing this 4 times, we need to go from 0 to 1 to 2 to 3. And each time through, we're going to create buckets for each digit. Now, a bucket is just an empty array. So we'll have an array that has 10 subarrays. That's how I would do it. And they all start empty. So index 0 of this array starts as an empty array. Index 1 is an empty array. And then each time through this loop, we're going to take each number, put it in the correct bucket based off of its kth, that's a really difficult thing to say, its kth digit, meaning that whatever this loop k is, we start at 0, we're going to put it in each number in the correct spot, correct bucket slot, using the 0th digit, and then the first digit, the second digit. So if we go here, right, if we run sort, go, first thing we do is we make these buckets. Here's our 10 buckets. Each one of these is an array inside of one larger array with 10 slots. And this is index 0, this is index 1, index 2. So all that we do for any number, which one's next? All right, so 10, we take the 0th number, which also happens to be a 0. So we take this number and put it in the slot 0, index 0. And we keep going. So here we go, we take the 0th number of this. We already wrote a helper method to do that. We called it, what did we call it? Digit, get digit, something like that. So get digit index 0 is going to give us 7. So we put the whole number in slot 7. So we keep going with that. And then the next time through our loop, we're going to look at index of 1, and then index of 2, index of 3. And then the other thing we have to do is replace our existing array with the values in the buckets. So this is where we reorder them a bit. So in this example, we put them all in their correct buckets. Can speed this up a little bit. And then at this point, we reform them into a list using the order that they're currently in. And there's a couple easy ways of doing that. You don't have to loop through manually and do this. I would just concatenate into a new array. And so we just keep that order, and then we start the process over. So there's going to be 2 loops. There's the outer loop, which happens 4 times. So we're looking at digit 1 or 0 in all the numbers, digit 1 in all the numbers, 2, 3 in all the numbers. And then we need an inner loop to actually do something to each number in the list. Okay? And then at the very end, return that list. So I'm going to implement this in the next video. Totally fine if this one is a little challenging. It's always fine. It's not my place to say that. But this is one that I think if you look at the code itself, the solution, ignoring the actual math from the last video about finding the digits and log 10 and dealing with modulo and all that stuff, the logic in the sorting function itself is relatively straightforward. So we'll do that in the next video. All right, so we have the pseudocode laid out. We have our helper methods written. Let's write the logic. So the first thing I'll do, I need my helper methods, so I'm going to keep those. And I'm going to define a function called radix sort. And it takes a list of numbers. And the very first thing after that, we need to figure out how many digits the largest number has. So we have this method, most digits. So let's make a variable called most digits or something like that. Max digit, let's do that. Max digit count equals most digits of nums. And then let's just print that out so we can see that it works. Okay, and then let's call radix sort down here and pass in a list of numbers with a couple of small ones, some larger ones. Okay, so what is the max digit count of this? Well, it looks like it should be 4. The largest number we have is a 4-digit number. If we run the code, we get 4. All right, so now we know we need to loop 4 times. So we can start with that. Loop from k, it doesn't have to be k, but k equals 0 up to that largest number of digits. So let's write a for loop. For let k equals 0. K is less than max digit count, k plus plus. So this gives us an index k going from 0 to 1 to 2 to 3. So we can use that and pass it into this method get digit. So we can ask for the 0 digit or the third digit. Okay, now that we have that written, we need to make our buckets. So I'm going to make a list. I'm just going to call it digit buckets with 1b. And we could, manually construct this, make an array, and then push in 10 empty arrays. But there's also an easy way, relatively easy. If we do array.from, and then in here, right here, if we pass in a length, set it to be 10, and then we tell each one to be an empty subarray. So if I just copy this over here and paste it in, if we look at what digit buckets is, it's an array of 10 empty arrays. So if I changed it slightly to be an array containing the string LOL, we end up with 10 sub arrays, each with LOL as their one element. Not what we want, but we want an empty array. So now we have 10 buckets, 10 slots inside of this one larger bucket called one array called digit buckets, and they're all empty. Now we need to loop over every number. So this part's easy. Let's just do for let I equals 0, I is less than nums.length, I plus plus. So for each number, we're now going to take that individual number, which is nums I, and we're going to figure out at position k, so at index 0 of each number, what value do we get? And then k will change, of course. So we're going to do get digit of nums I, comma k. And so that will give us digit 3, 5, 7, 2, 5, the first time through. And then k will go up, and k will be 1. So then we'll look at this number, the index 1 number. And then I will go up again, and we'll keep going. So we don't just want to get that number. We want to take that number that comes back, and then put nums I in the bucket at that index. So if I just print this out right now, it's going to be pretty ugly, but you'll see what we end up with. If we run our code, it's a lot of console.logs, but the very first time through, we end up with 3, 5, 7, 2, 5. So 3, 5, 7, 2, 5, 2. So we need to take those numbers. We need to put this number at index 3. This number, we got 5. We need to put it at index 5. So we could just do this. We could do it in one ugly line, which I don't like. Digit buckets of that result. So digit buckets of index 3 or index 5 or whatever we get back, dot push nums I. Now this is kind of a gross line in my opinion. I'm going to break it up. But if we actually do this, and let's just do it one time, and then let's just print out at the end of this loop digit buckets. You'll see, I don't want to count my eggs before they hatch, but everything should be in the correct spot. Like the first time through, we end up with all the numbers that have 2 as their first digit are in the 2 bucket. We have 23 in this bucket. We have these numbers that end with a 5 in the 5 bucket. So that's all working, but I just don't like how long this line is. So I'm going to break this up a little bit and make a variable called digit, just like this. Whoops, copied one extra part. And then we'll do index of digit, push nums I. So we're going to get the digit, so that will give us 3, and then this is just a way of breaking up the code. Digit buckets of 3 dot push the number. Okay, so we're almost there, but the one thing we're missing is after we break them into their buckets, we need to recollect them into a new array and do the same thing. Otherwise, we're just keeping them in the same order and then just sorting them into buckets. So we're sorting them based off of their first number, and then we're doing the same thing based off of the second number, but we're never actually ending up with a new order to the main list called nums. So we need to, afterwards, right here where we're printing out, after we've put them in the correct buckets, we need to then concat the array. So there's a nice easy way of doing this in JavaScript. We reassign nums to be array.concat, and then I'm going to use spread digit buckets. And I use the spread operator, the special syntax with the 3 dots, which if you're not familiar with it, it allows me to pass in all the arguments or every element in digit buckets as an individual argument. And the reason I need to do this, rather than just passing in digit buckets, is if we imagine, here, I'll do it down here, if I do a .concat, and let's say that I have 3 arrays, because this is an array of arrays, right? What we're looking at here. So let's say that digit buckets looks like this. It's very simple, but let's say it looks something like this. If I call array.concat, it's going to concat these into a new array, but they still are in separate buckets. If I want to take these numbers and just combine them back into the original form, so this, but in a different order, if I use the spread operator, the ... I end up with just the values there turned into a new array. So this is what I want. This is a nice, easy way. I don't have to manually, you could loop over digit buckets for each bucket, loop over all the values in that bucket and push them into nums or a new array. But this is a nice, succinct way of doing it. And that's all we need to do aside from returning nums. So let's do that. And let's see if it works. What I would like to do here is do a console.log. Let's go with digit buckets here. And then afterwards, after we concat back into nums, console.log nums. Okay, let's run the code. All right, so first time through, we end up with everything sorted, or not sorted, but everything put into the correct bucket based off of the 0 digit, the first one from the right. Then we concat this. So the order is preserved. Think of it as just smushing them all together into this array now. Nums looks like this. So we have 12, digit 2, followed by 9852, which ends in a 2, and then what ends in a 3 and a 5, and so on. So we took this order and just smashed them together. Then we went through and put them into buckets based off of this number. So you can see them here. So this is in slot 1, bucket 1. This is in bucket 2, bucket 4. And then we concat them again. So we keep this order and we end up with this. So each time we get a little more sorted, then we do it again and we look at the index 2, 0, 1, 2. So some of the numbers don't have a value there, in which case they're in the 0 bucket. So the smallest numbers are already in the correct bucket, but the 3 and 4 digit numbers are still working their way to their correct spots. So we concat again, we end up with this. And then one more time, we put them in buckets based off of their index of 3 number, what digit is right here. And then we concat, we end up with this, we're done, and we return that. And that is radix sort. So I think it's kind of a fun one. Once you actually write the methods or you find the methods on Stack Overflow for getting a digit, counting digits, finding the most digits, the logic itself can get rid of the console.logs is relatively straightforward, I think. Aside from this, if you haven't ever seen this operator, this is just a simplification, a nice short way of doing this. But the idea of what we're doing, I think, is simple. We're separating things into buckets based off of a digit in a given position, and then we reform them into a new list or a new array, and then repeat it on the next digit for all of those numbers, and keep going until we've done it for every digit in the largest number. All right, so we'll talk about Big O in the next video, and then we are done with sorting algorithms. All right. Welcome back. All right, let's wrap up radix sort quickly by talking about its Big O notation. Now, I should start by saying that there's a little controversy around this, and there's room for argument around radix sort, but here is the generally accepted notation. So time complexity for best, average, and worst is O of nk. So n is the number of things we're sorting, the number of numbers or integers. K is the length of those numbers, what's often called the word size, though for a number, it's not really a word, but the number of digits. So if we have really, really, really long digits, that's important to consider. It's not just a constant we can ignore, that's always the same. It's not like 2n or 3n. If we have really long numbers, then that does significantly impact the time. So n, the length of the array, the number of numbers we're sorting. K, the number of digits in those numbers. And the reason I say it's controversial is that this can be significantly better, on paper at least, than a comparison sort, which best case for their average is O of n log n. If we go over to Wikipedia, to the radix sort page, down to efficiency, there's a relatively large two paragraphs making two arguments, an argument and a counter argument about the time complexity for radix sort. And it has to do with how numbers are actually stored in memory on a computer. And if all the numbers are distinct in our whatever we're sorting, if our list contains all distinct numbers, then according to this, K, or what they call W, has to be at least log n. So if we plugged log n for K, that's going to give us n log n, which is the same as what we talked about for a comparison sort. So that's one argument, which is if you're dealing with all unique, randomly distributed data, then This simplifies, or it doesn't simplify, this becomes n log n because of the way that computers store numbers or store information. I don't have a great understanding on exactly why that is, but if we accept that, that means that radix sort is equally as good in the average case. If we're talking about nk, where k is log n, it's the same as n log n. Then there's a bit of a counter argument down here that says, well, actually, fine, if you're going to say that radix sort isn't as fast as it claims to be, then we're going to talk about some of the problems with comparison sorts, and that there's actually shortcomings in how random numbers are compared, and that it's a little slower than you expect. It's not something that I can speak on myself at all. I actually have always assumed that it was for radix sort O of wn or kn, where k or w is just the word size. And that's what pretty much every textbook or big O cheat sheet type thing that I've seen says. Then I went to just double check and fell into this rabbit hole. So keep that in mind, I guess. So theoretically, radix sort can be faster than any of the comparison sorts. But apparently, because of limitations on how computers actually store numbers in memory, that may not actually be the case, and it might just be tied with comparison sorts. But either way, I think that radix sort is a fun algorithm because it's sort of quirky. It takes advantage of a specific feature of our data, of numbers, and that we can use the digits in any given number and the number of digits in those numbers to sort things without having to ever directly compare any numbers. We're never checking what's larger or what's greater. We're simply moving them into buckets and then regrouping, moving into buckets, regrouping. So yeah, I like radix sort. It's a fun one. Cool.